I want to give you an overall picture. An overall picture. Let me go to the last slide. Have a look. Oh, there are so many things. At this left hand corner, I have the Schrodinger equation surrounded by cloud. The cloud shows that it is something something hidden, or uncertainty is in a way implied. By solving Schrodinger equation, by using quantum mechanics for various systems, we learn about the energy levels in atoms. See, energy levels and the electronic configuration. A sample is given here, 1s2, 2s2. These are familiar things. They essentially come from quantum principles and quantum ideas. So we learn about atoms. We also learn about metastable states and then lasers. Lasers is the outcome of quantum mechanics. And if you go to molecules rather than atoms, you have the concept of rotational vibrational energy levels, which explain the molecular spectroscopy and Raman effect, and host of things, starting from quantum mechanics. That is about atoms and molecules. You think of solids. Here is an example. Solids. When you try to explain the energy bands in solids in terms of quantum concepts, this is the classification that comes to us. On the basis, I think this is known to you, but essentially it has come from quantum mechanical ideas. These things were developed 1930 or so. And so in the insulators, there is a large band gap between the valence band and the conduction band. In metals, it is almost overlapping. Metals are conductors of electricity and heat. Semiconductor is something in between, and you pick up from here, as that was done in 1948 with the invention of the transistor. You pick up the things and try to see how technologies can be developed from transistors. As I said, you went further, and the whole of the things. This all may be summarized into just one word: quantum revolution 1, which comes from quantum mechanics. It is one, so fine. Is there any quantum? Is there any second quantum revolution? Yes, yes. We are presently witnessing it, and you and we are so lucky that we are in the third decade of the 21st century, and the second quantum revolution has started. Thank you so much. This is all I had in mind. Thank you so much.
Thank you very much, sir. Any questions from the audience? So, not if there are no questions, not without wasting much time. Sir, आपको थोड़ा सा ये वो करना पड़ेगा, unpresent वो करना पड़ेगा यहाँ से.
Stop sharing.
Stop sharing. So now I request Professor Sarah, who is Director, Institute of Gravitational and Cosmos at Penn State, USA. She will be speaking on gravitational waves and dark matter discovery. Welcome, ma'am.
Great, thanks.
Continue your talk. Thank you.
Thank you. So I need to share my screen.
Yes, you share and then you share entire screen and go to your PPT. This is the most easiest way.
Okay, do you see this full screen?
Yes, please start.
Okay, great, super. Okay, thanks. Great. All right. Well, good morning, everyone. Thanks so much for having me. I wanted to talk today about a really interesting opportunity, which is one of many that gravitational waves bring us, which is an opportunity for a discovery related to dark matter. So I'm a cosmologist. I study this beautiful big universe. The image that you're seeing is artist's representation of the evolution of the universe. And we have both this envelope on the outside, which shows us how the universe expands. And we have this detail on the inside, which shows us how the little inhomogeneities or density perturbations evolve from something that's pretty smooth and homogeneous all the way through to this absolutely beautiful structure that we have in terms of galaxies here in the present day universe. And this universe is full of questions. We don't understand many things about this picture. We don't understand how it started, this big flash here. We don't know the role of gravity and quantum gravity yet. In the center, we don't know the details about how structure has formed. We know many of the basic ideas, but without knowing what the dark matter is, what all of the particle physics of the matter in the universe is, we don't know how to tell this story completely yet. And over here toward the present day universe, as you know, we have this puzzle of accelerated expansion that's difficult to explain in terms of fundamental physics. And we have this absolutely wonderful collection of extremely dynamic and high energy events, including the mergers of black holes and neutron stars that LIGO has observed. And so somehow we want to understand the sort of deep underlying principles of the universe, what kind of matter is out there, what are the fundamental laws, by looking at this fascinating tableau of phenomena. And what's interesting about this is that this picture is mostly built up by data that comes through us through electromagnetism, so through light. Only very recently have we added other messengers to this picture, so high energy particles, cosmic rays, neutrinos, and the purpose of this seminar, the gravitational waves. The gravitational waves are extremely important because electromagnetism can't see everything. Not everything carries a charge, not everything interacts electromagnetically. But as far as we know, everything does interact through gravity. Gravity is universal. So gravity can help us see things that our own eyes cannot see. And one of the reasons that's very important is that we know from gravity that most of the matter that's out there, in fact, doesn't interact through electromagnetism. It only interacts, as far as we know, through gravity. This is a picture of a particular part of the universe where you're seeing several different images superimposed. You're seeing visible light. That's all the things that look sort of like galaxies, right, and stars in the picture. You're seeing hot gas, which is at a different temperature. And there's a lot of that compared to the visible stars. And then you're seeing this stuff in blue, which is a representation of all of the matter that's there, not just what's in visible light, not just what's in stars, not just what's in gas. This is the dark matter. And, dark matter we understand extremely well in the world of general relativity. So we know how to put it into the Einstein equations, treat it basically as a fluid, and understand how it affects the evolution of the universe. What we don't know is what the particle physics of that dark matter is. So it's sort of like knowing that water exists without knowing about hydrogen and oxygen. And that's what we'd like to do. We'd like to understand what is the particle physics? What's the equivalent of that hydrogen and oxygen that makes up the dark matter? And the way that we know this, coming from that picture, one of the ways that we know this goes back to just this idea of how do we see the sky in terms of electromagnetism. And so what I'm highlighting here is the light from stars. Those are the usual pictures that you see, the optical images. And of course, one of the remarkable things about the universe is that there's an extraordinary amount of light out there that's not what's visible to our eyes. So all the way from radio, the microwave, the infrared, the UV, the X-ray, the highest energy stuff, the things we call gamma rays. So really, already this is one of those great lessons in humility that the way that we as humans observe the universe is only a tiny, tiny fraction of what's out there. So what we see are these few frequencies of visible light, and to observe the universe, we've understood how to take this enormous electromagnetic spectrum and put together images of what's out there. So that was what was happening in that image there. There were different wavelengths of light. But the second thing that we can do is understand how gravity bends light. So just as gravity affects everything, and light passing through gravitational wells, in this image you see light from a distant galaxy toward us through this image of lensed galaxies, these lensing galaxies, and the matter here in these lensing galaxies distorts the light so that some of the light that couldn't have reached us if this lens hadn't been here, that would have gone out to infinity, is able to be bent and come toward us to the Earth. So the image that I showed you originally is this combined picture where you're seeing images across the electromagnetic spectrum. And then in addition, you're seeing a picture of how the light is bent, how it's distorted, the light coming from the background through this cluster of objects here. So by putting those things together, the bending of light tells us where all the matter is, and then across the electromagnetic spectrum, it tells us where the type of matter that we're familiar with lives in the stars and in the gas. So again, what does this have to do with your symposium, with your seminar? Well, the dark matter doesn't emit light, but it does gravitate. And we're in this really wonderful era where we have this new view of the universe that's purely from gravity, so gravitational waves. So this is a different version of the image that you saw from Gabby a few minutes ago, where it's showing up until, prior to '04, so this is really just about half the total events that we have. The image is showing you all of the different events that are mergers, and on the y-axis, it's showing you the masses of those objects. So you see each of the little merger images has a blue dot and another blue dot, two of the black hole objects that merge into a final blue dot, which is a heavier black hole. Along the bottom, it's also showing you images, representations of objects that were detected electromagnetically. So even though these things are black holes, of course, black holes live in an environment where they're, eating up a lot of matter, and that matter is emitting a lot of light. So we are able to, of course, detect black holes and neutron stars gravitation or through electromagnetism, but LIGO has given us a new view where we don't have to rely on that light. We have gravity only. So what do we do with this? Why is this interesting? What does this have to do with the story of all that matter out there that we don't yet understand? Well, we want to know where these objects came from. And that's an interesting question because although LIGO is incredibly good at telling us that these are black holes, it doesn't tell us where they came from. And an interesting fact about black holes is that you can't really ask them what they're made of, where they came from, right? A black hole is a black hole no matter how it got there. So why does that matter? Well, one place that black holes could have come from, and we know that they do, is in stellar processes. So all of the complicated physics of stars goes into these pictures of life cycles of various stars depending on their mass. And there's a lot going on in this picture. But for our purposes, we're interested in the fact that stars form in the early universe, and they have a variety of evolution pathways. And some of those evolution pathways end up in explosions of stars and these very compact objects that are the neutron stars and the black holes. So these types of objects that we sort of know their pathway to formation are a lot of the focus of understanding where the black holes detected by LIGO came from. And there's a lot of complicated physics in this picture, but there's sort of one really key fact about the matter that we know that enables this picture to be possible, and that's chemistry. So the whole reason that we can form stars in the first place is that all of the hot gas in the early universe that's in these big gravitational wells that made by the collection of dark matter, that matter is actually able to cool. And when the matter in those big potential wells can cool, it can start to clump, the gas can start to fragment, and you can get these very dense regions of the gas where you can actually have compact objects that our stars can form. And the reason that the gas can cool is that it has chemistry. So a simple example on the bottom would be in a gas in the early universe, the primordial gas, that's mostly hydrogen with a few electrons. And you can imagine a fast, hot electron coming in, hitting a hydrogen. It puts the hydrogen atom in an excited state. This is the beautiful quantum mechanics we heard about in the last talk. And the electron goes off a bit slower. That excited state of hydrogen can then emit a photon so that the hydrogen relaxes back to the ground state. And if that photon can completely escape its local environment, then the gas has cooled. The hydrogen and the electron are a bit slower, a bit cooler. The photon has escaped and the gas has cooled. And you often see plots where you can imagine a clump of gravitating matter, sort of in a free fall gravitational collapse. So its density is increasing. This is on the x-axis. This is the number density. And the temperature of the gas, as that number density is increasing, can go down because of these cooling processes. And there's some limit where you can't cool anymore, and the temperature can go back up. So that process of gas cooling is one of the ways that we know the black holes of LIGO originate. But there's a lot we don't know about the universe, and there are a number of ways that black holes could have formed that are not those simple stellar processes. So people are excited about the possibility that we can understand the origin of the black holes of LIGO, and is there a chance that we can understand if all of the black holes came from the processes we know, or if black holes could have had a different origin. There are a couple ideas for how that could be. The first one, which is what I'm going to focus on, is the notion that, in fact, dark matter, there's so much dark matter out there, we don't yet know its physics. Could you actually form black holes from dark matter? And the second idea, which has been popular for a very long time, is the notion that maybe black holes themselves are part of the solution to dark matter. So you might imagine that very early in the universe, you have these very big fluctuations that form black holes, and those things themselves can be part of this mysterious matter that we don't understand. So let me just tell you a little bit more about those ideas. The idea that there have been black holes out there for a long time usually goes by the name primordial black holes. And to make a primordial black hole really, really early, even before this CMB picture, the notion is that you have to have very large fluctuations in the density. So this is the density contrast, delta rho, the difference from the background density, normalized by the average background density. And if at very early time, so very high redshifts, you had fluctuations that were pretty big, from just the origin story of the universe, then as soon as those fluctuations sort of became of order the size of the present day horizon, they could collapse, taking all of the matter with them, and form early time black holes. So we can put some perturbations on this picture, but very roughly, in order for that to happen, you need density perturbations in the early universe that are much, much, much larger than the little things that we know on large scales produce the CMB, and the fluctuations in the temperature of the CMB, and produce the structure that we know. So this idea involves modifying physics at very early times in order to get this very, very old population of black holes. On the other hand, you can modify physics at later times in the sense that you can ask, well, what is the dark matter? And if the dark matter itself has some complicated particle physics with some chemistry, then you get black holes that form more on the timescale of standard model matter. So you get later time forming black holes that form because of chemistry. And these different ideas and ideas related to these, of course, are not distinguishable in and of themselves by the black holes that LIGO sees, but they do give you two very different pictures of what's happening in the structure formation of the universe as a whole. And so scenarios like these are distinguishable by other aspects of structure formation that go hand in hand with the black hole picture that we're building up. Another contrast to these scenarios is that often people talk about these early time black holes making up all of the dark matter. There's a long history of that idea. On the other hand, if you have dark matter that's producing some black holes, the story is a lot more like in the standard model, where there's lots and lots of standard model matter, and only a small fraction of that matter is actually in black holes. So in this scenario, you have a complicated particle physics of dark matter, and a tiny fraction of that ends up in black holes, but that fraction is powerful enough to tell us something about the particle physics itself. Okay, so why should we think about this idea that some black holes may have an origin that's outside of stellar processes? And in particular, why should we think about this in the context of dark matter? Well, the standard model that we have has this spectrum, sometimes this little represented as this little wheel of fundamental particles. We have of course, the Higgs boson here in the center. Its sort of central role of helping to give mass to many of the particles in the universe. We can see the quarks. We can see the electromagnetic sector, right? The electron and its heavier friends, the neutrinos, and the weak particles and the force carriers here in the center. So the standard model is complex. On the other hand, we often think about dark matter as being just one very simple thing. And this familiar picture of dark matter that's been around for a long time is a single particle that doesn't do much. It doesn't interact with anything except just enough to be produced in the early universe. And of course, it interacts gravitationally. But we don't know that's the case. It need not be the case. And there's been historic interest and sort of a resurgence of interest in scenarios where the dark matter itself is made up of multiple particles. So maybe not as big of a wheel of complexity as the standard model, or who knows, maybe bigger, but at least some little wheel of complexity, which are some different, perhaps a couple different force carriers, perhaps some different fermions or bosons here that make up the dark matter. There are lots of reasons you might think about that from a particle physics perspective. I'm happy to talk about that if there are any questions. But for now, let's just leave it at a motivation that the standard model is complex, so the dark matter may be complex as well. And if the dark matter is complex, so here's another little cartoon of the standard model versus dark matter, complex in the sense that it has a rich spectrum of particles with some charges, some force carriers, some masses, then that dark matter probably has a rich spectrum of matter on small scales, a rich spectrum of structure on small scales, somewhat analogous to what the standard model has. And what's fascinating about this story is that even if we can only detect this structure gravitationally, as we map out the masses and the densities and the types of objects that are out there, that actually is a pretty strong constraint on the particle spectrum, on what the fundamental nature of these little dark matter particles is, even though we're only getting that information gravitationally. It's actually a wonderful paper from a few years ago by Matt Buckley and Annika Peter that imagined that you're a physicist made of dark matter, and they go over the extent to which you could actually determine a lot of the structure of the standard model just by looking gravitationally at the universe around you, just by looking at these structures that are formed. So this gives us actually an opportunity to use gravity as a particle physicist, to use gravity as a chemist to figure out what the structure of these particles is. And that's true even if we're not able to directly detect the dark matter. So there are many ways to look for dark matter by looking for interactions between this matter and this matter. Many famous searches for dark matter particles operate that way. So far, we haven't been successful. That route hasn't taught us what the dark matter is. This gravitational route to discovery doesn't require that this interaction be strong enough for us to detect any time in the future. So it's really an alternate route to get at the particle physics of dark matter that relies on a different set of physics. So it's extremely complementary to what people do in the laboratory. There's another reason to think about this, and that is that our understanding of dark matter is extremely clean on large scales. So even though this little spectrum of fluctuations may not look large, they may look like small dots. This is on the scale of the entire sky. So when we think about what happens in the cosmic microwave background, that's actually pretty large scale physics, and it's extremely clean. It hasn't had a lot of this nonlinear clustering of gravity acting on it yet. And again, these pictures of light bending, especially on pretty large scales, this is again a pretty clean probe of dark matter, the largest scale of clusters. So there we understand dark matter, we can model it, we have lots of good criteria about how it acts. Facts and constraints about how it acts. People have been very interested recently in understanding what happens with dark matter on smaller scales. When you really look deep in the interior of galaxies, especially small galaxies. This is a little bit of an old plot by now, but there's a notion that when we go out and observe the universe, it doesn't look exactly like what our simulations, based on a very simple model of dark matter, where the dark matter doesn't do much. There's some tension here. But this story about what happens on the interiors of galaxies is extremely complicated because there's so much complexity of the standard model physics in here as well, right? It's forming black holes, there are supernova, there's all kinds of energy being washed around by all kinds of complicated physics. So there are hints from these scales that maybe dark matter is more interesting than a single particle. Maybe interactions of dark matter particles themselves are needed to explain observation, but it's a very difficult picture to really figure out correctly because there's so much complicated physics. On the other hand, if we think about things like compact objects and LIGO's data is extremely clean, right? We know for sure that those were ultra compact objects that collided, and we know their masses. So it's a very clean probe. There's no question about, is there some phenomena that originates here or here? We know those objects are there. It's a very clean probe. And that gives us actually a very interesting handle on dark matter for a reason that I'll come back to. Let me just say for a second again that this really is a sort of a new and complementary way of thinking about dark matter. You very often see this cartoon where people say, how can we discover dark matter? And they consider different ways that dark matter and standard model matter might interact. And they say, well, if we take two visible amount of particles, two standard model particles like protons, and smash them together, let's say in colliders, maybe we can produce some dark matter and find it that way. So far, we haven't found anything by that route. They sometimes say, well, there's a lot of dark matter in the universe, and there must be processes where dark matter out there smashes together, interacts, and ends up creating, for example, unexpected light. That's indirect detection. That's another way we might look for dark matter. And that route, so far, again, there's no definitive detection. And finally, people say, well, what if we we build a big vat of some material and wait for dark matter to come in, hit the matter, and we'll see that interaction and test and know what dark matter is. That's an extremely good way to look for dark matter. And there's been this very successful program of looking for dark matter in big vats of things like xenon. And the constraints have come down and down and down, and still no detection. So the perspective of gravity and dark matter is that rather than this picture of really focusing on interactions with the standard model, let's just focus on the fact that dark matter gravitates. That in of itself gives us a route to the particle physics. Okay, and that's why this hidden sector route, where instead of focusing on this interaction between dark and standard model, but instead focusing on interactions that may be between dark matter particles and relying on gravity to pass that message to us, is a very complementary perspective. Okay. So there are lots of ways you might think about complex dark matter. I'm going to talk about just a couple of ideas where we take this slew of particles that we know from the standard model and sort of take over a couple of those ideas and ask what would it look like if the dark matter was sort of similar to the standard model, but maybe not quite as messy. So we're going to take a couple of these particles. We're going to take the proton, the electron, and the photon and modify them just a little bit. The photon and the electron, we're going to take over the notion of those particles almost exactly. So something that is the force carrier, a massless force carrier, and a particle that is fundamentally a spin a half, fundamentally a fermion. That's going to be our electron. But it's a new electron and new photon that live only in the dark matter. The proton is a complicated particle. It's made up of quarks. That's a little too complicated for my taste right now. So let's simplify the proton. Let's not have it be made up of quarks, and let's say that it's a fundamental fermion as well. But let's keep the proton in the sense that we're going to make it a fermion, and we're going to keep the opposite charge of the electron. So this is going to be a positively charged particle, a negatively charged particle under this new force, which is in the dark matter itself. The reason this is an interesting model is that you can get the cooling channels that you need to form structure. But perhaps more importantly, we have this very famous relationship from Chandrasekhar about what the minimum mass of a black hole is. And that mass in the standard model is about a solar mass. But if we change the masses of the proton and the electron, in particular the proton, the heavy particle here, we can produce black holes that are much smaller. And they're lower than a solar mass, scaled by 2 powers of the mass of this heavy dark particle. So what that means is that a very simple model that's a little more complicated can give you black holes, and black holes that cannot be confused with anything that comes from standard model processes. Black holes can be below a solar mass. So a model like this gives you a very distinguishable feature in the black hole spectrum, and it gives you the cooling that's exactly like that picture of the hydrogen and electrons bouncing off each other and emitting photons that allows some of the dark matter to cool in the universe, which allows black holes to be dynamically formed. So this is an idea that many people have played with, and the reason it's interesting is that there's an enormous discovery space in gravitational waves. So you often see plots for gravitational waves that actually cut off at 1 solar mass, just because that's what most of the matter in the universe that we already are familiar with does. But it doesn't have to be, right? There's 85% of matter out there that's something else. We don't know what it is. And the ability of LIGO, even older LIGO and current LIGO at design sensitivity and future things like Einstein telescope have an enormous potential to explore. So all of this space where the chirp mass of the binary, which is this combination of well-measured masses, all of this space would be empty. There should be no events if we have a standard model of physics and astrophysics. So this is the discovery space for LIGO and dark matter. You can estimate if these rates are likely. I won't say too much about this because I realize time is getting short, but we did this some years ago and a number of other groups have done it. And, it doesn't have, there only has to be a tiny fraction of the dark matter in black holes, about 10 to the minus 5, in order for this to be detectable with LIGO. So this table is showing you for different values of the sort of dark proton, these new particles in the dark sector, what the Chandrasekhar mass is. It's pretty low, 10 to the minus 5. but you can produce black holes through this cooling process that are somewhat heavier, around a solar mass, a tenth of a solar mass, a hundredth of a solar mass, and those things are detectable by LIGO in principle. So this is very interesting and very promising. And in fact, LIGO does a subsolar mass search. It's separate from the main search because it's computationally expensive, but there have been searches through 03, and the fourth observing run subsolar search is in progress. And there has been no detection, unfortunately, but you can use the fact that there isn't a detection to already put new constraints on dark matter. And the way those constraints go are a constraint on the fraction of dark matter that can be in black holes. That's this fraction in these dark black holes, as a function of the minimum mass of the model. So LIGO can't see arbitrarily light black holes, so you see the constraint doesn't extend too low. But for models where the lightest black hole is somewhere around a tenth of a solar mass, we know that indeed not more than about 10 to the minus 4, 10 to the minus 5 of the dark matter can be in black holes. So that's a really important and unique and complementary constraint on a lot of scenarios that really comes just from gravitational waves. Just say one other thing, though, which is that we don't understand fully all of the events that have been detected by LIGO. And in particular, there's this really interesting event that has been classified as a binary neutron star, but looks very different from the binary neutron stars that have been detected electromagnetically. So here's the mass of the system. These are the masses of known binary neutron stars detected by other means. And this is an event seen by LIGO. And we don't know what this is, right? LIGO right now doesn't have the ability to tell if these are neutron stars or black holes. It's not clear. And so they're classified by their masses alone. But you could ask, what if this was a dark black hole? And this was some very lovely work led by a graduate student at Penn State, Divya Singh, where she showed that, in fact, if this was a black hole produced by dark matter, you would already know, for example, that based on this Chandrasekhar limit, that the mass of the dark proton is heavier than the mass of the standard model proton. So without saying too much of detail, this beautiful relationship about the mass of particles, fundamental particles, into the mass of black holes can be used directly by LIGO to teach us something about the particle physics of dark matter. There's some more complicated things you can say because these black holes, of course, form by cooling. And so thinking about that cooling process, you can constrain. But I won't say more about that unless there's a question. Okay, so let me just wrap up and say, with gravitational waves, we have this remarkable new view on the universe, and nothing escapes gravity. Every type of matter that we know, every type of particle that we know gravitates. That means that there's an enormous potential for LIGO and any other instrument that's looking at gravitational waves to teach us something about physics that we don't yet understand. All of those open questions in the universe. And what's really beautiful about gravitational wave probes of dark matter is that through the presence only of these gravitational objects, where the only thing we know is that they're massive and they're black holes, we can use that information, that purely gravitational information, to do particle physics through the beautiful Chandrasekhar relationship and through sort of all of the chemical processes that happen as structure forms in the expanding universe. So there are many discoveries remaining to be had with gravitational waves, and some of those may be very surprising, and there's even a potential for gravitational waves to help us uncover the nature of dark matter. Okay, I'll stop there. Thank you very much.
Thank you very much, Dr. Chandra. It was very nice to hear you. But you have established that gravitational waves can see what is unseen about the dark matter and dark energy, which is actually for this basic level, which is most of the attendees are UGPG students. So it is very nice to see that it is established as a new horizon by the uses of gravitational waves. Thank you very much for introducing us with this particular interesting topic, the use of gravitational waves. Thank you very much for being with us.
Thank you for having me.
One student has a question. Yeah, please come here. Yeah. So,
greetings. My name is Deepnil. I wanted to ask a question as we have heard about Einstein-Rosen bridges and we know about exotic matter. So is there a possibility that whether we can use dark matter as a solution to that?
as a solution to use it as exotic matter. That's a great question. Of course, I don't fully know the answer because I don't know what dark matter is. The one thing I can say is there's so much dark matter out there in the universe that we have many, many examples of how it does behave, because there's a lot of it out there. And so far, there's no clear suggestion that it's exotic in that sense, right? We don't see, it'd be likely, I think, that if dark matter was exotic, we would see phenomena that were sort of surprising, that didn't look, like other matter. So we're pretty sure that dark matter is not exotic in that sense. That doesn't mean that there aren't surprises in some corner of the universe out there for us to discover.
Thank you so much.
Yeah, Professor Sen Gupta wants to say something. Yes, sir, you can.
Yeah. Hi, Sarah. Thanks for the very nice talk. So one comment and a question. So you mentioned that, the LIGO searches for subsolar mass binary black holes, they are computationally expensive, whereas you really need to go beyond or far below one solar mass limit in order to be able to say something very concrete about this distribution. So is there any plans for, machine learning aided searches which can go, which can help you go much below the one solar mass limit that you showed? That is one. And the second question is, we have seen several recent works where, people have tried to calculate actually measure the dephasing coming from dark matter spike models due to the dynamical friction in addition to the gravitational waves that are carrying away the energy from the system. So even if you measure it, not necessarily in ground-based detectors, but maybe space-based detectors, can you say something about the nature of the dark matter from such measurements? Thank you.
Great. Yeah. So the first question about the sort of the search process. I'm not aware of any efforts that aren't sort of template based. I think you could do a similar version of sort of the unmodeled searches down there below a solar mass. I think, and this is really probably a question for somebody who's a LIGO expert, but my impression is that the sensitivity is not yet so good that you get a lot of bang for your buck by doing things like that. And the searches for the subsolar events also they do well by actually, shrinking slightly the frequency range that they look at, and you don't lose so much sensitivity to possible signals. But I think you're right that if we get better detectors, maybe it's worth some other approaches in this parameter space. So that'll be interesting to see how that evolves. In terms of the dark matter spike, this is not something that I've worked on myself. So, I don't know details of these models. It's probably possible if you really could study differences in details of the spike. Those differences, of course, would be there depending on sort of particle interactions of the dark matter. So it may be that there's some detail buried in there. Whether that's a better route, or a more straightforward route to find that particle physics versus looking at things like halo profiles and sort of substructure inside of halos, which you might get good statistics with something like Gaia. I don't know which of those would be more successful. That'd be good to pose to someone who works in detail on those spike models. Thank you.
Thanks a lot. Thank you.
Thank you very much, Sarah. Now, Professor P.C. Deshmukh, sir, he's from IIT Tirupati and mentoring the quantum science in IAPT, India. Sir.
Professor Sarah, thank you very much for an awesome talk. I have a layman's question, if you do not mind. Very much a layman question. Is the time reversal symmetry of any relevance in speculating on the possibility of having a universe before the Big Bang?
So I guess good, thanks. So usually I think of the Big Bang as the reheating moment when all of the energy was transferred into creating the hot universe. And before that, we think perhaps there was inflation. So I guess you mean if we think of some singularity moment as the start of the universe, could we go beyond that, or is that the nature of the question?
Well, I really don't know. Maybe that's the reason I'm asking.
Okay. Okay. Yeah. I think there are lots of ways that I think a person could approach this question. I think one interesting thing about the universe, of course, which maybe has to do, with time reversal symmetry, is why is there an arrow of time at all in the universe? And if you think about the scenario of inflation and Big Bang, why does the universe start in a low entropy state, and how is that, sort of at a macroscopic level? At a microscopic level, we sort of know about time reversal symmetry and how we can still have the second law, and how we can have systems that thermalize, even quantum, like, subsystems of quantum systems can thermalize. But at the level of the universe, we don't know yet. So I think it's an interesting question in the sense of maybe not what happened before, but just what are the fundamental laws, and how do we make sense of the starting point of the universe, and how do we match that with the symmetries that we know exist in particle physics now.
Thank you very much. It's really very fascinating. The story that you're building will bring many answers. Thank you.
Thank you.
Thank you, Sarah. One last question. Yeah, please. No. It is also from a student. Yeah.
Good morning, ma'am. Good morning, ma'am. My name is Gambhir Singh. Ma'am, first you share the picture of the universe which is here. You shared that this is the bright part of universe which we don't know what is this. Can we expect that this is the origination of the universe, which is the reaction which is called Big Bang. At today's time, it is still going on there, and which is still going on there at this place at the bright point. First, you share in the which is still going there, and there are so many particles. Expect dark matter are also coming from this, and the black holes also contains black matter and another particles like black matters. Can this is happening, or this is possible?
So you're right that very early, that sort of bright bang again is what I think of as when energy density that probably had the universe expanding early on gets dumped into all the particles that we see, and it's bright because there's that big energy transfer. And you're right that energy transfer would happen not just to the standard model particles that we see, but also into these dark matter particles. They need to be produced at some point, and so some of that energy must be dumped in to produce those dark matter particles as well. And when people have so we don't know the full story. We just know that has to be true somehow, but we don't have the concrete equations that we're sure are right for exactly how that process happens. Lots of models, but no certainty. And I think you were also asking, when people had these models of black holes produced very early on, then yes, all of the matter that was produced at that time collapses into the black holes, and they're made up of all kinds of matter. Even at later times, of course, a standard model black hole can accrete some dark matter, especially if that dark matter can be cold. And a black hole that formed from mostly dark matter collapsing would accrete some standard model matter as well. So most black holes would actually be a mix of dark matter and standard model matter. Not that we can tell the difference from the outside. But.
Thank you, ma'am. Thank you very much. So I think you have justified the question which you have asked to me on the first email which I have sent to you, your role. You answered the questions of first year students up to the professors like P.C. Deshmukh Sahab, who has authored renowned books on the topic of quantum mechanics. Thank you very much for being with us.
Thank you.
Thank you very much. So next I will call upon Professor P.C. Deshmukh Sahab, who is mentoring centers at IIT Tirupati and ISR. And he has mentored very many institutions like IIT Madras. He has been with IIT Madras for many years now. He is with RV University also and mentoring 2-3 centers there. He will be speaking about unriddling the general theory of relativity. So we'll pause for 5 minutes for setting up the connections with you also. He is with us. Offline he will be speaking. Thank you very much. So before I go online again, ये जो भीड़ आई है ये यही के लिए है क्या? Sir, for this segment, ये कोई बीबी भी कौन भी यहाँ कैसे आ गया? मुझे लग रहा है तो आपको बोला था ये। सर मुझे बोला गया था कि यहाँ सर नहीं कहाँ? नहीं मुझे लगता है वहाँ के लिए बुलाया होगा। इंजीनियरिंग ब्लॉक मेन कैंपस प्लीज आप लोग जो भी अभी आए ना प्लीज फ्रॉम स्क्रीन को, जैसे आप लोगों की टाइमलाइन में सब चीजें मैं टाइमर को स्टार्ट करूंगा।
Us to light in terms of use our experience, and that is where we are not helped very much when we learn quantum theory or relativity. So it all has to do with gravity, and it goes back to Copernicus, Galileo, Newton, Kepler, and so on. But even before them, there are references to literature in Bhaskaracharya II's shlokas, in which he talks about things falling to earth due to Earth's gravity. Now, we understand gravity in terms of these experiments, which are really very fascinating. And Galileo demonstrated that, irrespective of the mass of an object, if you throw a very big stone and a feather from the top, they would fall actually together. But the problem is that we don't ever see it. If you go if you go to a forest, you don't see a fruit and a leaf of the tree falling together. Okay, it really doesn't happen. But such experiments can actually be done. No matter what the masses, the two objects fall together, even a feather and a stone. And I would like to show you this video, which is available on the YouTube, but it's a very fascinating video. I enjoyed it. I see it many times, even if I've seen it earlier. So let me show you this video. This is an experiment in which 30 tons of air were pumped out of the laboratory, and a feather. So here, please watch it.
6, 5, 4, cameras on, 2, 1, release.
So here you have a feather and a ball, which has been released, a video recorded by Professor Brian Cox. It's very fascinating. You actually see the feather and the ball falling absolutely together. And this could be done after 30 tons of air have been removed, because otherwise it is the buoyancy and other things which prevents the feather from falling together. It's a very beautiful experiment, very fascinating. I've seen it a number of times, but every time I see it, I really enjoy it. And then we understand the Kepler-Newton two-body problem. We are familiar with this. Let me quickly point out the success of the Kepler-Newton model, because it tells you how planets revolve around the sun. But then it does more. In 1846, calculations based on the Kepler-Newton model predicted the existence of Neptune, and when you train your telescopes in that direction, you actually find it. So that is how Neptune was discovered. It's a remarkable success of the Kepler-Newton model. And then I will like to point out the work of astronomer Verrier in France in the 19th century. He made many fascinating observations in astronomy. And one of the things that he observed in 1859 was the precession of Mercury. So we know that all orbits are in ellipses. So if you imagine this shape to be that of an ellipse, then the size of the ellipse is determined by conservation of energy. And the fact that the ellipse is fixed in a plane, okay, the motion of the planet doesn't come out of the plane, is because of conservation of angular momentum. So there are two conservation laws operating over here: conservation of energy and conservation of angular momentum. But you can ask, why does the ellipse not precess like this? You see the picture? So the ellipse not only has a fixed size, not only is the fact that it stays in the plane, it does not precess, it stays fixed in this, which means that there is an additional conserved quantity, not just the energy and the angular momentum, but there is a third quantity which is conserved. And we can ask, what is this third quantity which is conserved? Even Pluto was discovered using the Kepler Newton law. Uh, Pluton, however, has lost its status as a planet because of certain limitations. I will not get into that to save time, but Pluto has even moons, but then it has not cleared the neighborhood of surrounding, so it does not fulfill all the criteria of a planet. So Pluto lost its status of a planet in 2006. But there are, we talked about the success of the Kepler Newton model, but then we also ask if there are any problems with this. And there are problems. And there are different kinds of problems which I will talk about. You can ask what would happen if the interaction between the sun and the earth is switched off. Okay? If it is suddenly switched off, in a model like this, you would expect the circling object to be swung off along a tangent. That is your expectation. But that doesn't mesh up with the fact that that light itself takes a finite amount of time to reach the Earth. As a matter of fact, it takes about 500 seconds, more than 8 minutes to get here. So there is some sort of a discrepancy over here as to how do you explain that there ought to be a delay, whereas you expect the object to be flung off immediately. The second question is what I mentioned about Leverrier's discovery in 1859, that the orbit of Mercury actually stays, it is not actually fixed, but it precesses. And you cannot explain it in terms of conservation of energy and conservation of angular momentum. So there has to be something else. The precision is very small. It is through about 1.6 degrees in 100 years. So it's very tiny precision, but it is very much there. And if you expect it to be not precessing, you should ask, what is it that is conserved in the two-body problem? And that can be understood very easily, because if you write the equation of motion for a two-body problem, the force is the inverse square law, so r over r cube. There is a magnitude in the numerator, so it is 1r square force. So this is the inverse square law that I have plugged in over here in this equation of motion. And if you take the cross product of this equation with the angular momentum, you get this relation, which is very simple vector algebra. You have a vector triple product coming up over here. You know the back-cab rule, so work it out. And what comes out of this is the fact that the time derivative of the sum of these two vectors goes to 0, which means that the vector inside the bracket must be a constant. Okay, the derivative goes to 0, so the vector itself is a constant, and this is known as the Laplace-Runge-Lenz vector. If you study this vector in further details, it turns out you can show it using very simple vector algebra that it is along the major axis of the ellipse, and what essentially happens is that the vector along the major axis is a constant. Therefore, the major axis itself is fixed and it does not precess. So this is what you expect from the Kepler-Newton model. It comes straight out of the Kepler-Newton model. It is known after Laplace and Runge. This Lenz is a different lens from the Lenz who appears in the Faraday-Lenz law. He studied the similar problem in the hydrogen atom, which is also governed by the 1 over r potential. So the Mercury perihelion advances through a very small angle. The ellipse is not fixed, as you can see in this picture. The ellipse major axis is precessing. it does not repeat itself, but the major axis is precessing. It remains fixed in the plane because of conservation of angular momentum, but it keeps precessing. And you can account for this precision due to various factors. Some of it is attributed to the fact to the precision of the equinoxes, some to the gravitational tugs due to other planets, some to the oblateness of the sun. But when you add up all of these corrections, you are still left with a tiny correction. Okay, you are still left with a tiny correction. The difference between this 5599.7 seconds of an arc and what you account for from the three reasons is 43 seconds of an arc. Okay, it is just zero point zero 0.01 degree in 100 years. So it's a very tiny correction. And you might dismiss it as saying that, okay, who cares? Now, this is very important. This reason is because of the fact that the Kepler-Newton law is not fully correct. It is a great approximation to the correct laws, but it is not fully correct. And what must correct it is Einstein's equation. That is where general relativity steps in. Okay, the Kepler-Newton law is not correct. It has to be corrected. And Einstein's general relativity, of course, has a background which the general relativity for 2016, 2015, 2016, 2015 actually. This was 10 years after the special theory of relativity. So we go back to the special theory of relativity in which we recognize that what is an invariant is not just the distance between 2 points, but distance between two events in the space-time continuum. So space-time is a continuum. So there is a fourth dimension that we must take into account. But this is not the same kind of dimension that we talk about when you go from a line, straight line being one dimension, a plane being in 2 dimensions, and a sphere being in 3 dimensions. So there is a difference. And if you understand this difference, you will begin to unriddle the general relativity. So what happens in space-time is that you have the distance between 2 events which are specified not just by x, y, z, but also by t. So you need 4 coordinates, and they transform when seen by another observer in a different inertial frame to x prime, y prime, z prime, t prime. These will be the coordinates measured by a different observer. This is where relativity is beginning to step in. And what happens is that the difference between these events must be an invariant, because if I look at the distance between 2 points, okay, let me use my left hand because normally we use a right-handed coordinate system. So I want to show a right-handed coordinate system by these 3 fingers. Are you all seeing it? And the distance between these 2 points must be the same no matter how I orient my coordinate system. Irrespective of the orientation, these are different mudras, if you might think. Okay? The distance between these 2 points must be exactly the same. And if you want to have the distance between 2 events between these 2 inertial frames of references, then the x, y, z, t and x prime, y prime, z prime, t prime must be related to each other according to a certain law, which is the Lorentz transformations. So you actually have, everything really goes back to Einstein. I mean, this is a great guy. Symmetry, of course, all right? And symmetry is at the bottom of many fundamental laws in physics. This goes back to Einstein. Quantum theory goes back to Einstein because Planck argued with his own argument after proposing it. And it was only after 1905 interpretation of the photoelectric effect by Einstein that Planck himself recognized the deeper truth of E equal to h nu. And I would say that the completeness to this understanding comes after the work of Satyendranath Bose. So the Indian Association of Physics Teachers is recommending that H should be called not just as a Planck's constant, but as a Planck-Einstein-Bose constant, the PEB constant, because you need an understanding not just from Planck, but also from Einstein and Bose. But then let's continue with the story of relativity, which is here. And I talked about, measuring the distance between 2 points and how to express it in some sort of an invariant manner, regardless of how you rotate the coordinate system. So when you do that, you look at the distance between these 2 points and you essentially use the Pythagoras theorem. Okay? The distance ds square is dx square plus dy square, and you take the square root of that. That is your notion of distance. And this is the metric that measures the distance between 2 points. You can extend this idea to 3 dimensions. Okay? And essentially what you're doing is taking the dot product of this difference vector with itself and then take the square root. Is that simple enough? This is just high school algebra. Now, this is a metric space. This is how you measure the invariance. And essentially what you see is this relationship over here, that the ds square, it is quadratic in these distance intervals, so don't pay too much attention to the notation. I'm not getting into tensors. That's not my intention. But I just want to show that it is a measure of this. You sum the quadratic term over here weighted by a certain factor. In Cartesian geometry, this G factor will be only unity, because it is just dx square plus dy square plus dz square, and you take the square root. That's what you're doing. So if you, however, write the distances, if you use the spherical polar coordinates, then the distance square in spherical polar coordinates, which are r theta phi, okay, that would be dr square plus r square d theta square plus r square sine square theta d phi square. And now you can see that this G matrix that you're talking about is not just 1, 1, 1, but it has got these weight factors which you must take into consideration. So this is the property in Euclidean geometry. But what you need for the special theory of relativity is not a diagonal 1, 1, 1, but the sign of these 3 elements is different. So in Cartesian, it is 1, minus 1, minus 1, minus 1, and in spherical polar coordinates, it would be this. Now, this is what makes the space. Now, this space is a 4-dimensional space-time continuum. And this is not Euclidean because of the difference in sign over here. Okay, so the signature of the G matrix is different. It is 1, minus 1, minus 1, minus 1. You can also take it as minus 1 and then attach a plus sign to the remaining 3. That's a matter of convention, and it's a choice that you can make. Different authors make different choices. But essentially, this is the space-time continuum, and this is, if you write it in the spherical polar coordinates, it would be this. But this space-time continuum is what is called as a flat space-time continuum. Now, if there is a further variation from this, so look at this. Instead of this 1 and minus 1, you have 2 other functions, u and minus v. Okay, these are different now. The form is the same. The general idea of distance between 2 events is the same. It is the same type of idea, but the details are different, and the devil is always in the details. Okay? Now, there is no way you can get an intuitive understanding of this, because this goes beyond our experience. It is essentially counterintuitive, and you have to get into the domain of. You have a question?
Yes, sir. I will choosing x1 is equal to ct, but x1 is equal to x, x2 is equal to y, and x3 is equal to z.
No, you're bringing in the time dimension, but then you write everything in spatial dimensions. So the speed of light multiplies it
The
to.
object here our space that the particle moving lag.
No, no, you cannot add or subtract quantities having different dimensions. So this takes care of the dimensions using a universal constant, which is the speed of light. But we can discuss it in further details later. So you have this non-Euclidean space to begin with in the special theory of relativity, which is flat. But now you have a curved space-time continuum in which you do not have 1 and minus 1 in the first two rows, but u and minus v, and there are different solutions for u and v that one can construct. What I have written over here is one of the solutions, which is the very common one, the Schwarzschild solution to Einstein's field equations. And it has this form. And so essentially, going beyond the special theory of relativity, if you apply the principle of equivalence, you ask that acceleration in free space, if it is at g meters per second, then it should be very similar to what happens on Earth when an object falls at g meters per second per second. Okay, so this is the principle of equivalence that you expect, and what it essentially means. So this is a picture which depicts that if you have an object falling under gravity, and if you see the same thing in a rocket which is accelerating at g meters per second, you expect an equivalence between what you would observe. And then you can ask, would it not happen to light as well? If you're shining light, if you have got a source of laser or light source or a torch in any way, what would happen to this light? Then if you're seeing it in a rocket, then would it not actually bend? And if light were to bend, then would it not bend under gravity? And this is the question that is very natural to ask, and this is the first experimental demonstration of the general theory of relativity, which was in 1919, just within a few years after Einstein's theory. Experiments done by Eddington, extremely fascinating experiments done during the solar eclipse, so that you could see the light coming from behind the sun, and you needed a dark atmosphere. You could get it only during a solar eclipse. Very beautiful experiment which demonstrated the correctness of the general theory of relativity. So time is very elusive, and you would expect the general relativity consequences to be measurable in all phenomena. And what it essentially means is that your head ages faster than your feet due to gravitational time dilation. Okay, so these are very interesting consequences. You can actually measure this. People make atomic clocks, and you can observe time dilation in these atomic clocks. If you just raise the atomic clock through 2 centimeters, how much is the distance? Nothing. And within that, you can see the consequences of time dilation. So the technology has advanced very much. LIGO is its celebration, detection of gravitational waves on the 14th of September. A great day to celebrate. So congratulations to the organizers, Yogesh Chandraji, for a wonderful series of seminars that you have over here. I think this is my last slide, or maybe one more here. Yes, I would like to tell you about calculations done by my student, Kaushal. He did these calculations as a first year student. I mentioned it in my talk yesterday as well. So he simulated the effect of general relativity in the precession of Mercury orbit. And it is not just the Mercury orbit which will precess, but other planets also would, because they are also governed by the same physics, essentially. So the Earth precesses, Mercury precesses, and Venus also does. Every planet does. The correct value is, I told you about the 43 arc second correction. So this the more accurate value to first decimal is closer to 42.9. Um, what Kaushal calculated was 43.3. For Earth, he calculated 3.7, whereas the literature value is 3.8. So he got fairly accurate results. It's a pedagogical simulation exercise that he carried out. It is published in Resonance over here. You can get the details. I will stop here. If there are any questions, I will make an attempt to answer. If they're easy, if they are not easy, I will direct them to other experts who are here. Thank you very much.
So the session is open for questions. Any question from the honorable guests? If nothing is there, then I will request. Thank you very much, sir. But before, sir, you move to your seat, I would request you to. एक मिनट सर, एक मिनट। Sir, are you here and are we visible and audible to you?
About 40 years or more effort to detect this. That's because even the first source, which was one of the strongest sources, in fact, involved detecting displacement of 10 to a minus 18 meters between two mirrors placed 4 kilometers away. So just to give you a perspective, and you'll hear a lot about this in later talks, and I'm sure you get more to the details of this. But I just wanted to tell you how amazing capability you have to develop. So you had the size of the hydrogen nucleus, which is 10 to minus 15, and this is like 3 orders of magnitude lower than that. Okay, so how do you detect such things? Is the big question, and I'm not going to go over this idea of how you use laser interferometers to detect this, but I just want to point out in the context of this quest and conquest cycle that you look at boundaries of measurement. So normally in daily experience, you would probably know of um, megameters. Say megameters would be international travel you do across countries, and millimeters, right? This is what we worry about. Maybe if you're a science student in physics and technology, you go to microns. If you are doing further, deeper research, then maybe nano, and then that's when you get to atomic scales. And we know that we have also ability to probe on nuclear scales. But now you have to move forward. As I said, you have to cross the boundaries of what was possible in measurements, and you have to be able to do measurements of things at the level of atometers, and which is the capability that came and allowed LIGO to start doing these detections. As Professor Gonzalez told you, Gabriel Gonzalez, that there have been 90 detections, and there are papers out of on them, and then there are many things in the pipeline from the current round. So it wasn't surprising that the Nobel Prize was awarded almost immediately after the discovery, and also there was a breakthrough prize given to the entire collaboration. But I wanted to point out again in this whole matter of what it takes to have this very vibrant quest and conquest thing is for people to identify a quest. So, for example, if I look at the 3 Nobel laureates, Kip Thorne was the faces to realize the importance of gravitational waves in terms of understanding fundamental science and its possibilities of doing gravitational wave astronomy. So he would be kind of representation of that group of people who really did that uh, apart. But then when you have to do that, you have to figure out how do you do it. How do you measure 10 to the minus 18 displacement? And Rainer was the one who realized that if you could scale up your laser interferometers from what they were to the size of 4 kilometers or more, so in 70s, the very impression paper, working out all the details of how this could be possible with technology and what would be required to make it happen. So these two are understood things in the quest and conquest part. Uh, then Professor Barry Barish, who is a particle physicist of very high standing. But why is he in this trio? Because of a reason that is quite important in the current day science. He was the person who kept a group of 1,000 plus people, focused on a goal of making a gravitational wave detector with sufficient sensitivity to get to the point where you are detecting sources. This is no ordinary feat, and this ability is also an amazing part of science that is becoming, important and should be recognized. That they are all evacuated and and such things. The other pictures, and then the inside of it there are lasers of amazing capability, mirrors, and when the mirrors are set up, you can see people are guarded almost like operation theater kind of thing, and work in very confined spaces to set this up. So there are remarkable, you know, technical abilities, patience, all kinds of capabilities which are at the extreme that are required to make such a thing work. Here are two of the mirrors. These are amazing objects, and again, I'm sure we will give you more specs. But just to wow the students, I would say that this is a 40-kilogram mirror held up by glass fibers. So these are fibers of zero point 0.4 mm, which are welded to the glass, and this is all done to keep this system very pure in terms of vibrations and capabilities. And they're very narrow resonance lines for them. And this is the last picture in the bottom right is are these mirrors hanging. Every mirror there's a counter mirror, counterweight, things like that. So it's a very complex system that is built into a chamber which is 2.5 meters or something. It's not a lot of room for you know working, but these are things that we are getting into as we talk about LIGO India. So LIGO India was proposed in 2011, and when we proposed it, I keep emphasizing this point that we did not anywhere in our proposal talk about being part of the detection with LIGO. Even at that point, it was clear that it's a big project, it will take time, but LIGO India would be critical to enable gravitational wave astronomy. Okay, so this was kind of accepted by the government in principle in 2016. We were given project funds, pre-project funds to do a lot of the legwork, like at the site and all. And then last year in 23 April, we got the full budget approval. We have for now, for example, the site acquired and sort of construction has started. And there are four lead institutes, and there are representatives from each of them. This meeting, so you'll hear from each of them. But when we proposed it, what was really the telling argument? So was say the first detection, which was historic, but for doing astronomy, that wasn't very useful because you couldn't really tell where the detection happened on the sky. So the uncertainty is this gray band that we see, banana-shaped band. So it is like 2,500 full moons, or you can even in terms of if you know the Saptarishi, the Big Dipper constellation, there will be seven such Big Dippers which can be fitted in this area. But had LIGO India been in operation at that time at the same sensitivity, we could point out that the uncertainty in where this event happened would have been 100 times smaller. That little thing that you see in a size hill at the center. So we knew that it would make a big difference, and it still stands that we will make a big difference. And there are arguments to say that the ability to follow up a neutron star merger uh, with LIGO India in operation in 2030 would go up by at least a factor of 20. Okay, so that's really going to make a big difference. So it's really happening that what we thought of is kind of how things are unraveling. So as we set up to build a detector, commissioned and operated in India by these institutes mentioned, and it will indeed be expected to launch gravitational astronomy in the sense that it will become more routine to have neutron star mergers which are being followed up by the astronomical community. I probably should have shown a slide, but I'm sure someone will mention that. The only neutron star merger that has been followed up was followed up by 70 observatories across the world for over a year in different frequency bands, and a lot of science came out. The number of papers that have come out of that is unbelievable. The first paper had some 3,600 authors. You can, it's sort of a shake, it shook up astronomy community like never before. And you want more such events to happen to really see the fruits of gravitational wave destroy. And for India, getting into this brings in high-end frontier technology with transformation capabilities, high-tech capabilities in many areas. So I've just listed a few, and I'm sure others will point out what I missed. Photonics, lasers, control systems, vacuum. The important point one should, I always have been emphasizing from the beginning, is yes, India, locating it in India does have a geographical advantage of being quite distant from US detectors, almost as far as you can see. But there are many countries which are very far from US geographically. The question is what's special about India, and I always felt that the demographic advantage we have is going to, be critical. And that sort of, in my opinion, has really panned out well. I mean, I told you about the large presence of students from India in the global gravitational community, and students who have been, uh, getting into the field after knowing that India is planning to build a detector, and that's quite heartening. And so this demographic advantage, I think, will allow us to really flourish in this very globally cooperative field. And then, of course, this is enhancing the research opportunities for students of science and technology, as well as many other fields. But in India, I think the really uh, distinctive thing about this mega science adventure in India is that it's going to be on Indian soil. So I'm sure some of the students sitting there, or many of the faculty also soon, few years time, will be able to go to the site and see this library getting ready. It touches a lot of disciplines, so it is, although it was led the science, science key science stakeholder, Ayuka is an astronomy institute, but it's supposed to touch everything, like fundamental physics, astronomy, as well as many, many technologies. And this is something that is a small ecosystem of science and technology that needs to be set up and needs to work very well under a common umbrella to be able to realize the potential of having LIGO India in India. So where is LIGO India coming up? So that itself was a big challenge because it's a fairly large piece of land, about 450 acres. It's probably the size of university campus like Pune University or many of the IITs and IISs, but in a L shape. So it was also had to be seismically quiet place, and also we looked at about 40 leads that we got, and some of them which looked promising. We even carried out seismic studies for a couple of weeks, and then we finalized on this site called Onda. It's in eastern Maharashtra, and it actually sits plonked in the middle of the Deccan Plateau. And that later in halfway through the site search, I learned that geophysicists knew that Deccan Plateau is actually one of the quieter places on Earth in terms of seismic noise. And then a lot of has been happening. These pictures are not complete, but they start from the early times when we were even checking out how easy it would be to excavate. We had markers and then geo, geotechnical studies. So there were these trucks at various places simultaneously drilling into the ground to map out the substructure because you have to build on this land. And then this is from the 3D rendering, and you can see that the building which is marked out in a circle is already there physically. This is now currently the Library India site office, but will later be a maintenance and estate office. And then we have all-weather station, fences in various places to mark out the area. So a lot of development are happening, and the last the construction is expected to start soon. So how challenging is going to be the construction? So you look at the civil infrastructure of 4 kilometers of place that has to be set up is huge, and with that operation. So all that and the big labs, central and the air station. But the laser has to travel through vacuum. So there has to be a continuous vacuum system of a mammoth size, like it stretches 4 kilometers in either sides, and then there is large chambers, and the vacuum tube itself is fairly big, 1.2 meters. So if you calculate the volume enclosed within this vacuum structure, it's about 10 million liters. So it's amongst the biggest, largest ultra high vacuum facilities in the world. It actually is larger than the LHC. So these gravitational wave, 4 kilometer gravitational wave detectors are, arguably the biggest ultra high vacuum systems to be built. So the point which I think a lot of people have appreciated is when India has to build them. Imagine the Indian industry which really puts this together, where it would stand in the global scenario in terms of its capability when make this happen and make it reality. So over the time period between 2016 and the final budget approval for the full project, we have money to test our ability to build in India the elements of this vacuum infrastructure. And this has been largely led by Institute of Plasma Research, and Sudeep is there, that's is there. So there were three elements of this, two types of chambers. They're called ham and PAC chambers, and then a cryo pump with a piece of the beam tube. These were all prototyped in Indian industries. So here is a picture of the two chamber of one piece of each of the full chambers, but of full scale prototypes, which were fabricated in Bangalore and tested to make sure that they have they have the whole vacuum to the levels that required. And then we have further checked other aspects, like we could transport them from Bangalore to Indore, Arakat, where they are currently sitting. And that is one part done. And then this is a piece of the beam tube coming up in a factory in Bombay. And this was an older picture, so it's been shipped finally, and it's sitting in Institute for Plasma Research. wrapped with quite fancy brackets and things like that. And then there's this cryo pump, which this picture doesn't have a bigger part of it, but it's a fairly, uh, you know, commendable thing that this could be built by an Indian industry. The cryo pump was built in Ahmedabad, and so we are fairly confident that all these elements have come together, and that sort of told us that the prototype is staged to now final full-scale construction. All the homework has been done, and we have checked them out. Similarly, the vacuum infrastructure, I showed you some pictures. So there are very complex optics laid out there, and we need to, have expertise built up in that. So, on setting up this optics. So there's a national testing and training facility at RRCAT, which is a very big lab structure. You can see the building and the hall in which, this is the empty hall. It's probably not as empty now, where a 10-meter prototype is being set up and many other activities will happen. And this is where I think we will be starting to reap the benefits of Digital Lab India. For the 10-meter prototype, all the amazing optics that goes into LIGO are being actually fabricated at RRCAT, Ramana Center for Advanced Technology. And this is going to be a stepping stone for Indian capabilities in these areas of ultra-high optics and many aspects that are required. So, for example, these are early pictures of the 10-meter prototype chambers and tubes, and they have been all put together by now. And this is how things will be going forward. I didn't touch upon other aspects like the computing centers which have come up, other outreach programs and training programs which are actively going on. So uh, this is one quest and conquest thing, but this was a global quest. I mean, it happened led by US to do this detection and conquest of technology, and we are kind of in India, trying to set up that technology so that you have a standing base stand on in terms of this capability to address the requirements of frontier science. I wanted to spend a few minutes pointing out that there are further quests, and if you were to listen to the Nobel Prize lectures of Kip Thorne and Revise, you'd find that they both mention that the next big scientific milestone, according to them, would be the detection of gravitational waves again, but from the beginning of the universe. So gravitational waves, just like electromagnetism, come in various wavelengths, corresponding frequencies. So we have detected them at this shortest wavelengths or the highest frequencies where we think gravitational waves will be generated astrophysically. And then, but you can have things which are exotic. So exotic in the sense that they're amazing. To see gravitational waves of cosmological scale right from the beginning of the universe. So if you heard Sarah's talk a little while back, she kept talking about this beginning where all the radiation energy was created from the vacuum energy of the inflation, and that is the beginning of the universe. And from that epoch, one expects gravitational waves to be generated, and the way you see them is very similar to the idea of a laser detector. So our universe is such that if you can look as far as 43 billion light years before every observer in the universe will hit a plasma screen sitting at 43 billion light years, and that's growing at 3000 Kelvin. But because of the expanding universe, that radiation when it comes to us is 3 Kelvin R, which we see as the cosmological background. And since the 90s, we have been seeing structures on this plasma surface and mapping it out with more and more sensitivity and resolution. Okay, so that's the field of cosmological background. And one promise that it still has to heal is to see the signature of gravitational waves on it. And why do we expect? So, since there are fluctuations, and these fluctuations, in fact, are the same fluctuations that gave rise to all the galaxies and everything that we see. So, we see the fluctuation in the radiation and we see them in the distribution of matter. And our belief is there's a mechanism which generates this fluctuation in the early universe, right at the beginning of the universe. And that not only creates the density perturbations that can give rise to galaxies and all, it has to be accompanied by gravitational waves. And the question is, can we see them? And we can indeed see them because what really happens with the gravitational waves on this scale is all of you will hear probably going forward that the way you detect gravitational waves in dipole is through a microsym interferometer. So there are end mirrors which one arm comes becomes shorter, another one it expands, and then that thing reverses. So the arm gets contracted, expands, and the other one contracts. And this is the thing that you detect as a phase shift in the interference, and that something very similar you can think of in this cosmic gravitational wave detector. So what really happens is if you have a gravitational wave which is of the size of this plasma screen sphere, right, this sphere that is surrounding us, so that is about 43 billion light years in radius. So imagine a wave, gravitational waves of similar wavelength. What it would do is gravitational wave shear matter, right? So what it will do to the plasma, spherical plasma, and it's obviously very exaggerated view, but at some 10 parts in a billion, this will create a parting of the sphere, and that changes the signal that you see in the microwave background sky, the cosmic microwave background. So the cosmic microwave background has hotter and colder regions, but also there's a linear polarization pattern, and gravitational waves are revealed by a particularly strange pattern which has a word, which has a handedness, and that is a telltale signature of primordial gravitational waves that we see. It could be at the level of as low as 100 nanokelvins or 10 nanokelvins, or between 10 and 100 nanokelvins. We should see something like that. But what we need, in the opinion of many of us, is that you need to send out another. We have had three the cosmic microwave background space missions. So the Cosmic Background Explorer, and the Wilkinson Microwave Anisotropy Probe, and the Planck mission. Now the community does realize that we need a near ultimate uh, experiment or probe that needs to be sent out, which will map out all the information that remains to be mapped out in the microwave background sky, particularly in that polarization. And if it sees gravitational waves, these will be an amazing thing because these are gravitational waves right from the beginning of the universe. It gives you an idea of how the universe began. But also in terms of fundamental sciences, this is going to be a kind of a validation of the approaches to quantum gravity. We believe, although we don't have a theory of quantum gravity, we believe that quantum science on a curved surface, curved universe like space-time, we know how to handle it. And these are all this gravitational wave background and the density perturbations which gave rise to all the structural waves are predictions from that. And as usual, when you have a very high, tough scientific quest and which requires immense capability building, if you can do it, it will also have many others, things that will just fall out of this, high sensitive measurements that we do in terms of how well you know cosmology, dark matter, baryons, neutrinos, all kinds of things like that. So in India, very akin to a proposal that we put out for LIGO India in April 2018, we put to ISRO a proposal from an Indian cosmological community to consider funding a project where this fourth generation CMB mission will be, uh, you know, it will be an international partnership, but led by India. So it involves a telescope or a spacecraft, which is the dimensions are given about 4 meters in radius and 4 meters high, 2 tons, and these are all well suited to be launched on India's GSLV Mark III, and it has to be launched to away from the sun towards something called the second Lagrange point, which is quasi-stable place where many of the things which want to look away into the distant universe, like the James Webb Telescope, the Plant satellite, many of them are Euclid, all of them as they have on there and mapped. So we want to do that. This itself will be a first for ISRO because we have done a lot of great things from ISRO. We have gone to the moon, Mars, and we have stationed a probe looking at the sun in the Lagrange point, first Lagrange point, which is the equivalent of this, but towards the sun, Earth along the sun axis, towards the sun. So this would be new, and it would also again require us to enhance our capabilities on various things that need to be that are important for a spacecraft and a telescope. In terms of technology, the breakthrough that was required for this are detectors which are more sensitive and in this terahertz band. And I just wanted to point out, just like the picture I showed you about boundaries of measurement of displacement, here it's a boundary of measurement of power. How small a power can you talk about? Again, daily experience, we talk about megawatt plants generating power, and then we talk about milliwatts in various devices that we have in our hands nowadays. Then, in terms of how small a power have we used, so FM reception itself, takes you to about nanowatts of power, nanowatts or tenths of a nanowatt power. So that is quite a sensitive detector in that sense, the FM radio that we build. Cell phones, amazingly, are 10 to a minus 13, 10 to a minus 12 watts. The picowatts are less. Again, this points to the fact that we worry about cell phone radiation, but actually, a cell phone requires very little uh, power from the signal to be working the way it does. Okay, so but what are these receivers? What are these detectors? So these are all detectors which were built generation after generation for scientific purpose. So, for example, many of us are talking about 5G capabilities. Now, these were in lab in the late 90s. They were laboratory objects of science for astronomy and other applications where you want to detect a little bit of power and even other searches and applications. And that has improved now to the extent that we can have detectors which are sensitive at atowatts of power. And that's also not enough for the goal that we are seeking. We have to line up many such, thousands of such detectors on a focal plane of a telescope. And such things are happening. In South Pole, there are telescopes which have these detectors in their focal plane and who are or would be also in the coming years looking for all this excess, this power from the microwave background sky. And also for ISRO, what would be interesting is we have in ISRO never launched a cryogenic satellite. This would be a satellite where you can see one end of it is at 380 Kelvin, but the detector sits on a plane inside this 42 Kelvin enclosure. This is all passively cooled, and then this has an intricate cooling system, and it's refrigerated to a Kelvin temperature, zero point 0.1 Kelvin temperature, 100 microkelvin, millikelvin temperature. Okay, so these are all new things, new conquests you have to have, you know, at the national level or even global level to make this happen. And I'll stop here with this possible story that I may be, you know, or someone else here, young people, you know, would be narrating to you maybe 10 years down the line of a vision of such capability and being launched to look for, you know, gravitational waves from the cosmic origin. Okay, I'll stop here and thank the organizers again for this opportunity to talk to students and other colleagues who have joined. Thank you very much.
Thank you very much, sir, for sharing this with us, the frontiers on which Indian science is working. Thank you very much. The session is open for questions. Any questions, if there are any? So if not much questions are there, then we have the next speaker, Dr. Manjari. She is again from the Institute of Mathematical Sciences, Chennai. So, as sir said, Swarajit sir, said that we are meeting online. We are near we are working. PC Deshmukh sir is at Bangalore, but you are listening in from Jaipur. Similarly, Manjari ji will be speaking from Jaipur on the topic hunting low frequency gravitational waves through pulsar timing arrays, the role of Indian pulsar timing array. I welcome Dr. Dr. Manjari.
to detect the electromagnetic signature, but those instruments are already there to do lots of other science. And we observe the frequencies, gravitational waves whose frequency lies in the range 10 to the power minus 9 to 10 to the power minus 4 Hertz. And there can be many sources, like mergers of supermassive black holes, that is astrophysical origin, and also that background is the merger of single binary and merger of and the background of many binaries. And there can be cosmological origin also. It's not as early as the Big Bang era, but slightly after that, what we call inflation era, and then phase transition is how we form one type of particle to another type of particle. Then there are many exotic models like cosmic strings, domain wall, signature of dark matter also. So in my nearby institute, there is another institute, IIT Madras. There is one cosmologist. He has so many say exotic theories, and many cosmologists are doing exotic theories of our dust year detection. So, but as an astrophysicist, I am mostly interested in the astrophysical origin, and our data actually last year supports that what we have seen so far mostly dominated by astrophysical origin, merger of supermassive black holes. So, what are those supermassive black holes? You know that we are in a galaxy, spiral galaxy known as Milky Way, right? And this is one James Webb Space Telescope image. You know there are many such galaxies, and many galaxies are just like Milky Way, spiral galaxy. And like Milky Way, all spiral galaxies has one supermassive black hole at the center. So supermassive black holes means we are okay, masses are 10 to the power 6 times of that of the sun. So, okay. And so far I say that stars or black holes can be bound from binaries. But we have seen from this James Webb light pictures that galaxies can also form binaries. Like actually our Milky Way is in a binary system with Andromeda, and when two galaxies are gravitationally bound, they are orbiting around common center of mass. They also get emit gravitational wave, and they come closer and closer, and eventually they merge. Yes, Milky Way will one day merge with Andromeda, but that is not the point. But when two galaxies are orbiting, the central supermassive black holes are also orbiting. So they are emitting gravitational waves. Because of that, they are coming closer, closer. So, and this gravitational is in the frequency I mentioned, that low frequency 10 to the power minus 9 hertz to 10 to the power minus 4 hertz. Uh, every time I will not say this range, I will simply call low frequency or 9 hertz gravitational wave. Uh, Now, this is the gravitational wave I am interested in. But how we detect them without building on interferometer? As I said, we use pulsars. What are pulsars? Pulsars are neutron stars, which are a special kind of, we invented a new English word, undead star. Because they are dead but not dead. So, what is undead star? So, you know alive stars like sun. The sun is a huge blob of hydrogen, right? But it has a shape. See, here if I open a can of hydrogen gas, it will be diffused throughout, right? That is the definition of gas. But then when you see spherical sun, because it is a huge blob, it is self-gravitating system. Means all the molecules around the perimeter are being attracted towards the center because of high mass. But then you will say why it is not collapsing? Because there is inward gravitational force, but there is balancing outward force that comes from gas pressure. You remember P equal to NKT. So if there is nuclear fusion, very high temperature inside the sun, so that gas pressure is very high, it balances gravity. And this type of stars, where nuclear fusion is going on, it is emitting electromagnetic waves, and you are seeing a balanced object are called alive stars. Now, you know, after some time, all the nuclear fusion will be over, but the star will keep on emitting electromagnetic waves, heat and light. So it will start cooling down. So temperature will start decreasing. So that time, this outdoor gas pressure cannot balance inward gravity. So what will happen? All the gas atoms, they will come closer, 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 and they will touch each other, right? But then gravity is too strong. So you remember your atomic small nuclei and electrons in different orbits, right? So at size of the inside the atom, maximum is free space. So gravity will break the atomic structure. So electrons will become free from the atoms, and all nuclei will come close together because of gravitational squeeze. Now electrons are fermions, probably you know. They obey the Fermi Dirac statistics and Pauli exclusion principle. Two quantum numbers cannot be same. Because of that, they give a kind of quantum mechanical pressure known as what's it, Gies energy pressure. Not only electrons, any fermions will give Gies energy pressure. So this time you have nuclei and free electrons, and instead of gas pressure, you have Gies energy pressure of electrons. And they, if they are strong enough, balanced gravity, you again get stable stellar structure. They are known as white dwarfs. But if gravity is so high that electron degeneracy pressure cannot stop the gravitational squeeze, then what will happen? The nuclei inside the atoms, they will also break. And I don't know whether you have read, even like we have atomic models of atoms inside nuclei. Also, all protons and neutrons cannot be anywhere. They have special orbits. So if you break a nuclei, then you can bring protons and neutrons much closer together. So at this moment, you have free neutrons, free protons, and free electrons. And this now proton and electron, they will have Coulomb attraction. So protons will absorb neutrons and will get mostly neutron matter. Those are neutrons now. There can be exotic particles like other baryons, etc., which will not go into details. So today you can consider you have just a free electrons, neutron soup, and neutrons are also fermions. They will also give degeneracy pressure. And if this neutron degeneracy pressure can to balance the gravitational squeeze, you get stable stars known as neutron star, and that is what I work on. And if this initial mass was so high that neutron degeneracy pressure could not balance gravity, you would get ultimate collapse and black hole. So today we will discuss only about neutron star. And this is the life cycle of the star. That's how a star goes, and ultimately the massive becomes white dwarf. Higher, more massive neutron star, and even more massive, then it eventually becomes black hole. But because of all this quiz, there are few interesting aspects of neutron star. They are extremely dense. So if you have a neutron star at the same mass of sun, so its radius will be only 10 kilometers, that radius of a neutron star. But on the other hand, sun's radius is 7 into 10 to the power 5 kilometers. So you can calculate how dense a neutron star is in comparison to sun. So we sometimes say if I take one spoon of matter, which is not possible from a neutron star, its mass it will be as heavy as the pyramid of Gaza. So that's it is very dense, and because so high density, all general features of general relativity are there. Actually, what you heard that precision of the orbit, for solar system planets, it is measured few degrees per century, right? We have a binary pulsar whose orbital precision is 16 degree per year. So because they are so compact. But this compactness is not the only thing. They have extremely strong magnetic field, and they are very rapid rotators. So, yeah. They are very fast rotators. They spin around their own axis in sometimes in the order of millisecond or second. And because of that, these two, they emit electromagnetic beams from their two magnetic axes. So say any neutron star is rotating, and you have laser pointer like beam through its magnetic axis. When it is rotating, this magnetic axis is rotating, also rotating, the electromagnetic beam is rotating. So you people are the people in Earth. So the electromagnetic beam is rotating, it is falling on Earth, you can see. So you see the signal once in every rotation, and that is why they are called pulsar. And we see them in radio wavelength using radio telescope, and we mostly use the radio. So we use here you see many of the world's famous radio telescopes. Like this one is Greenland in West Virginia, world's largest steerable telescope, and that is diameter is 100 meter. In India, we have a smaller but much more sensitive because its technology was very smart. 30 antenna with each 45-meter diameter. It is located near Pune. We use this GMRT, which stands for Giant Meteoroid Radio Telescope. We use this. But remember, all galaxies have pulsars in it. But so far, although we have such advanced telescope, we have discovered pulsars only in our natural galaxies, not anywhere. And you will be inspired that one PhD student discovered pulsars in 1967. So today we know more than 3,000 pulsars. Most are isolated, about 400 in binaries. We use them to test general theories of relativity, which will be a separate talk. But what we do with pulsar, as I say, that you see the signal, that beam, electromagnetic beam falls onto you once in every rotation, right? So it falls. After one rotation falls. After one rotation falls. You say, okay, what is a big deal? So if the pulsar rotates, spin period is 1 second. So I will keep on seeing after 1 second each pulse. But it is not so simple because when pulsars emit electromagnetic emission, they lose their rotational kinetic energy. So they slow down. Also, the space between pulsar and Earth has interstellar medium. So light travels on the interstellar medium. So light gets slow. And if your interstellar medium is a dynamic, so the speed of light also changes because it is speed of light in medium. And the distance between pulsar and Earth, if pulsar is orbital in an orbit, sometimes it comes closer. So the time it takes small. When it goes far, it takes longer time for the signal to reach you. So the time interval changes. And what we do, we say measuring time when one pulse come, next pulse come, next pulse come, and measure 100 pulse. Then I predict when the next 100 pulse will come. I model what can be the spin period, what is the property of interstellar medium, what is the distance, what is the velocity of the pulsar, and then we keep on observing. So if my theoretical guess and my observed guess, we try to match them by modeling. But still there is a difference which we call residual. So obviously it can never be very correct. But say you are observing a pulsar and this difference in time is in microsecond order. Suddenly it increases by some unknown reason. So if there is gravitational wave which squeeze the space between you and the pulsar, it can change. But what about if something else is not happening in that pulsar? Like we have earthquake pulsars have starquake. That is what we do. We observe 50 pulsars at the same time. And each 50 pulsar cannot have a pulsar quake at the same time, right? So if we see if there is something in the residual of all pulsar at the same time, we say, oh, they are being caused by a gravitational wave which is coming far from other galaxies, from supermassive black holes. And interestingly, we know so what should be the relation between that residual caused by effect of gravitational wave or the residual of one pulsar or and the effect of gravitational wave on residual of another pulsar, how they would be related with the angular separation of those two pulsars. That is called Helings and Downs curve. So what we did last year, we just found signature of this theoretical prediction, Helings and Downs curve, to come a number of pulsars. So we are seeing. So there are three group we did. One is American, North American Gravitational Wave Observatory. So in each case, you see the black line, that is the theoretical line which we searched for, and those firing light plots are data point. It has error bars in both directions, so looks like that. So this is the American result, this is Europe plus India's result, this is Australian result. We all found gravitational wave, signature of gravitational wave. And in last 5 minutes, I will tell you about the story of International Pulsar Timing Array. Theoretically, it was proposed something, I think, in late 80s. Then called after the name of their telescope, pulsar timing array. Then Americans started in 2008, North American Gravitational Observatories. Just then, next year, Europeans start the European pulsar timing array, with various European countries and many telescopes together. Nanograv also had 2, 3 telescopes. And in 2015, we started using GMRT. And now Japan, actually one university of Japan, they don't have their instrument, but they are participating in our experiment. So Indian pulsar timing array is actually India-Japan collaboration. But our instrument, because the nature of this experiment is why they did not detect Australia in 2004. Because the nature is this experiment is so that I said that you predict, right, when the next 100 pulse will come, your prediction becomes better and better. The more data you have to do your prediction. So it takes long time. But our GMRT is so extremely sensitive towards best radio telescope that although we are maybe if we compare to Australia, our data is as good as them. So because that I'm not showing you. This is the GMRT again. What I say, 30 antenna, each 45-meter diameter, and one advantage is that you can use say 30 antenna, 15 antenna in one frequency range, another 15 in another frequency range, and you can correlate and you get very good sensitivity. And it is multi-institutional effect. So actually, with 3-4 people we started in 2015. That time we was as one from INSC. I was there, from one from TIFR, two from IISc. We were there. Now we have one engineer friend from RRI, then many IITs and ISARs and Kumamoto University, and we have members in every level, faculty level, postdocs, PhD students, even undergrad students also there. So if you are interested, you can look at our website or our Twitter or our Facebook page. Some of us are here, and here what is the future? As I say that we have detected, but now at the very moment when I am talking here, young students and postdocs are working very hard because I showed 3 different plots, right? American result, Indian and European data already combined, our India and Europe result, and Australian result. Now we are combining the data, and the concept is that gravitational wave search will be happen on the combined data. It will be done, and the detection will be much better with bigger data by the next few months, by the end of this year. And all of us, we are not combining our data, we are observing and taking new data. So there will be that headings and downstar will be better. Also, we do not see one thing. It is quite interesting. Like go have seen single source. They have searched for background gravitational wave. They did not see this. We saw background source, but in our frequency range, we have not seen single source. As birds are of individual supermassive black holes that we hope we will see within next few months when we have combined data. And also we will do more astrophysics, understanding the sources better. And there are few other groups, like China has an excellent telescope, fast 500-meter, which is presently world's biggest radio telescope. They are also doing separately. We are hoping they will join us very soon. Then there is South African, which is their telescope mid-time. Actually, the telescope name is MidCat, and the name of the project is mid-time. And then there is a group of astronomers in Argentina. We are hoping they will also join, and lots of auxiliary science. Like I remember in 2011, North Americans thought that they detected a burst of gravitational wave. Then they realized that actually the mass of Jupiter was slightly wrong. We need to know, because when the signal of the pulsars are coming to Earth, they are passing very close to the other planets, right? So gravitational field of those planets also happen. We have to eliminate those. So mass of Jupiter was wrong in I think 8th or 9th decimal place. So Americans talked to their who in jet propulsion lab who maintained that planetary data. They corrected it. So there are lots of interesting application of pulsar timing science other than discovery of gravitational wave will happen, and the total pulsar astronomy and pulsar timing, astronomy and detection of low frequency gravitational using pulsar. We are expecting a revolution because square kilometer array is the next generation amazing telescope is being built. Those are being built because we need to stay away from human beings who are creating interference with mobile phones. So it will be built in South Africa at few frequency ranges and in Australia in low frequency range. But you see all the countries in dark blue part of this country. So India is a full member and we are contributing in SK square kilometer array. So this square kilometer array will be much better than any radio telescope we presently you can visualize, imagine. So we will do lots of great pulsar astronomy. So I hope many of you will be a good pulsar astronomer and one day I will sit here, you will tell us about new science. And another small thing in the morning I said that many of you are rightfully very ambitious about career and want to go for PhD abroad, but there is no need. You can do cutting edge science by being in India, and I hope to see you teaching me in pulsar astronomy and gravitational astronomy very soon. Thank you.
Session is open for any questions.
How do you figure out the frequency that you said about the ripple effect? The gravitational waves that travel to Earth, that it is not a. How do you figure out that wave is from a certain black hole, a certain neutron star, certain place?
Okay, so uh, this is a general question. So, uh, like when you gravitational wave is coming from this direction and coming from that direction, so the pattern means for LIGO it is easy. They see laser interferometer. Probably you have remembered Professor Uradi was saying that you see a waveform. So the pattern will be different depending upon which direction it is coming, and that because that is why they he was saying that 3 detector will be better because India will help in localizing the event from where it is coming. But for us, it is not so easy, but it is still easy because we don't have, we also have detectors around the world, but we have, so this is the sky. So this is, in sky we imagine imaginary longitude latitude. So we have, you see that many pulsars are around, those are the pulsars we are observing. So if say that your source is near some pulsar, the signature of the gravitational wave will be stronger to that line of sight. But we have not yet done this. So far, we did the easier thing, the combined background gravitational wave we have detected. But what you asked, that we are trying to do.
Every planet or every celestial body have a different pulsar, different pulsar gravity. I'm just saying that you are trying to say that every celestial body or every planet have a different gravitational waves or gravitational.
Yes. So you stand like this, then you rotate, you will emit gravitational wave, but that magnitude is undetectable.
Then how we figure out which this gravitational wave belongs to that celestial body or this gravitational wave belongs to that celestial body? First of all, there are so many gravitational waves which are coming, and how we figure out about that? And they also collide each other. When we drop 2 stones in a water, they make a wave, and they also collide each other. Then, and also we can say that the planets' gravitational waves are also colliding to each other, and they make a new wave. So how we can differentiate between them? This wave belongs to that planet, and this wave belongs to that celestial body.
Okay. Yeah, that is very interesting question. So actually, that's when you see that you have a binary object. So both objects are emitting gravitational wave, but again, what is the characteristic as a superposition, you are getting combined. And from those are coming from outer, not even our galaxy, coming from far away galaxy. So you can, in principle, 2 objects
stop here. Thank you very much, Dr. Manjuti. Now I will request Dr. Suvadeep Mukherjee from TIFR. Sir, please
Hi, can you hear me?
try to complete your talk within 15 20 minutes because we have to break for lunch for around 15 20 minutes before coming. Yeah, please start. Thank you.
So I think I have about 25 minutes.
25 minutes. Yeah, yeah. You just right. So you will be speaking on gravitational wave astronomy and you continue. Start.
Do you see my screen in the sharing the presentations?
Yes.
Okay. First of all, let me thank the organizers for inviting me to do this talk. Uh, so I have already heard about a lot of ways to predict gravitational waves in high frequency using the LIGO detectors and LIGO Virgo and Kappa and in future with LIGO India. And you have also heard about our efforts towards the nanometer gravitational waves which we get through pulsatile. What I'm going to talk to you about is how I am using this gravitational astronomy and opening a new frontier to understand what's going on in the universe using this process. So to cut down to the main summary of what we have learned so far to electromagnetic observations is that you have a complete understanding of the cosmic history that cosmically they use a pretty hot and dense at the early time, and then slowly the universe started forming its first atom, the universe started forming its first galaxies, and now we are in a place where the universe is dominated by something called as dark energy, which is causing the acceleration of the universe as per our knowledge. And this whole understanding has developed from several electromagnetic observations that coming from radio to X-ray and gamma. However, there are many mysteries on our kind of understanding. If I put a chart on what really the universe is made up of, as per you understand, I have to tell you that you only understand the 5% of the events, and remaining 95% is totally unknown. This is a model which fits the data of this way, and we call it the lambda core dark matter model. It has dark energy and dark matter, typically about 60%, 8% and about 20%. But we haven't learned much about these particular aspects. But now, what's interesting, as you've already heard in the predicted gravitational wave, there's a new probe to the universe by which we can see signal deeper and much better. What I mean by signal seeing much deeper and better is because with our currently telescopes that we are planned and operational in the future, we will be able to see gravitational wave sources up to very, very different far away distances. So basically, going back in time of the universe and seeing the gravitational sources such as binary black holes, binary neutron stars, to a very early. Secondly, because gravitational waves really don't interact much with anything else such as stars, it's we can practically see it is the need to from very high resolution. As a result, if you compare them to many other cosmic probes, gravitational waves serve as a very neat observable for us to go and measure the universe back up to very high. And what is now really coming up to the frontier is that the spectrum of gravitational wave which you detect is not only a couple of bands, but it spans from kilohertz range to all the way up to attohertz range, starting from super, like binary black holes, binary neutron star coalescing that we detect from LIGO Virgo Kappa, LIGO India and Future, and the next generation detectors such as Cosmic Explorer and Telescope. Then comes the millihertz range, that's the place over here where you see gravitational signals from supermassive black holes, which is about to detector in space called LISA. And you have just heard a talk on Pascal where he sees that really the biggest black holes in the universe are merging using pulsars at around nanometers range and going up to the can come from the earlier time. Our belief is that spring level of configuration. And that's can be detectable from the upcoming quantum telescope with the Simons observatory by about factor of 10 because then current any measurements and CMT score which is currently in the at the design phase. I will not touch much on the last two, the nanomers and atomers frequency in my talk. But what I'll be talking to you about the other two bands mainly. So let's try to focus on the this LIGO band at first, and let me tell you what are the detectors and they are coming up and what kind of sources we are going to measure from these sources, from this band. So here you are seeing a plot on the y-axis, the redshift activity see the sources, and the x-axis you are seeing the masses of the sources that are detected. What's very interesting, you can see that with advanced LIGO, we are able to see sources of the order of a few tens to hundreds solar mass up to a redshift of about 80 power millimeters. And if you look at next generation gravitational detectors, you'll be able to see way up to a redshift of 100. Practically any black holes we believe to be forming at any cosmic time, we should be able to detect them with the next generation gravitational. On the visa side, the story is pretty similar. Up to the redshifts, which go very far in redshift, around 15, 20. But what's interesting is that we are able to see sources of the order of few millions of stars. So as you can now start seeing, like we always talk about, galaxy surveys, quasars. Now we have a completely different kind of objects with which we can explore the cosmos up to very high. And I will not have much time to touch upon all the details which we can do with this science, but I will take the sequence of summary of why is this a very interesting probe. In my opinion, our simple way to summarize this is that the gravitational wave sources plays a pretty unique role in this length, redshift, source, and time scale domain. We see sources up to very high redshift. These sources can vary in time scale of a few milliseconds to seconds to hours to years time scale depending upon their masses. You have sources starting from binary neutron stars to supermassive black holes, and these sources actually probe physics from very different length scales. When the black holes are very nearby, it's basically probe kilometer length scale physics problems and extreme strong gravity tests, as well as when the properties you see them on the gigaparsec scale, you'll be counting cosmic evolution. So the simple way to think about it, this whole domain of science, the gravitational wave has an impact, can be nothing. This is possible because the signal is very, very well predicted from general theory of relativity. If you are really in a scenario where we actually can predict the signal as a function of time as the black holes are evolving, we can do a lot of different science using these salient aspects of gravity. So to tell you what's now opening up, what gravitational science is really opening up to astronomers, is that we are starting to probe the universe in stellar gravity. With LIGO, with stellar gravities like black holes and neutron stars, we are exploring typically low radiation. And as we have shown over here, this cosmic history of time, we will be exploring a very good using the stellar gravities such as binary black holes of all masses. And that's not the only story. As we just heard from my talk, that there will be also stochastic operators that are detectable, and those can in practice go to very, very high energy. Practically a very early tip off of the universe has just started expanding or accelerating. To move on, that if I tell you that what are the interesting science goals is possibly any science goals you can imagine about in the sense of in astrophysics, cosmology, and fundamental physics, one can do using gravitational waves, starting from searching of dark matter, searching of compact optic properties, multidimensional cosmology. But today I'll be focusing on a very few topics and I'll tell you what are our recent discoveries being made with the help of LIGO Virgo collaboration and the future scopes with both LIGO, Virgo Carla, LIGO India, and in the future with nanoworks. So, to summarize this part, what I would like to tell you that it's a really tip of multi-messenger cosmology and astrophysics. There are telescopes coming in both the gravitational side and in the inside, and they are really transient and static sources. which will be really useful for us to close the process. Let me focus a couple of things now. Let's one of our major discoveries with the help of Lycomel is that we have made our first measurement on the expansion history of the universe using gravitational sources confidently with the with the source having an electromagnetic counterpart. So one of the very appealing aspects in cosmology currently going on is something called as cosmological tension on Hubble constant value, which basically tells us what is the current rate at which the universe is expanding. It turns out to be the case that the two different cosmological probes, supernova and CMB, gives you a very different value of the same number, which is not possible unless there is some thing going on in the systematics, something going on in the physics side, and we don't understand this. And that's what this plot is saying. You know that the blue, the supernova results are around always above 70. The CMB results in black is always below 70. And here is the first impactful result on coming from cosmology from gravitational wave science of first part, where a binary result study in GW17.17, which has been detected by LIGO back then, and we could identify the electromagnetic counterpart to this source with the help of large number of telescopes operating from gamma ray to radio, and we could also identify the close galaxy administration. That's the image you are seeing on the right hand side in the box. When you combine these two measurements, we can get a direct inference of the cosmic expansion history without doing any additional calibration usually required for other cosmological probes, such as supernova. That means I am now having a direct measurement of this Hubble constant shown in blue in the curve below. Right now, our measurements are not very precise because this is from one source, but this is an avenue which is bring up absolutely neat measurement of Hubble constant and which can break the current tension in the in the in the office. Moving on, another very important aspect which gravitational wave will be exploring is cosmic acceleration and testing gravity at the largest scale. Here, the very fundamental idea is that if the gravitational wave propagates from one source to Earth, it gets diluted because of uh, the heat darkness or something called a frictional term, which is shown by this term in the blue box in gamma by gamma zero. So when this quantity gamma is less than zero or greater than zero, you see a reduction or damping of the gravitational wave source because of modified chemical. And this is extremely important to probe because this has a direct impact on our understanding of cosmic acceleration, which we have to easily attribute to that. Here you are seeing a plot made up by one of my students approach, which is showing that we will be able to construct or we will be able to test gravity in a model independent way for the very first time using gravitational waves right sides. This is a plot as a function of redshift in the x-axis and the amount of energy spent on the y-axis is shown. What is very the take-home message for you is that as we go from NBK with I1 or 2 events to about C, which is a next generation gravitational detectors, or our measurement of this quantity will be percent. So that means currently the large range of theoretical models such as Hodesky models, Curtis and series, which predict of the acceleration because of modified gravity, can be explored by gravitational wave intelligence. Moving on now, let's start asking a very interesting question. I now change my topic a little bit from cosmology and fundamental physics to stuff on astrophysics and start asking questions on where and how the black holes form in the universe. What you realize is that this kind of questions were really difficult to answer 10 years back when gravitational measurements were never made. Now we have opened up two windows here to detect black holes. One in the heptahertz range using nanohertz power, and in the nanohertz range using pulse timing array. So let me tell you the story of what we have learned so far and what we will learn from it in the future in the history transient field, we call it GWPC field. Yeah, on the y-axis, the masses of the black holes we have predicted, and the x-axis, the luminosity distance on these plots is practically telling you that there is already up to 90 sources, which is kind of telling us a hint on the population of sources up to very high distance or high ratio. So what we need to do to understand this, what this means is that in this cosmic history, how these black holes are forming, I need to understand it. I need to understand the properties of galaxies. I need to understand the star formation in galaxies, stellar radius evolution, stellar mass, which are these are the quantities which drives the planet stars property, and different formation channels and how black holes actually form in the universe. It's not only one channel, there are many channels by which black holes form. There can be common another, there can be harmonical mergers. So we need to understand what is the story that's actually by which the universe is making black holes in the universe. And Ligo Kavra sources started opening up this window for us for the very first time after very high ratio. Here you are seeing a plot of the distribution of black holes in the universe we have seen in the Ligo Kavra as a function of its mass for different ratios. What this plot is showing you in different colors is that there is a mild hint that the black holes at the higher ratio seems to be little more heavier than the black holes at the lower. And this is very interesting result because for the very first time we are getting a hint on how the black hole mass spectrum is and what is its evolution with the cosmic time. With the future detector, these measurements are going to improve significantly because we already have a factor of 2 more sources than what we had in 0 to 2. This is the work which was led by one of my students was research. Moving on, let's start talking about the pulse of timing element and what can we learn about the black holes from those. So what we need to understand as in the last talk that these black holes of extremely heavy masses of the order of a billion solar mass are possibly present in the center of the galaxies after they have formed. So that means each of these galaxies are going to have a nanohertz gravitational signal extremely weak and superimpose to form a hum of stochastic gravitational. But what's interesting is that there is going to be a very strong correlation between the galaxy properties of these binaries with the gravitational wave masses and the energy they release. But my student has shown Mohit that using nanohertz gravitational wave and galaxy distribution, we will be able to tell for the very first time the cosmic evolution of supermassive. So the cosmology of black holes, how the black holes grow in the universe, and how they evolve is an absolute mystery until date. But what nanohertz gravitational wave is going to do for us is really going to open up this window of understanding how supermassive black holes has formed and how they have evolved. On the right hand side, you are seeing a plot on the signal to noise ratio expected from such a measurement. In yellow, you are seeing the current detectors. So we are not having any very high hope with the current detector because the noise dominated. But in future, once supermassive array will be operational by the end of this decade, we will be in an excellent scenario to get into a measurement close to about 5 or more as we see more pulsars and we make a much better measurement of the signal across a wider frequency. So, in summary, what I would like to tell you is that probing the cosmos with stellar graviars is a new window that has opened up. At the lower shift end, we will be exploring from individual compact objects such as binary black holes, binary neutron stars, supermassive black holes of different masses, from nanohertz of billion solar mass, and from LISA with about 1 million solar mass. And we can go up to really very high redshift, seeing practically the very first epoch of cosmic time using stochastic gravitational wave. When I talk about the stochastic gravitational background, I couldn't touch upon cosmological origin signal, but when we go to the very early time of the universe,
we'll be practically seeing the initial hum of the gravitational wave started coming from initial fluctuations generated during the birth of the universe and how the universe has evolved, which is an extremely interesting epoch because we do not know anything about this so far. And just the very fact that we can go and see gravitational wave up to very far, the gravitational wave opens that window to explore cosmic fluctuations and cosmic inflationary epoch to a very high accuracy. What's interesting is thanks to the currently ongoing detectors, LIGO, Virgo, Camera has a plan, as I'm showing over here, we are currently in the O4 status, shown by the purple bands. We are moving towards O5 in the next few years. And soon after, by the end of this decade, hopefully the LIGO India will be joining the effort, which is currently already funded, as you heard in one of the previous talks. And this is not the only story. What you have to understand is the coming decade is around a golden period in the area of astronomy, with the help of several detectors also in other bands that's operational, are going to be operational. We have DAISY, we have Vera Rubin Observatory called as LSST, Roman Telescope, which is going to be operational in near future. More and in a little bit by the end of this decade, Square Kilometer Array, and by the mid of next decade, LISA is likely to be operational. So that means we are in an excellent situation where we will be basically starting to see the cosmos in multi-messenger bands across EM and gravitational waves. And hopefully the neutrino observations will also help us in that. With this, I will try to wrap up my talk telling you that we are really at an era of data-driven multi-messenger science with the help of electromagnetic observations and gravitational observations. And stay tuned for more data and more discoveries. Thank you very much for your time.
Thank you very much, Professor Shivadeep. The session is open for questions if there are any. So as there are no questions, we will break for 15 minutes for lunch. We'll continue with the program at 1:30. Thank you very much.
Hello, am I audible to you? Am I audible? Hello?
Yes, you are audible.
Okay, all right. I can start. So, hello everyone. I'm Saurabh Sanangi. I'm the Senior Outreach Coordinator for LIGO India. A short brief, LIGO India Education and Public Outreach. So, more on what education and public outreach team works like and how on what basis we work. So before we have been listening about what about LIGO India and the gravitational wave community for past few lectures, and I feel that the students now have are now interested to also know that what career opportunities this project brings for the students of India. So let's begin. So before we begin, let me wish happy 9th anniversary to GW 150914. So we will go through a brief timeline of how we came to this point where we are now building a gravitational wave detector in India. Uh, and this will be really short, but so we know that Albert Einstein, in 1916, when Albert Einstein was working on his theory of general relativity, he predicted the existence of gravitational waves, but he also believed that the detection of these gravitational waves will be very difficult because those will be very weak. Fast forward 100 years, not even 100 years. This was in 1916 when he said that, and in 2015, which is not even so, it's 99 years. And the advanced LIGO successfully directly detected gravitational waves with the help of the two observatories in the United States, the LIGO Livingston and LIGO Hanford. A few years later, on 11th May, Indian Cabinet in 2023, last year, Indian Cabinet finally approves the construction for LIGO India, and India joins the global network. So let's talk about what LIGO India brings to the table of the gravitational wave astronomy. So it will be advancing the gravitational wave astronomy. It will be joining the global network of gravitational wave detectors. Also, this has already been discussed in great details before by Tarun sir, Sauradeep sir. It will also enhance the sensitivity and the precision of the gravitational waves. And while LIGO India is being built, it also requires high-tech, cutting-edge science and technology development, which by building it, we will get more, we will get further introduced to high-edge technology. So LIGO India is a multidisciplinary project which is being built in Hingoli in Aundanagnath Taluka. And when I call it a multidisciplinary project, I mean that this project requires many people from different backgrounds, not only people from astronomy and astrophysics background, but also engineers from, let's say, the vacuum technologies or the laser technology, the optical engineers, even people from the IT and the CS background, where we require people from for cloud computing and data centers. And even from the theoretical physics background who study general relativity and quantum gravity. Apart from these all, there is also a sector where we like to study about how the LIGO India impacts the students and the education in India. So there are works going on where we look after the higher education and the research background through higher education and outreach programs. Uh, so if you want to, now that we have discussed that there are all this project requirement of students in these sectors to get involved in GW science or in engineering part of this, there are opportunities which come up with which this project brings up. So there are summer school programs, there are workshops and research projects happening, and also citizen science projects. So we will discuss one by one everything, and I will also be talking about the upcoming opportunities which are coming in next few months. So every year there is a summer undergraduate research fellowship program organized by LIGO Caltech. This is for the students, undergraduate students in physics, astronomy, and engineering. They are mentored in topics of engineering and gravitational waves in Caltech and in LIGO laboratories. So you can also, to get more information about this program, you can watch our interview on LIGO India YouTube channel of Kushal Jain. He was 2023 LIGO Surf selected student. Then there are summer schools. So ICTS in Bangalore hosts a gravitational wave astronomy summer school. It's for the graduate students of physics, astronomy, and engineering background. So this school is majorly for the students who are working or are interested to work in gravitational wave astrophysics and related fields. Similar schools are also done internationally, which is Manitow Summer School of Gravitational Waves, and the other Cavillum Summer School on Gravitational Waves. There are upcoming opportunities. So the upcoming opportunity right now is workshop on gravitational waves and LIGO India by BITS Pilani. So in BITS Pilani, this is organized by IUCA and BITS Pilani in the Pilani campus. So this will be for the postgraduate and the engineering students interested in learning gravitational wave physics and technology behind LIGO detectors. So to get more information or to apply for this program, you can scan this QR code right now, and you can get more information on this workshop on the website. There's a Get Go scholarship, which is for the students who are interested in pursuing masters through research in United Kingdom. To get more information on this about this scholarship, you can scan this QR code. Before I could discuss about what does PhD and postdoc positions in Einstein first is, let's discuss about what we do in. So before I could discuss, I will come back to this later. This we will discuss about how what is education and public outreach, and what this position of PhD and postdocs actually mean. And then there are gravitational wave open data workshops where the students are trained in handling and analyzing the gravitational wave data. All this information is available on the website. So if you go through this, so on gwosc.org, tutorials and workshop, you can get more information on this data. Then there are research opportunities. So students who have done who are doing their undergraduate or their postgraduate are working on some their bachelor's thesis or their master's thesis. The students can apply for research for their small master's thesis projects at IUCA, RRCAT, or IPR, or in other LIGO laboratories in various parts of the countries. So LIGO India also offers these opportunities. Citizen science projects. About citizen science projects, so we all know, if we are not aware about this, then there is Zooniverse is an organization which organizes different, which has this is a very cool website where you can actually look for other citizen science projects. But over here, I will only be talking about citizen science projects related to gravitational waves. So Zooniverse has the 3 to 4 gravitational wave citizen science projects, where you can help the scientists to study and reduce the noise, or in black hole hunters, where you will be using the data from the test satellite to look after the graphs and to look for graphs. To look at how the brightness of the star changes over time, and gravitational microlensing. You can obviously look at these websites and look for it. So then there are gravitational waves science games around. These are for young students who are not even in their 9th or 10th standard, but younger, who are just getting introduced to astronomy and would like to explore what it is. So these games are available on these games. You can find it on our QR code, which I will be sharing it later. But then there are these games. So you have to dominate being a bigger black hole, or uh, there is this Black Hole Hunter, another game. These are few new games also with GW Science. And Einstein Home is basically Einstein at home uses your computer idle time to search for weak gravity astrophysical signals from spinning neutron stars. So you just give up your computer when you are not using it to the research community, research, and then so let's come back to. So I was talking about the PhD and the postdoc position at the Einstein first. Let me discuss about what we do as LIGO India Educational and Public Outreach. So first is the site and the local outreach. So by site and local outreach, we mean the outreach in Hingoli and Naundanangnath region. So the LIGO India is being built in a region of which is rural, and developing scientific understanding for the people of this rural area is a very difficult task. So for that, we have a special programs where we organize outreach for localites and of Hingoli. Then there is national outreach where we target big institutes like IITs and Jaipur National University and others. And then there is online outreach where we advertise and share information about uh, the upcoming programs and opportunities through social media and through our website. So do check out our social media handles at Instagram, Twitter, and Facebook. We keep posting about upcoming opportunities. So these are a few of the four images about our outreach. So these are from the outreach at Hingoli and nearby districts. Also about the national outreach, and then online outreach. So our online outreach really began in when we were all stuck in COVID-19 due to COVID, and educating people about the project was necessary. Also, every year in the month of February, we organize Cosmic Canvas. It's a gravitational wave science art competition where we ask students to submit their art forms. It can be anything from digital art to drawing to poems and others, and we ask them to submit it on topics related to gravitational wave or LIGO. So these are few of the selected Cosmic Canvas entries. This is an online competition. Also, in the part of gravitational, so in LIGO India outreach community, we handle the news releases where we try to explain the news release of some big gravitational wave detection event in a very simplified manner to students in India and in abroad. But the language is made sure that it's easier to understand. So for that, we translate it to different languages like English, Marathi, Hindi, and Bengali. This is what we have done till now for the news release. About it, so one of the ways we educate the people of Hingoli about gravitational waves and LIGO India is by taking teachers training programs. So we aim at teaching the like not teaching the teachers, but in training the teachers to explain their students, because the best way to propagate any knowledge is by schools and teachers. So once the teachers teach about this to their students and the student goes home and talks to their parents, we are done. We are happy with what we have done in our mission. So we conducted two teachers training workshop in Hingoli about this. So we started with basic concepts which are from NCRT textbooks uh, till 10th standard. So topics like light, electromagnetic spectrum, waves, and other properties of light which are involved in LIGO, like reflection, refraction, and interference pattern. Also, in the second part, we talked more about the career opportunities similar to what I'm discussing today, and about more concrete topics related to LIGO and gravitational waves, how gravitational waves are formed, or what how the LIGO will be detecting. One of the major aims of doing these teachers training program is also to not let misinformation spread in that region. Also, we also take opportunities to teach local students, especially students from 8 to 12, 8 to BSc level, where we try to explain the hard concepts of complex concepts of gravitational waves, because the idea of gravity is only limited to Newton in places like Hingoli. So over there, talking about a detector which is detecting gravitational waves, which is not related to Newton, is something which becomes a difficult task, and we try our best to educate them in a manner where even the students from 8th to 10th standard or higher level understand this. Also, there are other national space day celebration programs which we which we participate in. So let's go back to the PhD and the postdoc position. Before I go to this, so the PhD and the postdoc positions in just a second. Okay. So the PhD and the postdoc position in Einstein first is for the students who have done their masters and who are interested in doing research in outreach. Especially the PhD and the postdoc position is to look for so Einstein first is a project in which they have introduced the Einsteinian physics to the school students through teaching, and the project and this PhD and the postdoc positions looks for the development in the students which has happened due to this project. This project is in Australia, so this will be up on website sooner. Right. And then, if you want more information about gravitational wave or LIGO education and public outreach, there are these resources. So if you go on this website, you can find all the educational resources and the books which you might quench your thirst of understanding of gravitational waves and physics. And LIGO India keeps uploading videos and interviews related to gravitational waves and LIGO on its YouTube channel and Vimo channel. And please scan this code and you will get information about other opportunities which I had already mentioned. Thank you. Are there any questions? Hello.
So Devesh, sorry, Saurabh, hello.
Yes, sir. Yes.
Yeah, so just a quick question, since uh, nobody else is raising a hand. It's not a very important one, but I thought I'd ask anyway. So, I mean, how can students from say IITs participate in this? Some of the
So,
programs that
uh,
you
so you mean through for out programs in outreach or engineering?
both maybe. Can you, if you
Okay,
can say
so
a few words?
okay, IITs organize so for outreach we have IITs organize tech fest and science fest in their institutes. If they call us or invite us, we usually participate. And if we are not able, so we even give out our uh, books and then instruments which we use for outreach. Uh, okay, I will come back to your question later. And so when we participate in IITs, we make sure that the students from IITs also participate in it. So by that they can also join the outreach community. Also, if they mail us, me or Devrit Chatterjee for gravitation for outreach programs, then we definitely work with them also for
So basically, for I mean, you can actually send a team over to the IITs for the tech.
yes, we do send our teams
Is
to
there any
IITs.
facility for, say, a few interested students to go and visit some of the LIGO India facilities? I mean, institutes like IUCA, for instance, to.
Yeah, they can come to institutes like Ayuka, but I think a better information on this can be given by Suresh sir.
Okay.
Yeah.
I think
And
you were saying something else also, yeah.
yes, so I was also saying about for students interested in engineering and the science part of gravitation, where they want to work on some thesis or some project for their skill development, they can mail to professors who are working in LIGO, and or they can get information about this on our LIGO India website. So they are always invited.
Okay, thank you so much, sir.
Yes, sir. Uh, is there any workshops for MSc physics students? Workshops in it depends on so we don't organize workshops just for some particular group of students, but if your institute invites us for some program or for some workshops, then we organize it for BSc and MSc students together. So there is so we have divided our outreach programs into we can say two or three parts. Where first we target the young students who have not much information, just a basic understanding of things falling down due to Newtonian gravity. So we can say that 8 to 10, 12 standard kids. But for BSc and MSc, we have developed programs where we try to explain them topics which are more complex about gravitational waves and like so.
So thanks, Saurabh. Thank you very much. Now, next speaker is Professor Patrick Das Gupta, a pioneer in the field of quantum mechanics in India. Sir, am I audible to you?
Am I audible?
Yes, you are audible, sir.
All right. So first of all, I begin by thanking Professor Sharma and his team members for organizing this wonderful one-day seminar to commemorate the first direct detection of gravitational waves exactly on this day 9 years back. So let me try going to my slides.
Sir, go to share and then entire screen. Then click
That's
on
right.
the screen and then share.
Yes, yes, I have done that. Are you able to see my entire
No,
screen?
no, not yet.
Oh,
Go to share on this Google Meet screen.
okay.
There is a hand besides it. It is a tab written share.
Uh,
So click onto that. If you will click that share, then a screen will be there. Then
One
on
minute.
that screen there will be the three tabs will be there. So last one entire screen you have to click.
I'm seeing an arrow tab called
Yeah,
present
yeah, yeah.
now.
Yes. You
So
please click onto that.
that's right. I've done it. And then uh,
A
the
screen is
share is
seen.
not highlighted, but let me check this. The share part is not getting highlighted. Uh,
No, if you are clicking on share, then something is happening or not.
no, the only the cancel part is highlighted. I have put the option to the entire screen. Uh,
Yes. Then there is a screen which is
okay,
seen. You
now I
click
got it.
onto that.
Okay, now I got it.
Yeah. You click on that and then click share.
Yes,
Yes. Yes. Yes.
are you able to see the
Now, now
slides?
you now you do full screen.
Yeah,
Then it is visible.
yeah, sure.
Okay. Yeah. You start, sir. Thank you.
Yeah, great. Thank you, Professor Sharma. All right. So I'm going to speak about some of the sources of gravitational waves which are of interest in the coming future. Of course, this has been highlighted again and again in this one day seminar, and let me not uh, go into this, except that this was the first detection. Fortunately, was a strong burst, and as you can see, that even without going into the data analysis part, which is the expertise of Professor Anand Sengupta, who is going to speak shortly, the evidence of gravitational wave in both the independent LIGO detectors were quite obvious. And this, we already know that amount of energy that gravitational waves carried for this first event was three times the rest energy of the sun. Uh, uh, Now, we all know that Albert Einstein, when he realized that Newtonian gravity is not consistent with special theory of relativity, he worked for about 10 years to get a gravitational theory which is consistent with special relativity, and lo and behold, he found that gravity is not a force, but rather it is the geometry of the space time that masquerades as gravity, and the geometry gets warped by the energy and momentum of matter. So, Newtonian gravity would say that the satellite is going around the Earth because of a gravitational pull by the Earth, while Einstein's general theory of relativity says that actually the energy and momentum of the spinning Earth, it distorts the space-time geometry. It's the space part is no longer Euclidean, rather the space part is non-Euclidean, and a freely falling object like a satellite, it just follows the geodesic, that means the shortest space trajectory in this curved space-time. But of course, we all know that gravity is universal. That's because everything in the universe has energy and momentum, and therefore everything in the universe would cause gravitation. Unfortunately, gravitation is also the weakest force, and that's the reason why it took 100 years after the prediction of gravitational waves by Einstein to have been detected directly by LIGO. And for all standard matter, we all know that gravity is attractive. Uh, so, this is just a picture to just illustrate that more compact a mass is, that means if the density of the matter is high, the curvature in the space time will also be great. Let me not go into this slide, it just illustrates what is the meaning of non Euclidean geometry versus Euclidean geometry. Two predictions of general relativity were a black hole, where if matter is compressed to a region below the so-called event horizon, entire matter collapses into a single point where the density becomes infinity, the space-time curvature becomes infinity, and infinity in mathematics and physics is referred to as singularity. So, if you compress any matter, for example, if you compress our sun to a radius below 3 kilometers, then entire matter of the sun would just collapse into a point, and there'll be a mathematical surface around this singularity called the event horizon. For the sun, the mathematical surface will have a radius of 3 kilometers, and this was black hole formation was one of the predictions of Einstein's general relativity. But there was another prediction of general relativity which says that anything, any matter, if it changes its mass distribution in an asymmetric fashion, then the geometry of the space-time propagates like a ripple in the geometry of the space-time. So even when I am speaking, the vocal cords is not only producing sound, but the vocal cords are vibrating. It is also producing gravitational waves. Unfortunately, the magnitude of the gravitational waves is very tiny when I am speaking, because gravity is the weakest. So you need astrophysical objects so that the energy and momentum carried by them is so large that when the matter distribution from such heavy sources change with time, they send a ripple in the space-time geometry, which we call gravitational waves. There is a lot of difference between gravity and electromagnetism. Even in the case of Newtonian gravity, we know that only those particles which have charge, only they can experience electromagnetic forces, while gravity is universal. And because of the Newtonian gravitational constant g divided by fourth power of the light speed in vacuum is so tiny that gravity is also the weakest of all forces. However, because mass and energy are additive, if you take astrophysical objects, then the net energy, equivalently net mass, is so large that the gravitational wave produced by asymmetric motion would cause gravitational waves that could be in principle detected by detectors like LIGO. Uh, so, in other words, we know that if you have two objects which are attached with a light spring, and the two objects have identical masses m but opposite charge q. One has charge q, other has minus q, and you set this into oscillation, then both dipole electromagnetic wave will be produced. But Einstein's general relativity also says that quadruple gravitational waves will be produced, because such an object, when they oscillate, the quadrupole moment also changes. Pure dipole gravitational wave radiation don't exist. Ultimately, it is the mass quadrupole moment which is defined by this, where rho of R0 is the density of matter. Their change, asymmetric change, causes gravitational wave, where the second two double dot means second derivative of the reduced quadrupole moment, which is obtained from the normal quadrupole moment by certain application or projection operators. And the reason why the gravitational wave amplitude is very tiny is because of this factor, Newton's gravitational constant g divided by the fourth power of the speed c. C appears because general relativity is a relativistic theory of gravity. Capital G, of course, appears because it is a theory of gravity. So, in other words, any asymmetric motion would cause ripples in the space-time geometry that would propagate outwards. While the general Einstein equation is given by this, let me not go into the mathematical details. While if you have a very tiny perturbation on the Euclidean space-time, the tiny perturbation is the gravitational wave amplitude that satisfies the equation of this kind. If there is no matter, then del square by c square del t square minus square of the, or rather minus the Laplacian operator is zero, which is nothing but a wave equation. This tells us that gravitational wave also propagates with speed c. And this is the mathematical expressions for relating the gravitational wave amplitude, the space-space component of the gravitational amplitude, with the second derivative of the trace-reduced quadrupole mass tensor. This is the space-reduced, the trace-reduced part, and because of the second derivative of the mass quadrupole formula, it has the same dimension as kinetic energy. So for back of the envelope calculation, you can, from this, you can get an approximate formula which says that amplitude of the gravitational wave is simply 4 times the gravitational constant times the kinetic energy associated with asymmetric motion divided by C4 times the distance of the source. So if you have two massive objects, then when they go about, the quadrupole moment changes, and applying the formula, you can show that the gravitational wave amplitude has this form, which is called the chirp waveform, and this is what was detected by the LIGO detector. And there was a faint, unfortunately the noise was very large, there was a faint hint of seeing quasi-normal modes of the final black hole formation, namely the ring down when the black hole was settling down to its stable form. And incidentally, here I must mention such a ring down was predicted in 1972 by late Professor C.V. Vishweshwara. And the chirp waveform for two mass points going around and sending gravitational wave and thereby losing energy and then inspiraling towards each other. This has been confirmed by many, not only the first directly detected two black holes going around each other, but many such objects. And the waveform is given by this mathematical expression. So this is at least to certain post-Newtonian order, this has been confirmed very well. So one of the things the gravitational wave is different from electromagnetic wave is that its antenna pattern has a quadrupole radiation pattern, unlike the dipole radiation of electromagnetic wave pattern, and these two patterns are different. However, just like electromagnetic waves have two distinct polarization, so does gravitational wave. So if you have test particles put in a circular ring, normal, the plane being normal to the incident direction of the gravitational wave, the plus polarization, when it goes through, it would make the rings deform in one half of the cycle in this manner and in the next half of the cycle in this manner. While the cross polarization, if it goes through, then the deformation will be this kind. So essentially, this deformation is related to the tidal deformation caused by the gravitational waves. So we have already seen two mass points coalescing. They have been detected, but then there are other predicted sources of gravitational waves which could be detected by future detectors. Namely, if you have a neutron star spinning with a magnetic field, such objects are called pulsars. Then if the neutron star is non-axisymmetric, if it is axisymmetric, then no gravitational wave will be emitted because the quadrupole moment doesn't change. However, if it is slightly, if there's a hill or any deformation on the surface of the neutron star, then the quadrupole moment will change with time, and such periodic gravitational waves will also be detected. And I hope Professor Anand Sengupta will speak more on this. Then there are, of course, supernovae, which are the end stages of the evolution of a star, massive star. Such supernovae have been detected. For example, this is the explosion that was directly detected in 1987. It's called the 1987A and supernova. And because supernovae are expected to be non-axisymmetric, so therefore of the order of kilohertz frequency gravitational waves are expected to be emitted, because the core collapses within a time scale of millisecond, and therefore the gravitational wave. Another difference between dipole electromagnetic radiation and quadrupole gravitational wave relation. So neutron stars, two neutron stars which are going around each other. We know that spinning neutron star with magnetic field, they are detected as pulsars. I'll talk a little bit of pulsars in the subsequent slides. But two neutron stars, when they go around each other, incidentally, the first case of indirect gravitational waves were detected from such a binary neutron star, namely the so-called Hulse-Taylor binary neutron star. And Hulse and Taylor received the Nobel Prize in 1974 by showing that the amount of energy released by such object exactly matched the quadrupole Einstein formula of energy released due to gravitational wave. So when two neutron stars, as they release gravitational wave and thereby lose orbital energy and spiral towards each other, when they collide, they not only give out intense beam of gravitational waves, they also release intense beam of gamma rays and X-rays, the so-called short duration gamma ray bursts and kilonovae. They have been observed, the so-called gravitational wave 170817, which Professor Suresh Doravary will highlight on. Eventually, of course, they form black holes. So in other words, supernovae, when the core collapses to either a neutron star or a black hole, they can release powerful signals, gravitational wave signals. Like we know that there is also a type 1a kind of supernovae, where a white dwarf star, when matter falls on white dwarf star from a secondary or from circumstellar medium, then the white dwarf star, when the mass becomes bigger than the Chandrasekhar limit of about 1.4 solar mass, that implodes and gives rise to a type 1 supernova. Crab supernova remnant that we can see on the sky is an example of a remnant of a type 1a supernova. And such supernovae also can release gravitational waves. Then there is also gamma ray bursts. Gamma ray bursts, the prompt emission of gamma rays take place from such objects, and there are two kinds of gamma ray bursts. One is the long duration gamma ray burst, whose prompt emission of gamma rays is the duration is greater than 2 seconds, and short duration gamma ray bursts, which are gamma ray bursts believed to be caused by inspiraling of two neutron stars, and there the prompt emission of gamma rays lasts for less than 2 seconds. Now, according to the theoretical models, long duration gamma ray bursts are the final stages of a huge star whose mass could be greater than 30 solar mass, so that the core is of the order of 100 to 1000 mass, essentially are made of iron. And because when the heat goes away, such an iron ball cannot um, uh, be stable, because gravity, again, due to Chandrasekhar's work, we know that the gravity cannot, gravity will be overpowerful. It's overpowerful compared to the Pauli exclusion principle, and the whole 100 to 1000 solar mass iron ball collapses to a black hole, and the circumstellar debris around it forms a disk, and that they give rise to jets of powerful gamma radiation. And these are the model for long duration gamma ray burst. And here is a schematic: the circumstellar disk around the black hole, because of the rotation, there's angular momentum axis, and the gamma rays are emitted along the axis in a jet like form. And these, because they are the result of the collapse of 100 to 1000 solar mass iron ball, they'll be powerful emitters of gravitational radiation. The other is the short duration burst, which we have already talked about, two neutron stars going around each other. And the evidence for such an object has already been seen by multi-messenger astronomy, as well as gravitational wave detector, LIGO detector, namely this particular event, which Professor Doravary is going to highlight on it. And multi-messenger astronomy is going to play a very, very important role. And one of the early papers of Bernard Schutz in 1986 also showed that if you have both the electromagnetic counterpart of a gravitational wave source as well as gravitational wave source, you can also estimate parameters of cosmology like Hubble parameter and the deceleration parameter, because gravitational wave signal, when you detect the signal, that gives an independent, and if you know the exact form you expect, you can find out the distance independently, while the electromagnetic signal, from that you can find out how the electromagnetic waves get stretched because of the expansion of the universe. The stretch plus the independent distance measurement can lead to parameters of the Big Bang cosmology. So here is an example. The Chandra X-ray telescope, this has observed the so-called Crab pulsar. Within the Crab supernova remnant, there's a pulsar, namely a spinning neutron star with great magnetic field. And because the magnetic field is precessing about the spin axis, the electric and magnetic fields change with time, so that an outside observer sees that when you have a changing electric field, and that produces a huge amount of electromagnetic signal. And this is what essentially drives the emission from pulsar. Of course, pulsar radiation mechanics is very complicated. It's a still matter of research. But the evidence of rotation is clear from this actual Chandra X-ray image of the Crab pulsar. The Hull stellar binary pulsar, as I told you, about two pulsars going around, this was detected. The research work was done in 1974, and Hulse and Taylor got the Nobel Prize, I think, in 1993. And this was the indirect evidence for gravitational radiation. Then you also have neutron stars, which have incredibly high amount of surface magnetic field more than 10 to the power 14 Gauss. Such neutron stars are called magnetars, and the evidence for such magnetars come from the fact that there are astrophysical objects which time to time release huge amount of X-rays and gamma rays, and when you model them, you find that these are rotating neutron stars with magnetic field more than 10 to the power 14 Gauss. And it is believed that the magnetic flares and magnetic reconnection is responsible for such energy. Now, because of the high magnetic field, it is expected that the magnetic stress on this magnetas will be huge, and therefore they would not be axisymmetric, and hence the magnetas, which typically are slowly rotating compared to normal pulsars, 1 seconds to 10 second. So you have a rotating object, and because of this intense magnetic field, if there's a deformation, then they could release periodic gravitational wave, which in principle LIGO can detect. Uh, for general curiosity, you know that there's the Orion constellation, and one of the stars in the Orion constellation, namely Betelgeuse, is poised to undergo supernova explosion. Of course, we can't say when, 100 years, 1,000 years, there's still matter of uncertainty. Uh, now I go to the cosmological sources, namely, we know that if you peer into the deep sky using a powerful telescope, then you see galaxies, elliptical as well as spiral galaxies. So here is an example of a spiral galaxy. Here's another spiral galaxy viewed edged on. Then you have also examples elliptical galaxy. By now, it is evident, and 2020 Nobel Prize was because of showing that there is a supermassive black hole at the heart of our Milky Way galaxy. Now, there is strong evidence that almost all galaxies at their core have uh, huge supermassive black holes. By supermassive black holes, I mean black holes which weigh more than million times the sun's mass. And there is a fantastic correlation between supermassive black hole mass and the bulge of galaxies which house these supermassive black holes. And we know that galaxies also interact with each other, and because of the dynamical friction predicted by Chandrasekhar, they spiral in towards each other. And obviously, black holes in these two such interacting galaxies will also spiral in together, and such binary supermassive black holes evidence are there. For example, the radio galaxy 0402 plus 379 is supposed to be a binary supermassive black hole, and the supermassive black hole, the total mass is about 15 billion times the sun's mass, and the orbital period is about 24,000 years. So from this you can see that the gravitational wave frequency will be roughly 2 divided by this orbital period, and it will go to the nanohertz level. So you would have already heard Professor Manjari Bagchi that nanohertz gravitational waves, they can be very well studied using the pulsar timing array, and Indian pulsar timing array is also going great guns. And such uh, binary supermassive black holes as well as stochastic gravitational waves believed to have been released when early in the universe, if there was a phase transition, then you could have colliding bubble walls. They would release stochastic gravitational waves, and the pulsar timing array has given bounds on the density, energy density in the stochastic gravitational wave. Then we also know that the very low frequency gravitational waves can also be detected by space-based gravitational wave detector like the LISA or LISA, and we hope it will soon be launched, so that if you have radio sources, powerful jets coming from the accretion disk going around supermassive black holes, one could estimate the kind of gravitational wave from using the LISA detector. Then there are other exotic idea, namely white holes. People have speculated when black holes form, then instead of forming a singularity, the singularity might be linked to another region of space-time, so that the entire matter which collapses gets out, the so-called white hole. And there are all kinds of conjectures. Some people have shown that, in particular, Kip Thorne has shown that white holes are exceedingly wormholes as well as white holes are unstable. So if they are formed but unstable, they will again collapse to black hole. Such processes will also release gravitational waves, and such exotic objects can, in principle, be detected by gravitational wave detectors. So, in other words, that because gravitational waves are very weak, therefore, their scattering cross section or absorption cross section by other matter is negligible compared to electromagnetic waves. They are negligible even compared to the neutrinos. And therefore, in the early universe, just after the onset of Big Bang, any quantum fluctuation which would have released stochastic gravitational wave, bubble collision due to phase transition, which would have released gravitational waves, they can be detected today here because the gravitational wave produced there hardly will get absorbed or scattered because they are extremely weak. And hence, low frequency gravitational wave detection can tell us a whole lot of things about what was going on when Big Bang took place and the entire space time and matter was created so as to produce galaxies, eventually planets, and eventually us. And so, in other words, we would be able to, using gravitational waves, unlike any other particles, whether it is photons or neutrinos, that cannot be seen from the Big Bang time era, gravitational waves can be seen. So, although they are weak and therefore very hard to detect, but because of the weakness, there's a strength also. They also hardly get absorbed or scattered, and hence detection of such highly low frequency but weak gravitational waves will tell us about the dawn of time when entire universe, space-time, matter were created. I think I should stop here. I would rather take questions. Thank you very much for your patience.
Thank you very much, sir.
There seems to be some other
Yeah. So
device
the
which is.
session is now open for questions if there are any questions. So, if there are no questions, then we say thanks to Professor Das Gupta, sir.
Thank you. Thank you.
Thank you very much, sir. It was very nice to hear you. Now, we will be having an offline talk. Dr. S. Sunil, who is Scientific Officer at Institute of Plasma Institute of Research, Rani Nagar, will be speaking about the role of vacuum in gravitational wave detection. We will pause for 5 minutes, sir.
लैपटॉप उन लोग का था सेकंड फ्लोर का थर्ड फ्लोर का नेट बंद हो गया है तो उन लोग को चालू करना है
Everyone might have gone through vacuum systems and vacuum things. So, in a simple way, one can understand is if you define the number of particles inside a chamber, you can say that it is in a vacuum state, or it is in a not vacuum state. So suppose if I have two chambers and I differentiate between two chambers, one is having larger number of particles and the other is a lower number of particles. So relatively, I can say that there is a pressure difference because there is a particle number of particles change. So in terms of vacuum, when we say, we define in terms of the mean free path. So mean free path is nothing but the distance between two particles. So if you go through the regimes, you change from viscous to transition to molecular regime. So this is a table which actually shows that what is the molecules per meter cube in an ambient condition, a low vacuum, in a medium vacuum, high vacuum, ultra high vacuum, and extremely high vacuum. So these are numbers which comes into picture when you talk about uh, ambient conditions to ultra high vacuum condition. But in an astronomical scale, when we talk, because we are discussing with gravitational wave detection, in an astronomical scale, you can just see what the parameters looks like. In the interplanetary space, it is around 11 molecules per centimeter cube. So that means if you have a box of 1 centimeter cube, volume of 1 centimeter cube, you'll see only 11 molecules there. But on an interstellar space, you will see only one molecule per centimeter cube. Whereas on an intergalactic space, you can see 10 raised to minus 6 molecule per centimeter. So you can estimate how much of a particle are there when you talk about space. Yeah. So curiosity arises when we say the farthest thing that we see today is 46 billion light years away. So that means a photon or a light which you can see is around 46 billion light years away. Now, this is something which which you feel that it is a huge number, but after the Big Bang, when you see chronologically how the time started. So when I say Big Bang, that is t is equal to 0. That is the time just started, and from there to almost 13.7 billion years.
Sunil.
Share this PPT.
Yeah, so I think that is
So sorry.
Yeah, yeah. We cannot see the top.
Thank you, ma'am.
Yeah, okay.
It's a Microsoft PowerPoint. Yes, GNU talk, no? The Microsoft PowerPoint. No, this. I think. Now, is it visible? हाँ? Sorry. अच्छा एक मिनट है कोई बात नहीं सेलेक्ट विंडो और स्क्रीन एंटायर करना था ना मैं खुद कोई बात नहीं अब yes now it is better na yes now you please now can you see
Yes. Thank you.
okay should I start from just one slide before just for the sake of continuity or I can start from here
Yeah, it's fine. Yeah.
okay, so I was just defining the basic about vacuum.
Sure.
You have two chambers with a different number of particles, and then you say that it's a pressure difference. Where particle density defines the pressure difference. One being a higher pressure, and the other being a lower pressure. And I was trying to explain the regime which it follows from viscous to transition to molecular regime, and these are defined by the mean free path. And the tabular shows that how much of a particles per meter cube is there as you follow from ambient pressure to extremely high vacuum. On an astronomical scale, I was saying that interplanetary space, interstellar space, and intergalactic space, how much of a molecule per centimeter cube exists. Going to the next slide, I was just telling that curiosity arises when we say that the farthest thing that we see today is 46 billion light years away. So I was trying to explain that after the Big Bang, when we say actually our time t is equal to 0 started, to almost 13.7 billion years, that is the present day, the present moment, we are around 13.7 billion years away. So there are a lot of time from t is equal to 0 to the present day that many things happened on an astronomical scale. And there are some instances where nothing could be revealed. So normally we say that those are the dark matter or the dark space that one could not follow what was there. But those were the times that there was something which was going on an astronomical scale that we see right now. So if you look at this chart, you'll see that it's only 5% of the matter that we know exists, but there are almost 90% which is still undisclosed. So there is a lot of energy in hidden space as far as the whole space is concerned. And now, as far as the states of matter, everyone knows that there is a solid, liquid, and gas, and there is also a plasma state, which is a fourth state, which IPR is dealing with. So this is how curiosity arises, and we say that how the vacuum becomes an important part in defining what happened from Big Bang to the present stature that we are right now. So the importance of vacuum exists in presence of space. So and the conducive conditions that has evolved in the present status, and the less interference, because there has not been interference, or if there has been an interference, maybe the things would have been different. So less interference. So in short, we can say that an ideal condition for a precision. So as far as the LIGO detector is concerned, the precision brings about precision is very important. That is an ideal condition to exist and to detect gravitational waves. So commonness, what you see in the laboratory scale, this is just pictorial demonstration where you see that we have a LIGO. There's an international science facility. Then there is a CERN. Then there is ITER, and then there is LZ. Now, this LZ is primarily based on dark matter experiment, and facilities at IPR. If I highlight these, SST1 is there, Aditya is there, LVPD is there, and LI Vista is there. Now, the commonness in all these facilities is vacuum, and the chambers are huge, and maintaining vacuum is an extremely tough condition, because without vacuum things won't work. We won't get the idealness what we want to achieve. So that's a common feature in all the big experiments which is going around in the world. Few points on gravitational waves which I would like to highlight just for the sake of continuity, because you have a lot of other speakers who has already disclosed all these things, so it's not a new thing. So here you see that there are binaries which are orbiting around each other, and they produce gravitational waves. This is one of the black hole merger which led to the first direct detection of gravitational waves, and they gave us a Nobel Prize. So this is a video clip which this is actually a working model which shows the deformation in space, and this video model I would like to share. Oh, somehow it's not working.
You click on it.
Yeah. No. Anyway, so this is one working model which demonstrates that if you have a denser media, in a fabric of space time, it actually deforms the space time. So here there is a pictorial representation. So you see over here there's a huge mass which actually deforms the space time. And if you have a lower mass coming close to it, this orbits around the heavier mass, and they ultimately merge. And when they merge, the energy which is released by the smaller mass or the um, orbiting of both the masses, those are the gravitational wave which propagates from that particular place to outside. Now, there are different concepts of gravity which people have been discussing. Newton proposed that the deformation of space-time cannot be possible and it's infinite, whereas Einstein with Einstein field equation, he has shown that uh, if you have 10 raised to 43 newtons put somewhere, you can actually deform the space-time. So gravity is a curvature of space due to a massive object. So if you put a massive object, then the lower object will come towards it. So instead of saying attraction, it's actually merging towards each other. So gravity is a curvature of space-time. And how much of an energy is released is defined by the luminosity value. LG is so enormous that the distortion space-time and generates gravitational wave which travel with the speed of light. So this is one of the important features that how the gravitational wave emits and it is propagating. Now, the fact is, at the point where the gravitational wave produces, the amplitude is very high. But when it travels in the vastness of space, its amplitude decreases. And on Earth, if you observe these gravitational waves striking, we see a very minuscule, a tiny feature. Now, this is actually merge. This tiny amplitude gravitational wave actually are merged with the noise, and it becomes extremely difficult for us to pick out the gravitational wave or differentiate between the noise and the gravitational wave signal. So one of the best devices which has been which is being used is the gravitational wave detector, which is actually a laser based gravitational wave detector, which is normally called as LIGO, laser interferometer gravitational wave observatory. Now this also people have discussed about this, but just to give a feel of what the interferometer is, it's a simple Michelson interferometer. But in a Michelson interferometer, you have only two mirrors placed right angle to each other. But if you want to detect gravitational wave using a simple Michelson interferometer, then your arm length has to be very long, maybe of the order of 700 to 800 kilometers long. Now, if you want to reduce the arm length, you'll have to fold the beams which are going across. So a simple way you can do is insert two mirrors, make a fabric cavity within the arms, and you simply fold it. Now, when you fold this, you're actually defining the same path length, but you have reduced the length to almost 4 to 5 kilometers. So this is one of the simple feature of Michelson interferometer and very effective in detecting gravitational wave. Now, gravitational wave signal is usually denoted by a strain, which is called the delta L by L, ratio of delta L by L, which is actually defines the displacement between two spots and the distance between the two spots. And this is one of the simpler representation of a LIGO interferometer working in US. And these are some of the parameters. So you can see that even though there are only a small number of optics which are shown over here, but there are huge amount of optical components which are involved as far as the function of the detector is happening. These are some of the parameters which shows that what and all are the key features of LIGO interferometer. Now, when you talk about laser-based detectors, it's not very easy because there are a lot of noise which comes along with it. So some of the noise which are described over here are seismic noise, Newtonian noise, thermal noise, and quantum noise. Now, these are seismic is due to a ground motion, Newtonian noise is due to gravity gradient, Thermal noise is from the mirrors and suspension. Quantum noise is the photons, that is the lasers. Now, if you look at the graph over here, all these noises are represented by different shades, but this dark one is a total noise. So integrated effect of all this actually defines how much of a noise or how much sensitive your detector is. So here primarily, if you see that the sensitivity is between 100 to 1000 hertz and the sensitivity is around 10 raised to minus 24 root hertz. Now here we represent in terms of the noise factor, because all the noise, because the signal of the gravitational wave is very less, so that you decipher in terms of the spectral density. Now the main task is to identify each noise and try to mitigate it. Now, role of vacuum system comes, role of vacuum in LIGO comes in defining how much of an extra noise that particles are giving. So this is a schematic of LIGO India, especially. This is a slightly modified version of what is there in the LIGO US, but not compromising on the functional aspect of it. So these are some of the chambers which are represented in HAM and BSE, and this yellow ones are the cryo pumps, and the beam tube is represented as BT. So there is a exam in the YM, and there is a filter cavity over here. So these are some of the big chambers which has been constructed, which has been fabricated by IPR, and these are all 1:1 prototype chambers now. And we have one of the so we have touched almost all aspects of vacuum chambers as far as LIGO India is concerned. Now these are some of the parameters which are shown here. It is just to highlight that how much big your volume is. Now if BSE is called the basic symmetric chamber, and HAM is the horizontal axis module, and CP is the cryopump, and IVV is the integrated vacuum vessel. Now, BSE and HAM actually holds the key optics which are required for the operation of the LIGO interferometer. Now, these are the some of the parameters, like volume of BSE is around 27 meter cube, HAM is 11 meter cube, CP cryopump is around 14 meter cube, IVV is 25 meter cube. And as far as the height or length is concerned, it's around 5 meter, 3 meter, 5 meter, and 20.6 meter. Now, diameter also you can say that it is around 2.6, 2.1, 2, and 1.24. Now, these are all 1:1 chambers, and these are not a single chamber. If you consider HAM, there are around 8 HAMs, and BSE there are around 5. And the total volume which encapsulate the LIGO detector is around 10,000 meter cube of volume. Now, all this said, how much is the vacuum you require? You require vacuum of around less than 1 into 10 raised to minus 9 millibar. Now, this is a requirement for a fully function to make the detector functionable and do not compromise on its sensitivity. Now, how this value of 1 into 10 raised to minus 9 comes, that is what the next slide shows. So, one knows that gases, the ambient conditions over Earth, the gases that comprise are nitrogen, hydrogen. There are major constituents of gases are nitrogen, hydrogen, water, oxygen, argon, carbon monoxide, carbon dioxide, and methane. There are other gases also, but their concentration is very less. Now we have to attain a pressure, a vacuum of 1 into 10 raised to minus 9 in a 10,000 meter cube volume. So how does this affect those? There's a simple relation which actually shows that your noise factor is directly proportional to your pressure, square root of pressure, and R. This R is actually directly proportional to your alpha, that is a molecular polarizability. So if you know that whatever is the species that are coming in between, you have to reduce it. This only helps the functioning of a efficient functioning of a detector. Now, if the proper vacuum is not preserved, there's something called acoustic noise also that comes into, or acoustic displacement that comes into picture, that actually moves the mirror if the pressure is not properly maintained. So, and the gases and the pressure which needs to be maintained in this volume is nitrogen around minus 11. These are in millibar. So I can say that 1 millibar is around so much of atmospheric pressure. Water is 10 raised to minus 10, hydrogen is 10 raised to minus 10, CO2 minus 11, carbon monoxide minus 11, and methane is minus. These are the major constituents which you have to reduce. Now, when you start a vacuum pump, many of the species get evacuated, but there are some dominant species which always there at a lower pressure, especially water and hydrogen. So these residual species has to be removed. Now, if you don't remove, what happens is vacuum the phase noise gets involved. So there are actually beam refraction due to gas density fluctuation. Then there happens a acoustic noise transmitted to mirrors, and sometimes you have a absorption, that is monolayers are formed on the mirror. Now mirrors are huge, 40 kilogram in size, and they actually have their own coating. Now if you don't properly remove many of the residual species from it, what happens is laser pushes these residual species, and they actually stick on the mirror surface. Now, when they stick on the mirror surface, there is an absorption loss which happens, and that actually deforms the mirror also, which actually destroys the functional aspect of the LIGO interferometer. Now, there is other problems also, because laser for a LIGO interferometer, they have their energy is around not the power is around 200 watts starting power, but when it circulates within the cavity, the power goes to around 800 kilowatt to 1 megawatt. Now, when this happens, what is happening is there can be a scattering loss also. Now, when there is a scattering loss, the functional aspect of the sensitive LIGO detector get destroyed. So, vacuum becomes a very important role. Vacuum plays a very important role as far as this LIGO interferometer is concerned. So, how to reach this designated vacuum level? There are a lot of process which goes on in defining how to reach 10 raised to minus 9 millibar. We use certain number of pumps, and these are all pumps which doesn't contaminate the system. So there are good pumps, but they excessively release hydrocarbons, which is not a good signature for as far as the vacuum is concerned. So we use dry pumps, which can be rotary pumps, thermomolecular pumps, ion pumps. But in the final running, we use pumps which are not mechanical in nature. So these are the ion pumps which we use, and we have cryo pumps also in line. Cryo pump actually traps a water molecule. Now, how do you select the material? All the materials which has been, all the chambers are made of stainless steel. And the one thing which you take care is the outgassing rate from the material. Now we have at IPR an outgassing facility which actually measures the outgassing rate of steel coupons. So our outgassing rate is prescribed as 10 raised to minus 14 millibar liter per second per centimeter square. So anything less than it will compromise the pressure value. Now, how to attain this low outgassing rate is we go for air baking of the steel, which is actually air baking to 440 degrees centigrade for 36 hours. Then after it is done, we clean it, fabricate it. After fabrication also we clean it, and then the ultimate cleaning is carried out by steam cleaning. So once the steam cleaning is carried out, there is a visual inspection. Once it gets dried, there is a UV light which we shine, and we go through all the chambers properly and see that if there is any residual particle. If there is a residual particle, again the whole process of cleaning takes place. So this is one of the, there are few things which is not mentioned here, but every aspect of it has to be taken care. Otherwise, getting vacuum is a difficult task. Now, once it is fabricated and installed, we we evacuate it, but during the evacuation process there is baking also that takes place. Now baking is actually, we call it as a vacuum baking. So we don't put the chamber into a vacuum, but what happens is when it is evacuated, we bake it. So this baking happens at 150 degrees centigrade. That also for 36 to 48 hours, and this is how we stage by stage, with multiple baking, we achieve the minus 9 pressure. So here you can see that this is called the LI Vista facility, which is designed in IPR. now installed in IPR. And now again, the one more thing which I would highlight is, so when we fabricated BSE, when we fabricated HAM, and when we fabricated this LI Vista facility as well as the cryopump, there was always a problem with the industry whether they would be able to fabricate such a huge thing. Now, this actually shows that Indian industry is capable of fabricating whatever is a requirement for LIGO India. And you can see over here that we have done a multiple baking of this particular facility, LI Vista, and we have achieved around 5 into 10 raised to minus 9 millibar as vacuum inside this chamber. Now that is an achievement, and now we are going further to achieve less than 1 into 10 raised to minus 9 in this particular chamber. This is a 1:1 prototype, and the lists are long. So the key values which are expected is, the goal is to get all these partial pressures, minus 10, minus 11 for the residual species. LIGO has achieved, these are some of the numbers which you see on the table. And of course, once it is installed, you have the helium leak testing, which is an individual leak testing as well as a global helium leak testing. This is some of the results which we have got from RGA. RGA is a residual gas analyzer which actually maps all the species which are in the range of 1 to 100 AMUs and say that how much is the pressure, how much is the partial pressure within the chamber. So this is one of the plots which we have got from the LI Vista facility. And ultimately, what we have to get is this. So you can see over here the spectral density plot where this color, there's a brown color, is a total noise level or the sensitivity of the detector which is expected, and all the other things are the noise feature. They are integrated, and this is the final one final graph which you see. And if you see over here, this orange one is a residual phase noise which is because of vacuum. So as minimum as you can keep the vacuum, the better result you will get. To summarize my talk is, pressure plays an important role in sensitivity. Experiment shows the sensitivity affects by a factor of 2 if the pressure varies by 2 to 3 order. Total noise sensitivity is coupling of all noises in the interferometer. A minimum pressure less than 10 raised to minus 9 millibar of residual species to be maintained to improve interferometer sensitivity. More to achieve. This is the eagle's eye view of LIGO India detector. And there are 4 nodal institutes which participate in building this detector. One is RRCAT, another is IPR, IUCA, and DCSEM, which actually have their own importance in this building of this LIGO India detector. LIGO India will be in Hingoli, and I am part of this LIGO IPR team headed by Professor Mukherjee, and we are working hard to get this less than 1 into 10 raised to minus 9 millibar vacuum in our LI Vista facility. Thanks.
So the session is open for questions.
Yes.
Sir, as we say, gravitational wave stretches space-time.
Yes.
So the light passing through it will also get stretched?
No. Light won't get stretched, but light gets distorted because the space-time is distorted. So if you look at the fabric of space-time, if it is not distorted by this mass, it will go straight. But if it is distorted, it will bend.
So would you like to comment on this?
No, I think he
Yes, he answered.
I hope you understood.
Anyone else?
Can I ask you a question?
Yes, sir, please.
It was very nice talk. So I'm curious, how will you manage building all the things in there and then transporting to LIGO site or?
Yes. As far as the what you say decision is being concerned, not yet decided how it will be taken care. But we would feel that we will always expect that it happens everything on site, because then the transport will be easier.
Yeah, and also during transport, some things might get distorted, right? You make so much care.
we have, if you have listened to Tarun Savandeep's talk, he has mentioned that manufactured a few chambers in Bangalore, and then we shifted all the way to RRCAT. So that's around more than 1,000 kilometers away.
Those are little smaller, right?
No, these are big chambers. These are 1:1 chambers. So exactly the as big as whatever you see in the LIGO. So what we did is we pressurized the whole chamber with nitrogen. So just to see that this deformation doesn't happen, and there is no contamination also because of extreme weather conditions. And this happened somewhere in during August or June, July, August, during the COVID times. We actually participated. We completed this during the COVID time, so that there was no interference, and the factory was free. There were laborers over there. We, myself and my colleague, we both were stationed at bank. During COVID. We were able to we were able to do that. Totally, we
Sunil, I have a question. Hello.
Yes.
Yeah, yeah, sir. Please.
Yeah. Hi, this is Anand here.
Yes.
So Sunil, can you show that plot where you show the noise PSD?
This one?
Yes, yeah, this one. So I understand that lack of vacuum would lead to some residual gas, right? And there will be scattering, and that leads to this kind of a noise, right? So is it easy to understand how it is related to frequency?
This is actually one of the plots which I have taken from
Yesterday, Gabriel was discussing
one of
this.
the literature.
Yeah.
So I haven't gone extensively into how to determine all this. This is just to highlight that one of the noise feature is the residual gas, presence of residual gas species,
right?
Which actually you see in the gas noise, the color.
Right.
So it is just a representation. So
Yeah, I understand.
I don't know.
I think Suresh has a comment. Yeah, thanks.
Yeah, it contributes quite directly, basically because you see, we measure gravitational waves by looking at the phase delay of wave fronts which arrive in the dark port from the two arms.
Right.
And these density variations or scattering of light essentially adds phase noise to the wavefront.
Yeah, I understand that. What I'm trying to understand is how does it why is it a broadband feature?
Because the distribution of density fluctuations is broadband.
Okay, maybe I'll take it offline sometime with you. Thank you.
Okay.
This is just a representation, just to show that how it affects. It may not be an actual actual scenario. Maybe actual scenario might be better than this, but this is just a representation to show
the so-called gas noise.
Yes.
You see in the plot, no, there is something called gas noise. It's an estimated quantity in the noise budget. On the bottom.
Yes, I see that. Yes.
Orange color.
The orange curve.
Yes.
Your orange is my yellow, but
right. Yeah, okay. Thanks.
So, it's okay.
Is it done, sir?
Yeah, please proceed.
Okay. So thank you very much again, Dr. Sunil. Now we have Ma'am Archana with us.
So shall I come out?
Yeah. Ma'am, now I invite you to continue with.
Okay, yeah, I see. So our next speaker is Dr. Suresh. Who is speaking next? I think I missed.
Yes, Dr. Suresh is speaking, ma'am.
Okay, fine. Yeah,
Dr. Sunil.
yeah. Right. So, yeah, it's my pleasure to welcome Dr. Suresh Doravadi, who is again a member from the LIGO India team from Ayuka. So we just heard from Dr. Sunil, and Ayuka is one of the four core institutes of LIGO India. Suresh has wide expertise, starting from he has worked on ultra high vacuum, some expertise on that, as well as controls and data acquisitions. And he has been working on gravity related experiments, namely testing equivalence principle, as well as he has experience working in LIGO, US. So let's welcome Dr. Suresh to give his talk.
Thanks, Archana. Thanks for a generous introduction. And thanks again to the organizers, Professor Sharma, and glad to be able to address the students and faculty at University, Jaipur National University. Let me see if I can share my screen. Okay. Can you see my screen? Or do I need to maximize this?
Yeah, I think that would be a good idea if you maximize, but you can see the screen.
Okay. How do I maximize this?
So you can turn on slide view.
Or press F5.
F5. Yeah, but that's in Windows and mine is a Mac. So let me maximize this. Should be in
You can
view.
see their slideshow, right? I don't know whether.
Yeah, slideshow I pressed, but it doesn't seem to do what I expect.
So
I am full screen just now.
Right. So Suresh?
Yes, I can continue, I think. Maybe it's...
No, wait. So go to view right on the top.
Yeah.
And click on slide only.
Slide only. You mean in
on Keynote?
No, well, I'm not on Keynote.
Oh, you're not on Keynote. All bets are off.
I'm presenting from an iMac, but this is Windows.
I think it's right. I think we can proceed with this, right? I mean, it looks clear. Yeah.
It's curious. Anyway, yeah. So today, what I would focus on is it doesn't change slides. No, I think I know what is going on. I need to switch to my. Okay. Now it changed slides for you?
Yes.
Okay. Starting from the morning, several speakers have already spoken about several of the topics which are the introduction to gravitational waves and things like that. So they've made my job easier. And so it gives us a little bit more time to talk about some technical details if time permits. I think what I will focus in this talk on is how to detect gravitational waves and how do gravitational waves affect an interferometer and how is that effect detected in the interferometer. I would also then towards the end of the talk speak about our attempts to build a community in India which has the skill set for building LIGO India and operating LIGO India detector. So that will be the main thrust of my talk. First, how to detect gravitational waves, and then how do we prepare ourselves to build a detector and run it. Gravitational waves, as you have heard, are ripples in space-time. They are fundamentally different from electromagnetic waves because these are actually electromagnetic waves travel through space, but gravitational waves are actually fluctuations in space itself. That's the fundamental difference between the two. And sometimes it is difficult to imagine a fluctuating space or ripples in space. The origins of that concept is within Einstein's theory that space-time is a flexible, I hesitate to call it a fabric because it's not a two-dimensional object. So it's more like a sponge or a jello. It's a flexible three-dimensional object which can compress and expand. So in a two-dimensional representation, a collision of two black holes is visualized in this fashion. Initially, the black holes are far apart. They're orbiting each other. And beneath, we have shown the space as a two-dimensional fabric in this case. The way gravitational waves generated in this phase are called, this is called the in-spiral phase, when there is a smooth sinusoidal wave which is gradually increasing in frequency. As they come closer to each other, this in-spiral phase moves into a very rapid, the orbital frequency increases, the orbital period decreases, and we get this increasing frequency, which we call a chirp. And at this point, the two black holes merge, and we call this the merger. And after merger, there's a ring down. So in the case of collisions, the evolution of the gravitational wave signal clearly has three domains. One is the in-spiral, merger, and second is merger, and third is ring down. But remember that this is a three-dimensional event. So let me show you another video in which this two-dimensional representation is replaced with a three-dimensional representation. And this time, I would like you to pay attention to, let us see, the video has to start. Why is it not starting? Okay, so here we have two black holes, but we are deep inside the space-time region which is simulated. Now we have zoomed out, and I would like to pause the video here to draw your attention to these three or four gray disks which are here. These gray disks are, let us say, a flexible circular mass that is kept there. And this mass is a flexible one, it's not a rigid mass. So as the gravitational waves go past this particular circular mass, the shape of the circular mass changes. And the nature of the way this distortion occurs is something which is related to where that mass is placed with respect to the orbiting black holes. So this one which is closer to us here will oscillate in a different... So here you see two planes. The one where my mouse is presently is the equatorial plane in which the two masses are orbiting. The one on the top is the axial plane, which is the polar region of this thing. And these two distortions are different. Okay, the gravitational mass waves have arrived at these masses. And here you'll see that there is an ellipse which is slowly rotating. Whereas I don't quite understand. Okay, maybe my computer is just slow. It just pauses for some reason. I give up. Let's go to the next slide. Basically, we have to understand that in the equatorial region, the distortions are different from the polar regions. And so the orientation of the plane of the orbital plane with respect to us changes the nature of the gravitational wave that is received by us. The okay. Does it now have a full screen?
Yes.
Okay. Now let me see if this works. Yes, it works better this way. I was trying to manipulate the image.
Sir,
yes,
I can suggest, please don't click in between. First, let it finish.
Okay.
Then, if we can pause, then try again. First, complete. Let it complete.
Okay.
Thanks.
It's taking time to load this time.
थोड़ा डिले भी है आपके उधर से जो दिख रहा है उसमें और हमारे को जो दिख रहा है उसमें.
अच्छा. Okay, maybe I'll restart it this time. Okay, I will not touch anything.
Yes.
Yeah, so here we see the black holes. We zoom out in this simulation and then pay attention to the gray disks. Now you can see the disk on the top is rotating, while the disks in the equatorial plane, they will be oscillating. It stopped again. I've never had this happen before whenever I've done this. This is the first time.
If you have this video at separate place also?
But it is a very large file.
So, but you just go to that video and show us that video separately.
Yeah, I can do that.
Down this PPT and show us that video.
Do we have time? Because it will take me a little
time. You can. If it is so interesting and important, we have all of the time with you.
Okay. I'm not sure I can find this video. Maybe I'll show it in the end after I finish my talk. For the moment, just notice that the distortion of the wavefronts are different in the orbital plane versus the polar plane. Now, this particular video talks about shows the nature of propagation of the wave, gravitational waves. The arrow here is designating the direction of propagation, while the rings, each of these rings is the distortion of the space in a plane perpendicular to the direction of propagation. You can find all these videos in the references which are below the picture. None of these are prepared by me. I've taken it from others. So I have... okay. So a simple Michelson interferometer, which is naturally suited towards detecting gravitational waves. Imagine that this mirror and this beam splitter form three suspended masses, which are like markers in space, which are looking at the major axis and minor axis of this ellipse. And the distortion of this ellipse would essentially lead to a change in this arm length versus this arm length. This is what is shown here on the right-hand side as an animation. the light from the laser passes to the two mirrors. When the gravitational wave passes by, the distortion of the ellipse changes these two the end mirrors. So here is a light beam which splits in the beam splitter into two parts. Each of the beams goes to the end, returns to the beam splitter. This is a standard Michelson. And then we have what we call destructive and constructive interference in this region, which is called the dark port. So in the dark port, the oscillation of the mirrors would lead to the oscillation of these mirrors would lead to fluctuating intensity of light landing on the detector in the dark port. That detection, the detection of that light in the dark port leads to a detection of a gravitational wave. This is how the detector works in a very simplified fashion. All the rest of the technological advances we do are essentially to enhance this effect and increase the amount of fluctuating light that we can observe in the dark port, and to minimize the noise in the detector, because there will be other reasons due to which light may fluctuate in the dark port, and we try our very best to reduce that. To reduce that to reduce those noise effects. Using such detectors, we have other speakers have also mentioned that. Okay, I think there's one thing. So here we are talking about the motion of these mirrors, and the amount of the motion of these mirrors is extremely small. For a typical source, this has been estimated at something like 10 to the minus 18 meters, which is an extraordinarily small distance, which is hard for most of us to imagine. Such a detection was the first detection due to which that was the first detection, and these are the Nobel Prize winners, the pioneers of this field. I should also mention that there was one more pioneer who unfortunately passed away a few months before this Nobel Prize was awarded. His name was Ron Drewer, who was also a crucial member in inventing much of this technology for suspended interferometers. You've seen pictures of these vast interferometers before. I'll skip this. So we have also seen that we have not merely these two detectors in LIGO and Hanford, we also have detectors in other parts of the world. Presently, we have them in Europe, and Kagra and LIGO India are expected to join soon. This and also if Australia's proposals come across, so there will be another detector in Australia as well. Presently, it's in a proposal stage. So we'll have a global network of detectors. And the reason why we want a global network of detectors is because we would like to do sky localization. I would like to spend a few minutes on the detection process itself, like what are all the various things that we have to do to detect gravitational waves. The various activities are what we call source modeling. We have to know how these gravitational waves arise. So we have sources like black holes or cosmological sources, which several of our speakers, Patrick spoke about it. So we model sources to understand what is the nature of the signal that is developed. These signals then propagate through space and arrive at the detector. And at the detector, they are converted into something like a voltage signal, which then is recorded and analyzed. The detectors are typically suspended interferometers. And we will talk a little bit more about the detection details of the detectors. But once a signal is detected, we undertake an activity called data analysis. This is an enormous activity computationally. It's so the templates that are generated in the source modeling are used, and we look for those template. When I say a template, we are talking about a typical expected signal in the detector in case there is a particular kind of a source. And we look for those templates in this, it's called a template search algorithm. There are also other algorithms. So a huge number of pipelines that are used to analyze this data. Simultaneously, there are also other parts of the astronomical community that are involved. So we supply to them what is called a low latency trigger. Low latency refers to as soon as possible, we let people know that we have detected a possible gravitational wave event. And we tell them where approximately in the sky it is to the best of our ability to localize that event in the sky. And then whoever has a free telescope which is capable of looking at that patch of the sky, they would like to turn it and look at it and see if there is a electromagnetic counterpart to that detection. And this, so these two things go in tandem. People turn as many telescopes as possible towards this event and try to look for a electromagnetic counterpart. If it is too far away, or if it's a black hole pair, then the chances of detecting something in an electromagnetic domain is small. If it is a neutron star black hole event, or a neutron star event, and if it is relatively close by and bright enough, then the chances are quite high that we would detect it. Unfortunately, we have so far had only one such event which has been observed in both gravitational waves and electromagnetic waves. But we hope to continue to observe and add on to the statistics of that. So these two pathways put together, the gravitational wave analysis and the electromagnetic analysis, together form what we call a multi-messenger astronomy, which tells us a great deal of information about the nature of the sources and the physics of whatever is happening in that part of the space. Now, let me switch gears to focus on the main topic of my talk, which is how do gravitational wave detectors achieve their extraordinary sensitivity. As Sunil mentioned, there are a large number of optics in the LIGO detector. And after the initial portion, after the laser has been stabilized and the light goes into the detector, every optic between the laser and the final photodetector almost all of the optics are suspended. So it's not just the core optics that are suspended. Almost every optic, the input mode cleaner, the power recycling mirror, the beam splitter, all the optics are suspended. Some are suspended with quadruple suspensions. Some are suspended with single stage suspensions, depending on how susceptible the detector is to noise injected at that particular optic. So the simple Michelson, which used to be, so I draw your attention again to this picture on the top right, which is a reminder of the fact that we started talking about a simple Michelson, and the distortion of that ellipse formed by these three masses, the beam splitter, EMY is the end test mass in the y direction, and EMX is the end test mass in the x direction. You can see that part of it is once again reflected in this portion of the detector, the beam splitter and the two end test masses. That is still the core of the detector. This portion is now the dark port, which is this one where the PD used to be there. And this portion is called the bright port, where the light actually returns to the laser if we allow it. But instead, we put what is called a power recycling mirror here, and we stop the light from going back into the laser. We use that to enhance, we push the light back into the detector and enhance the power trapped inside the detector so that we have a better detection in the dark port. The technology of the laser interferometers has been under development for more than 4 decades. So it's a very sophisticated piece of technology. We have, in almost every piece of technology we put into LIGO, we do the best that we can. When I say we, I don't mean us LIGO group, I mean the entire humanity. There is no technology that we have not exhausted in order to build this detector. We have hit the limits of our known technology, and any improvement in the detector depends upon discovering new technology. we have to push the envelope of technology in order to make advancements in this field. And that's an exciting front where young people can contribute, because you're fresh minds, you can take a new look at things and and push the frontier of sensing technology, of vacuum technology, of every technology that is used in LIGO. For example, you see these mirrors here. These mirrors are about 40 centimeters in diameter, and they are polished to 1 nanometer in RMS. 1 nanometer is 10 hydrogen atoms. That means the variation of thickness of this surface, or the height of this surface from the mean surface figure that they're supposed to have, is just 10 hydrogen atoms tall across the entire 40 centimeters. That's the kind of polishing technology that is available with only one company in the world, and the customers are only gravitational wave detectors. Nobody else wants it. Nobody else needs it. So much of the technology developed for LIGO is somewhat like that. We are the only customers, and there will be just one company in the world which can do it, and we push the technology to develop those companies. In India also, at the moment, if you ask for a company which can build the vacuum chambers we want, there is no such company. Nobody has the experience to do it. So they have to do the prototyping, they have to learn to do it, they have to look at what was done before and develop the technology within India to build these vacuum chambers. So it pushes the growth of industry in every country. This is, if you ask why is America so successful at building fantastic machines, it is because they have invested in this kind of technology in the past, and their engineers are capable of doing this. Now, how do we achieve these extraordinary displacements of 10 to the minus 18 meters and so on in a quadruple suspension? The suspensions, so on this plot here, what we have written here on the y-axis is called isolation, which means if the ground shakes a certain amount, what fraction of that motion is transferred to the suspended mass. In the case of a single pendulum, the suspensions provide an attenuation of ground motion, that is the ratio of what happens to the mirror divided by what is happening on the ground. That is this ratio which is there on the y-axis. On the x-axis, it's a frequency. Different frequencies of excitation of the ground can penetrate into the mirror with different attenuation factors. Typically, at frequencies higher than the resonance of the suspension, the suppression of the mirror motion goes as 1 over frequency squared for one stage of the suspension. Since we have quadruple suspensions, the curve which is relevant to us is the bottommost curve, which goes as 1 over f to the 8, where f is the frequency from the fundamental, typically like the 100 hertz here. So from the highest frequency mode, which in this case is like 3 hertz or 4 hertz. So as you go to higher frequencies from 4 hertz, the attenuation gets better and better. The mirror motion compared to the ground motion now is at 10 to the minus 13 meters at 100 hertz, or 10 to the minus 15 meters at 100 hertz. Sorry, 15 as a factor. So if the ground moves by, let's say, 10 to the minus 6 meters, at 100 hertz, the mirror motion is less than 10 to the minus 21 meters. Of course, there are other noises which will come into play at that point of time. But if we can push the motion of the mirror to less than 10 to the minus 18 meters, we're already done. And this is how we achieve that. The interferometer itself, on the top left, I've once again shown you the simple Michelson. But as the interferometer is built up to its final configuration, the power in the arms increases. So a simple Michelson with arm cavities without the power recycling and signal recycling has a certain degree of sensitivity. As we put in the power recycling mirror, the light gets pushed back into the interferometer and the power in the arms increases. That means the light that leaks from the arms into the photodiode at the bottom will be proportionately larger when the arms are unbalanced, when there is a change in the length of the arms. And finally, the signal recycling cavity is introduced to change the frequency response of the detector. So it becomes a broadband detector. Without a signal recycling mirror, it is a relatively smaller band detector. So the sensitivity curves change. So far we have been talking about the signal that is generated in the photodetector. Let's talk about the noise in the noise in the interferometer. The signal that is received in the dark port is affected by many things in the detector. Primarily, for example, the mirrors being shaken by seismic effects or thermal effects or any other effect which shakes the mirror. In addition, when the laser light passes through vacuum, even though we think it is vacuum, there could be residual gas, and the random density fluctuations within this gas, or I guess it's the density fluctuations, and they can act. Even individual molecules passing through through the beam will scatter a certain amount of light out of it, and that can introduce a phase noise into this. And eventually, when the beams reach the dark port and they recombine, we may have a small fluctuation of light in the dark port because of that, because of the gas in the beam. So this is the reason why the vacuum system is so important, which Sunil mentioned to you. There is also other esoteric noise sources which we generally encounter only in textbooks, such as the short noise. These are the fluctuations of light because of its particulate nature. Then we encounter something called zero-point energy fluctuations of quantum nature. They're called vacuum state fields. These also are affecting us. So we typically, the kind of noise sources, we classify them into two parts. One is called technical noise sources, such as frequency fluctuations or intensity fluctuations, gas in the vacuum chamber. These are technical noise sources. There are, however, also fundamental noise sources such as photon short noise and vacuum fields and thermal noise of the mirrors and so on. So these are much harder to to reduce and get across than the technical noise sources, which one presumes one can do something about. One of the techniques we use to identify which is the dominant noise source which is preventing us from making better measurements is what we call a noise budget. Noise budget is a frequency domain plot. It's a spectrum of noise, and different kinds of sources contribute noise in different parts of the sensitivity band of LIGO. You can see the reference here on the bottom right. You can get this particular plot from there, and the analysis of this plot is given. It's a regular activity that goes on every day in LIGO to figure out where we are affected by noise and how to get the better of it. A long list of noise sources are listed here. We can go back to this if people are interested. Now let me switch gears again to see about this multi-messenger astronomy. I think several people have spoken about it. This particular event has been an extraordinarily good fortune for us to have this event detected so soon in our observation runs. It occurred quite early, 2017, and we have not seen one since. So it's a relatively rare event. So we are lucky to get it early. And this is a neutron star merger. Every gravitational wave event is given a name based on the date on which it was detected. This is a gravitational event in 2017, August 17. So GW 170817. It's an extremely well-studied event because we have information in both the gravitational wave as well as in the electromagnetic spectrum. You can see here the electromagnetic spectral observations of this particular event. They span the entire radio, infrared, optical, UV, X-ray, gamma ray, and gravitational waves. So each of these bands, which were different optical telescopes, X-ray telescopes, UV telescopes, were all used by the astronomical community to identify and observe this source after the trigger was distributed to them from the gravitational wave detectors. And this is the new domain. It's it's a new branch of astronomy that has essentially started with the rise of the gravitational wave detectors. It is similar in terms of a revolution that has occurred in gravitational in astronomy. This is similar to radio astronomy, the discovery of radio telescopes or the discovery of gamma ray telescopes. It is of that class where we have essentially figured out a new way to look at the universe, and then we are seeing things which we have never seen before. We have spoken about the stellar graveyard, as people like to call it. We have now doubled the number of observations where we have seen various classes. So let me point out some classes here. For example, I think all these blue dots are black hole mergers. Then you have these, so there are black holes which we only see in gravitational waves. Then there are things called electromagnetic black holes, which I think could be seen in by electromagnetic observations like X-ray emission or something, and then we know that they have merged to form a black hole. Then we have electromagnetic neutron stars. These neutron stars, we have seen these neutron stars in the sense we have seen them in gravitational waves, but of course we have not, I think, seen them in electromagnetic domain. But once we have these neutron stars merge, the resultant could be a black hole which has entered the regime of, on the left-hand side you see the mass of these black holes or compact bodies in solar masses. So we have some which are in the one solar mass domain, which are typically neutron stars, and then we have slightly heavier, which are there is some doubt sometimes as to whether they are neutron stars or black holes. So this was a big question sometime. What is the heaviest neutron star that could exist before it collapses to a black hole? This has also been an active field of research driven by gravitational wave observations. Nor did we suspect that there were 160 solar masses before gravitational waves were discovered. We thought most, because all that could be seen were in the electromagnetic domain, and there were not much more than 10 or 20 solar masses. So the spectrum of solar masses has increased significantly. So the spectrum of black hole masses has increased significantly since the gravitational waves were detected. We are seeing black holes which we never suspected. Now, we have so far focused solely on ground-based detectors, but several other speakers have mentioned that we have other ways to detect gravitational waves in different frequency bands. And since other speakers have touched upon it, I don't need to go back to this. But we are having the terrestrial detectors are on the far right, and the longest period detectors are the CMB polarization. They are almost frozen into space. So we see them as an image in the polarization of space. In between, we have LISA, and then there's something called decihertz detectors, which are between LISA and the terrestrial detectors. Among the space-based detectors, there's the pulsar timing arrays. On the terrestrial detectors also, we have a plan, we have a roadmap going all the way to 2035, where we have a series of detectors of greater sensitivity which are planned. Currently, for example, we are close to 2022, which is this blue curve here. The blue curve is called the advanced LIGO design, and its sensitivity is a little better than 10 to the minus 23 in strain. But presently in 2024 to 2026, we will upgrade this detector to something called Advanced LIGO Plus, which will have better sensitivity. Beyond that, as for up to Advanced LIGO Plus, that is A+, it is an approved program, it's a funded program, we are going to do it. Beyond that, the proposals are at the moment being drawn up and being considered by the governments. We have Voyager, Einstein Telescope, and Cosmic Explorer. Voyager and Cosmic Explorer are primarily proposed in the United States, and Einstein Telescope is a European proposal. the Einstein telescope is well on its way. Actually, it is going through several prototypes at present, and it will soon. The timeline is 2035. It's on a much more stable ground in terms of proposals and funding. Cosmic Explorer is yet to be, I think, proposed to the government and being considered by the US government. So one of the things I would like to point out here is that it takes a long time for these detectors to be proposed and built. Typically, the time scale is like 15 years. Present advanced LIGO was proposed in early 2000s. The designs of this were, they started designing it in early 2000, 2002, 2003. We see papers on advanced LIGO coming up. The proposal was put in place and funded from 2008 onwards. It was completed in 2015. So it's roughly a 15-year timescale just to complete the installation of an upgraded detector. So that's the reason why we are talking about a detector in 2035. We started talking about this in 2010. So by 2035, we hope to have a detector. It may slip a little bit because a lot of technology that is necessary for this detector needs to be still developed. Now, what is the use of these detectors? Very often students would ask, how far can we see with this detector? Well, on the right-hand side, we have compared various detectors and how far we can see. If you see these numbers, 0.1, 1, 10, and 100, they're in the units of redshift. At cosmological scales, it is easier to express this in redshift. Z redshift is symbolically indicated by Z. Z of 1 is about 10.8 billion light years. So this 1 here is 10.8 billion light years if we are sitting in the center of this sphere. And on this blue curve here is the present detector which we are using. This is the A+, so it has a slightly longer range, but it still doesn't, this about barely reaches 0.1, between 0.1 and 1, a Z of 0.1 or 1. And these dots here are of different kinds. The yellow ones are neutron star collisions. The black ones are white, black hole collisions are indicated in white here. So now, if you want to have a significant number of neutron star collision detections, we can see here that our A+ is also not going to do it. To actually see significant number of neutron star collisions, we will have to have either a Voyager, which will just begin to sample it, and Einstein telescope and Cosmic Explorer will definitely encompass much of what we can see. These will go up to a redshift of almost 100 when it comes to black hole collisions. So the bigger detectors allow you to see much farther into space and also see almost all the possible gravitating events in the space. Sunil has spoken about, I'm shifting gears again to LIGO India, and the organization of LIGO India is the task of building the detector is divided into 4 parts, among 4 institutions. We can talk about which institution does what, but Sunil has spoken about it already, so I'll skip this. This also has been mentioned. The chief advantage of LIGO India is in the pointing ability of the entire network. So when we take the network together, we can point to the location of a source much more precisely. This allows other telescopes to point into the same location. So this enables multi-messenger astronomy and a greater depth of study that we can do on the objects. Okay, so now how do we build these wonderful detectors? We need people to build this and operate it in India. So we have a LIGO India training program, which is overseen at IUCA, which is one of the tasks of IUCA is to build this team called the commissioning team. The job of a commissioning team is to take the installed detector up to the sensitivity at which it is supposed to work. And it's a long path to take the detector, fix all the problems in it, and make it work as it should. The very first level of this training program is accessible to college students, And we regularly take master's students and bachelor students who are interested in working in this field and give them the necessary training to put them into a career path in this direction. So you can contact our education and public outreach team, or you can write to us at IUCA for more details. Basically, we take you through a training program involving all the basic technologies of LIGO India, the suspensions, seismic isolation, laser stabilization, control systems, noise hunting. So the focus is on training people to analyze the noise in a detector, understand where the noise is coming from, troubleshoot the detector, and fix the problems. That is the general activity. But to train somebody to do that, you need some equipment. And in building that equipment, we understand a lot about how noise propagates in the system. So we have a suspension training module. We have a seismic isolation training module. We also develop seismometers. There's a laser stabilization training module, which at the undergrad level, they are accessible without vacuum systems, without clean rooms, or without infrared lasers. So the primary requirement of level 1 is that it does not have high-tech stuff, which is very expensive. So this is a proof of concept, conceptual level development. Level 2 has details of exactly, it's a transition from a normal laboratory to a LIGO laboratory. So we have to pick up the additional technical skills that are necessary to work in an observatory. So that's what the level 2 does. So if you plan to stay in this field for longer and want to work on the observatory, then you need the additional skills. Otherwise, at the college level, the conceptual understanding can be imparted without the overheads of ultra-high vacuum, high-power lasers, and clean rooms. And subsequently, if you stay with us longer and plan a career with us, then we would send you to the observatories or the prototypes to pick up the necessary skills to work on the observatory floor itself. Because just knowing the technology is not enough. There is a culture of working in a very large group in a very sophisticated place. It's like operating a battleship. Just because you know how to swim, you can't get on a battleship. So it requires a discipline to work in that, and all that requires considerable training. So you can see that the bottom, it typically takes, each stage takes roughly 1 year or 6 months. So the total program is like 3 to 4 years. What I would like to also point out at this stage is that I think Saurabh Salunke had also mentioned, and Tarun also had mentioned, that students may wonder, do I have the skills to contribute to LIGO India? Maybe I'm a chemist, I'm a biologist, can I do something? I think almost every branch of human knowledge has contributed to LIGO or the gravitational wave detectors. So I don't think you need to worry about, do I fit in? I'm a mechanical engineer, where can I contribute? I'm an electronics engineer, where can I contribute? Almost every branch of engineering, every branch of physics, chemistry, and mathematics are used in these extraordinary detectors. So it's a highly interdisciplinary field. Often engineers come to me and they sit in our labs and then they learn some physics. Then MSc students come with a physics background, they sit in the lab and learn some engineering. So it's an interdisciplinary field. Everybody learns a little bit of everybody else's job. And that's how the interferometer was built. So we call them changing hats. Everybody wears multiple hats. This is the present status of our LIGO detector. It is yet to take off, but it's very, very soon. I think we will be placing the orders for building the site, and then we will be able to invite you all to visit and contribute. Thank you.
Thank you, Suresh, for this wonderful talk. Let's see if we have any questions.
Any questions from anyone? I don't think so, ma'am. We may move further.
Okay, so thanks a lot again. So the next speaker is, I think, could you remind me or do you want to take over?
Professor Sudeep Bhattacharya from TIFR. Professor Sudeep Bhattacharya from TIFR will be speaking. He will be speaking on many interactions of neutron stars. Sir, you may start.
Yeah. Let me try to share.
So press the arrow.
Yes, I have already placed that, but
present now. Then you will see the select window or screen share. So entire screen you have to select.
Yes, I'm.
Everyone is giving the email ID. Yeah, that's more than the knowledge.
Yes, I have placed window, but
there you will be seeing a tab of entire screen.
Should I space entire screen?
Yes, entire screen.
Yes.
Entire screen, then share.
But it says can't share your screen.
No. You press entire screen.
And it says can't share your screen. Google Chrome might not have screen recording permission on your computer.
It is
System preference.
No, it is not like that.
One second.
I have worked with Sun for 2 months. Okay. Some kind of, I don't know what this was. It just trained us for like 2 years, 2 weeks, and then gave us the data sets to go. I do have. My name is this. If you can search for it on Google, you'll get everything about it. Yeah, just search this on Google, you'll get everything. Yeah, sure. I would love to.
Professor Sharma. Hello.
Yeah. So meanwhile, we may proceed. Tell us, sir, what are you telling?
I was just saying that while Dr. Sovadeep fixes his computer, I would like to respond to a question which came earlier with Sunil.
Sure.
One of the students asked when the space is stretching and contracting, and we are using light to when we are using light to look at the contraction and stretching, compression of space, is it not true that the light also will stretch and contract? Then how can we see? So the trick is actually in the time duration between the light transit time between the arms and the frequencies that we are observing. We are typically observing frequencies up to about 1 or 2 kilohertz. whereas the light transit time is faster than that. So as far as light is concerned, as the mirrors oscillate, we are taking kind of quick snapshots of the detector at a much faster pace. And that's how it's like we are taking a snapshot every 100 times within the expansion and contraction of the space between the mirrors. So it's a matter of time scale. Actually, light does stretch, and if you go to higher frequencies, when you're observing shorter and shorter frequencies, shorter and shorter time scales, then we will reach a point when the contraction and expansion of space and the round trip of light matches, and then we cannot see anything. So the instrument does have blind spots in the frequency domain.
Oh, great.
Yeah.
So now I think thank you very much, Professor, for clarifying this more. Now we can welcome Dr. Sudeep Bhattacharya from TIFR. Sir.
Yes. Sorry for the delay and some glitch.
No issue.
And good afternoon. And I thank the organizer for inviting me to deliver a talk on neutron stars, which are fascinating objects and among the densest objects of the universe. This talk is kind of an interlude among all the gravitational wave source talks, but this is also very relevant for this event because neutron stars are gravitational wave sources and they are used also to detect gravitational waves. So they are very relevant. So it will be very useful to understand neutron star. I will, however, give a very brief and general talk, mostly for students, as I was told that a large part of the audience would be students. So slide is not changing. Can you see a change slide?
Yes.
All right. Thank you. Yes. So what is the neutron star? This is a neutron star in comparison to a city. And these are some of the properties of these very extreme stars. This is, however, by the way, the city Chicago and Lake Michigan. So neutron star crams a mass worth of or more than a solar mass within a radius of only 10 to 15 kilometers. That is within a city radius. And the core density is 5 to 10 times the nuclear density. And magnetic field can be 10 to the power 7 to 10 to the power 15 Gauss, which cannot be achieved, cannot be produced in terrestrial laboratories. Some of them can also spin very fast, that is several hundred times in a second. So in all these ways, neutron stars are very extreme objects. Another kind of extreme object is black hole, but we should remember that there is a very important difference between neutron stars and black holes. Black holes do not have a hard surface, but neutron stars are like normal objects. They have hard surfaces. Now, how are neutron stars created? The stars are created from giant gas clouds in galaxies, which are called stellar nurseries. Some parts of these clouds collapse to become a star. And if the star is a high mass star, then they burn for about a few million years. And then the outer part of the star is expelled by a very violent explosion, which is called supernova, and the core of the star collapses to become either a neutron star or a black hole. If the core mass is little small, then it will become a neutron star. Otherwise, if it's for very massive core, it will become a black hole. Now, because of these very extreme properties, neutron stars are a unique natural laboratory. Many mysteries of the extreme environments of the universe are hidden in neutron stars, and I'll give some examples. For example, look at this plot carefully. This plot shows the strength of gravity of many kinds of objects of the universe in two ways. Along the x-axis, this is the simple gm by r, where m is the mass of an object and r is its typical size. So this is the gravitational potential, well known to all of us. But we know in general theory of relativity, the effect of gravity is manifested through the curvature of space-time, and a measure of that curvature is in the y-axis, which is gm by r cube. So you can see that many kinds of objects are here. For example, this MW, which is our Milky Way galaxy, it spans a large part of this plot. Then there is this Earth, our Earth, white dwarf WD, main sequence star MS, and at the top right you will see that there is NS, that is neutron star, and both the axes are in log scale. So you can imagine that neutron stars creates a strength of the gravity which is orders of magnitude, many orders of magnitude stronger than the gravity produced by other objects of the universe, apart from stellar mass black holes. Now, neutron star is such a diverse kind of object that there is no branch of physics that cannot be applied to neutron stars. From the center to the surface of a neutron star, which is about 10 to 15 kilometers, the density decreases by 14 orders of magnitude. And therefore, this neutron star study needs the contribution from astrophysics, gravitational physics, nuclear physics, high energy physics, and even solid state physics, because neutron star crust is the strongest known solid in the universe. It is many orders of magnitude stronger than steel, for example. And another very important aspect of fundamental physics, which can be studied by studying neutron star, is the very dense matter, which is 5 to 10 times the density of the atomic nucleus, but still it is degenerate matters, cold matter. It's not the matter created by collision of particles in large hadron collider, for example. This is called degenerate matter. We do not know their properties. This is a fundamental problem of physics and particle physics. We can study them only by observing neutron stars. For example, neutron star, its core could be a bag of, for example, 10 to the power 57 free quarks. We do not know. This is a very fascinating, tantalizing possibility. So we can study these aspects of extreme aspects of physics, fundamental aspect, only by studying neutron stars. How do we observe neutron stars? Because they are not here. They are in the sky. Those are cosmic sources. So we need to observe them. And these are the observational windows. Mostly we observe them through electromagnetic spectrum. And as we know, that electromagnetic spectrum spans from radio to gamma ray, where they are different by their wavelengths or energies. So a radio wavelength could be of the size of a building or humans, while the gamma ray wavelength can be of the size of an atomic nucleus. But we cannot observe this entire cosmic electromagnetic spectrum from here, from the surface of the Earth, because our atmosphere stops a large part of them. For example, gamma ray, X-ray, ultraviolet, etc. cannot penetrate our atmosphere. And that is good for us because that is why we can exist. And you see that visible light can partially, maybe 80% can penetrate through the atmosphere. We can observe them from here. And radio also, there is a big window which we can observe from the surface of the Earth. But for many other wavelength ranges, particularly high energy, gamma ray, X-ray, ultraviolet, to observe them, we need to send our instruments above the atmosphere via satellites. And it is extremely useful, actually essential, to observe the universe, cosmic sources through the entire electromagnetic spectrum, because you can see that this is the sun. Four photos of sun in radio, infrared, optical, and X-rays, they look very different. Not only they look very different, the source of this energy, the physics, underlying physics are very different for different wavelength bands. Therefore, we need to study all the cosmic objects in a broad electromagnetic band from radio to gamma ray. And neutron stars actually emit from radio to gamma rays. They are observed in a wide range of electromagnetic wavelengths, but they were originally discovered in radio wavelengths. And here is a little bit of history. So in 1932, you know that neutron was discovered. Before that, proton and electrons were discovered, but neutron was discovered in 1932. And in the next year itself, these two people, Zwicky and Bade, from the supernova observations, I already mentioned supernovae are basically the explosions of the massive stars at the end of their life. From the supernova observation, these two people predicted there could be a star which could be very small, could be made of neutrons. And on the other hand, around that time is Chandrasekhar, our Chandrasekhar calculated a celebrated limit which said that if a star, collapse of a star is stopped by electron degeneracy pressure, there should be an upper limit of the mass of the star, around 1.4 solar mass or so. But he did not that time say anything about neutrons. But soon after that, Tolman, Oppenheimer, and Volkov, they not only predicted about neutron stars, but also calculated the plausible structures of neutron stars. But then the Second World War started, and this research was almost stopped, and neutron star was not detected. But in 1967, neutron star was detected and was identified as neutron stars. This detection was done in radio by Jocelyn Bell Barnell and her PhD guide, Anthony Huish, and they detected a pulsar. As the pulsar, this is a neutron star here at the center on the left bottom corner, and there is the magnetosphere in green shown, and there are open magnetic field lines through which there are the emission of radiation and particles which create the radio, and those radio beams are rotated around the spin axis of the neutron star. Therefore, we observe them only sporadically or periodically, and that gives rise to the radio pulsations of these neutron stars, and therefore they are called pulsars. So that's how neutron star was detected. But neutron star is not only observed in radio, they are observed in all wavelengths. For example, this is an example of neutron star observed in X-rays. This is the actual image of the Crab Nebula by Chandra. This is a very Chandra satellite. This is a very famous nebula. At the center of it, there is this neutron star. One can see it seen in X-rays. So this neutron star was created only about 1,000 years ago. The supernova happened as we observed from Earth, the supernova happened in 1054 CE or AD, and that supernova was recorded by various astronomers throughout the world. For example, Chinese astronomers. That's why we know the supernova happened that time. And so this is a relatively young pulsar and neutron star. But there can be older pulsars as well. So this is an example of older pulsar, very famous Gevinga pulsar. The ejected mass in the form of supernova has already been dispersed, and the pulsar has left its original place due to a kick at its birth, and it is speeding through the interstellar medium in our galaxy. It is about 10 to the power 5 or 10 to the power 6 years old, and you see that the pulsar wind emitted by this neutron star is hitting the interstellar medium around it and creates a shock which emits X-rays. And these X-rays we can see in this image of Chandra satellite. But these are all isolated neutron stars. Neutron star can also be in binary systems. For example, here, where on the right-hand side at the center of the disk is the neutron star, and left-hand side there is a huge star, and the matter from star through a wind is falling onto the neutron star. And this is called a high mass X-ray binary because these are mostly seen in X-rays. In contrast to this, there could be low mass X-ray binaries where the companion star could be a low mass star and there is no wind, but the matter is still falling onto the neutron star at the center on the right hand side disk. And this disk is emitting, inner part of the disk is emitting X-rays. Now this disk, particularly its inner parts, which is observed in X-rays, can be very useful to probe some of the fundamental aspects of physics. For example, this kind of objects can have an age of more than 1 billion years, and their orbital period is very small. The orbital period of the two stars can be very small, so minutes to days. Neutron star magnetic field for these particular objects can be relatively small, 10 to the power 7 to 10 to the power 9 Gauss. That is why the accreted matter can approach very close to the neutron star. For this case, the disk can approach very close to the neutron star, and therefore they can actually probe like a tool, like an instrument. They can probe the strong gravity region around the neutron star, and that is why these objects are very important to understand some of the fundamental aspects of gravity or accretion or the dense matter. So here is an example, for example. So here you see that at the center, on the left top corner, at the center there is a neutron star in black and the accretion disk around it. So there could be iron in that accreted matter, a small fraction of iron, and there could be atomic transition as shown on the top left corner, atomic transition within the ions, which could create the characteristic iron K alpha line, for example. And since this emitting matter is rotating, and because of the geometry, this narrow iron line, which is narrow in the frame of the emitter, will become broad with respect to the observer, as can be shown on this figure on the right, composite figure on the right, the top panel. It is broadened because of geometry, observing geometry, and because of Doppler effect. And then due to the effect of special relativity, some part of the matter is coming towards the observer and some is going away because it is rotating around the neutron star. Therefore, there will be boosting of some part of the emission and deboosting of some part of the emission. So due to special relativistic effect and with the beaming, this iron line will become asymmetric in the second panel as shown. And then there will be gravitational redshift, there will be transfer Doppler shift due to which the entire line will be shifted. And finally, there will be light bending effect also, which I have not shown here. And finally, there will be line emitted from various annuli of the accretion disk, and we will, of course, cannot see, we will not see them separately because for us it is just a point source. So we will see them all together, and the observed line will look like the lowest panel of the composite figure on the right. So this way, this is a very clean way to measure the general relativistic effects and other properties of the system almost like the textbook. So we can separate out various effects here. It's a very clean system. And then I will give another example of thermonuclear X-ray bursts. The matter is being accreted and accumulating on the surface of the neutron star. This matter accumulates on the surface of the neutron star, and then the condition for thermonuclear burning is satisfied. So the temperature is right, the column density is right. So suddenly this matter will be burned by thermonuclear burning processes, thermonuclear fusion processes, and that will give rise to a burst like this in this figure, intensity versus time figure on the right. So before the burst, there was the X-ray intensity that is shown at the beginning of the plot, and then we show here that the intensity increases rapidly, and as the burning is over, neutron star surface cools down, the intensity, X-ray intensity slowly decreases, as shown in this curve. These thermonuclear bursts, the duration of them is about 10 to 100 seconds, and they are extremely energetic. For example, the energy release in 10 seconds during such a burst is so high that sun takes more than a week to release this energy. So these are very bright events, and this burst is ignited not only, it does not ignite on the entire surface of the neutron star simultaneously, but it ignites at a certain point like this. And the thermonuclear flame spreads, propagates to engulf the entire surface of the neutron star. And the study of this thermonuclear flames propagation, the thermonuclear burst itself, and their various timing spectral properties can be extremely useful to understand the extreme physics of neutron star. Both is core physics, where the density is more than the 5 to 10 times the nuclear density, as well as the physics of the surface, which is itself very important because neutron star has high magnetic field, strong gravity, and so on. So far, I have talked about all the entire electromagnetic spectrum, which can be used to observe neutron stars, but neutron stars can also be observed through gravitational waves, and these figures you must have seen today many times. So this is this figure, famous picture, the cartoon of the of 17 August observed on 17 August of 2017, and it emitted gravitational waves, but because of the merger of two neutron stars, some matter was also ejected, and this source was electromagnetic radiation in a very broad band. So this essentially gave rise to the multi-messenger astronomy. Electromagnetic radiation is one kind of messenger, the traditional messenger, and now a new messenger, gravitational waves. So two messengers which are giving us information about this object. So it essentially gave rise to multi-messenger astronomy. And so therefore, this shows neutron star is so important because it gave rise to a new field as well. But this gravitational wave emission was due to the merger of two neutron stars, where the strength of the gravitational wave is very high. Neutron star, a single neutron star could also emit gravitational waves. So this is a cartoon of a neutron star where z-axis is the spin axis of the neutron star. And since neutron stars are very compact, we expect that the two perpendicular axes perpendicular to the spin axis, that is in the direction of x and y, the radius of neutron stars should be very similar. That is, in one direction radius is a, another direction radius is b, which are the radii in the direction perpendicular to the z-axis. They should be very similar. That's what we expect because it's a very compact star. But if they are even slightly different, and how slightly? The radius of a neutron star is 10 kilometers. Suppose in these two directions, x-axis and y direction, the two radii are different by even 10 micron, we expect that there will be gravitational wave emission because of asymmetric, this rotation of this asymmetric mass distribution. That will be a non-zero mass quadrupole moment. Therefore, there will be the emission of gravitational waves. However, the strength of this wave is expected to be very small, and it has not been detected so far, but there are upper limits. The current instruments, LIGO, etc., have given upper limits, but it is not detected so far, but we hope to detect it soon in the future. I have talked about various aspects of neutron stars. One may say that neutron stars are so far and they're too small, so our interest in neutron star could be entirely academic. But the question is, can they directly affect us? For example, there is sun. So we have academic interest in sun, but sun also directly affects us in many ways. So can neutron stars directly affect us? So I'll give two examples. One is this, the same plot, same cartoon, the merger of two neutron stars. We now believe that the heavy elements, particularly the elements heavier than irons, were mostly created by the mergers of neutron stars. And these heavier elements, originally the constituents of the universe are hydrogen and helium. So the universe originally does not have heavy elements. They are created by various processes, nucleosynthesis and other processes. So the merger of neutron stars can create heavier elements, heavier than irons, and it is believed now, or at least this is one opinion, heavier than irons are possibly by neutron star mergers. And therefore, and we need such elements for our existence. Our body needs it. We need it various ways. So therefore we owe our existence and of course our gold to neutron star mergers. So neutron star is a giver of life that way. It's so important for us. And then I'll give just one example before I complete my talk. The neutron star can also be destroyer of life. Consider this kind of neutron star. This is also a cartoon. But these neutron stars called magnetars, their magnetic field is very high, in the range of 10 to the power 13 to 15 Gauss. This field is many orders of magnitude higher than the magnetic field that can be created in terrestrial laboratories. Many orders of magnitude higher. So this magnetic field is so high that this magnetic field sometimes can fracture the crust of the neutron star. You can see in the figure, it's a cartoon. It can fracture the crust of the neutron star. And like our continents on the Earth or our tectonic plates, these crust could then, they are fractured, they could move them, and magnetic field lines are anchored in those crusts. So you can imagine if those crusts, basically new tectonic plates of neutron stars, when they move, these magnetic field lines is also rearranged. Their structure is changed fundamentally, which we call, in technical language, we call it topology change. So when this topology changes, then the huge amount of energy from such neutron stars can be emitted in a very short time. So these are called magnetar outbursts. And such magnetar outbursts could directly affect us. And I will give one example before I end my talk. So first, with this, assuming that there are many students in the audience, I will talk about first this tsunami, very famous tsunami in 2026, now December of 2004. So the students were, of course, very small that time, and they were not even born, but this was very famous. I hope you can see the video. That an earthquake, a huge earthquake in the region of Indonesia created this tsunami, and these waves in the ocean propagated, and killed many people. For example, in India, it killed many people in Andaman and Tamil Nadu. And this earthquake had an energy of 23,000 Hiroshima type atomic bombs. Now, this earthquake was and tsunami was very famous throughout the world. But there was an astronomical event that happened on the very next day, 27th December 2004, that is known only to the scientists, particularly to astronomers. That is the explosion of a magnetar, SGR 1804-20. The magnetar itself is 50,000 light years away. And possibly its crust slightly moved, its magnetic field topology changed, and there was this huge outburst of energy. That energy propagated this length of this distance of 50,000 light years. And very coincidentally arrived here on Earth on the very next day of the tsunami, on 27 December. The actual incident, of course, happened 50,000 years ago, but it arrived only on 27 December 2004. And if you compare the energy, you will see that the energy of the earthquake is minuscule with respect to the energy involved in this event. This event released an energy in just 0.1 second, which sun releases in 150,000 years. And it's good for us that it is 50,000 light years away. If it were within the 10 light years, then it would severely damage our atmosphere. So the neutron stars are actually important for us, for our existence. It's a giver of life. It can be very dangerous also. It could be destroyer of life. And with this, I will stop. Thank you.
Thank you very much, Professor Bhattacharya. Any questions? So we move forward to next speaker, Professor Anand Sen Gupta from IIT Gandhinagar. Thank you, Professor Bhattacharya. We'll meet again.
So thank you, Professor Sharma. Can I share my screen?
Sure, sir.
Is this visible?
Not yet. Yes, now it is visible.
Okay, so I'd like to thank Professor Sharma and his team for giving me this opportunity to speak at the National Seminar on the Discovery and Detection of Gravitational Waves, organized at Jaipur National University. So the title of my talk is Highlights from the Gravitational Wave Songbook. So by this, what I mean is, hopefully I'll be able to give the attending students and a little peek into the world of gravitational wave astronomy. I mean, how can you leverage these signals that we detect in the LIGO detectors or LIGO-like detectors? What could we learn from these signals so far, and what are the prospects of finding new, or verifying new ideas as we discover more such signals from binary black holes? So before that, of course, Professor Patrick Dasgupta and Professor Deshmukh and other people have comprehensively described what gravitational waves are. But for the purposes of my talk, I would like to have a very brief overview of what we are dealing with here. So I'll go back to Newtonian gravity. Is my mouse pointer visible if I move it around?
Yes, yes.
Okay, thanks. So as you know, Newtonian gravity is described by this Poisson equation, where the matter distribution is related to the Newtonian potential phi, which leads to which leads to, so if you change a rho on the right hand side, if there is a redistribution of matter, then of course instantaneously the gravitational potential changes everywhere in the universe. And this implies that while this theory of gravity is very good at describing low energy events and describing things like the motion of planets, we launch rockets using this equation and so on. It is not consistent with special relativity. It's a non-relativistic theory of gravity. And there are no gravitational waves in Newtonian gravity. So basically, this leads to a new idea. This led to a new idea, which is a geometric theory of gravity, which does not involve any forces, which is Einstein's general relativity. It's a geometric theory of gravity, and I won't go into the details here because Patrick and Professor Deshmukh have covered it so well. I just want to point out to the students that we use general relativity not as an abstraction or a curiosity, but we use it in very, very practical devices. For instance, so what I mean to say is general relativity is much closer than you think. So all the GPS devices that are there in all the smartphones nowadays, they use GPS navigation, and which takes into account the time delays because of the general relativistic correction to the time delays from these GPS satellites as they are received on your phone. So if you do not take into account general relativity, you'd actually make a huge error, and your GPS navigation would not work. So it's a very practical. There are many practical uses of general relativity, and it has passed several observational tests, including the perihelion advance of Mercury, the deflection of light. So, these are very famous pictures of a background quasar that is getting lensed because of the deflection of light from some sort of a mass lens, which is sitting right in front of, in between the object, in this case a quasar, and the observer sitting here on Earth. So you see these Einstein rings, which are very very well known. Not only does Einstein's gravity predict this new phenomena, but it also predicts the existence of black holes. So, for instance, here is a very famous, aggregated picture of, it's a snapshot of the galaxy in the center of our own, the black hole in the center of our own galaxy, and the star field around it. Of course, you cannot see the black hole, but what you can see is that if you take a series of snapshots, you see these stars moving around in a very peculiar fashion around some central object. And when you analyze their motion, you can ascribe it to a central object which is dark but has the mass equivalent of millions of solar masses. So although they are theorized as mathematical objects in the theory of general relativity, they are pretty much very, very real objects. And of course, more recently, we have this very famous picture of the black hole shadow, where the shadow of the nearby galaxy, the black hole present in the nearby galaxy, was imaged using a slew of radio telescopes, and you could make a giant synthetic antenna with which you could observe this. So, but more interestingly for our purposes, general relativity predicts these black holes to go around each other in spiral and then finally merge and generate gravitational waves. So I'm not going to show the entire video. So it's going to start at a very late stage where you see two objects. I'm just going to stop it here for a moment to make a few remarks. So this is the simulation of two black holes One of them is twice as heavy as the other. So one of them is 14 times the mass of a sun. The other one is about 7 solar masses. And these are at a distance of 440 megaparsecs, which to just set it into context, it's 1.4 billion light years ago. And so if you were traveling with the gravitational waves as it was traveling out and reaching the Earth, halfway through you would have seen the dinosaurs actually go extinct. So, and of course, this finally, these two black holes merge, as you can see in this video. It slows down just to show you what happens. And then finally, the resultant black hole, which has a mass of about 21 solar masses, kind of settles down by radiating away all extra degrees of freedom. So this is something that is predicted in the theory of general relativity. And this is exactly what we observed on 14 September, exactly to the day, about 9 years ago. Maybe 10 years ago? No, 9 years ago, right. So this is what we observed in the two detectors. So if you follow the arrow here, so these are the traces of the data that was received in the two advanced LIGO detectors that had just begun operation after going through the advanced LIGO upgrades. And before even we could say hello, we were received by this amazing signal that arrived at these detectors. And you see that, of course, these two sites are geographically separated by quite a long distance. So their noise is completely uncorrelated. But if there is an astrophysical signal, you expect some correlation to happen. And you can see that so the left and right panels are basically the time frequency resolution of the data that was received during this time. So this is a window in time. And if you take the time frequency, if you resolve it in time and frequency, you see all the energy getting dumped along a neat track, which is called the chirp track. And that happens for both the detectors. So this is a telltale signature of a gravitational wave signal. And of course, there were several tests that was done to make sure that we were not seeing something spurious. But nevertheless, this was the first detection of gravitational waves that was observed in the advanced LIGO detectors. Since then, of course, we have several more detectors have started operating. So here is one of the LIGO detectors that has been shown many times before, I think, by several speakers. This is the one at Livingston in Louisiana State in US. Which is a part of the international network of gravitational wave detectors. So this is a 4-kilometer arm, Michelson detector with Fabry-Perot light storage arms. So one study that was done some time ago by Anthony Searle and also my student some time back was to figure out where in the world would you place an additional detector which would give significant advantage to, say, the volume of the universe that was accessible to these sources. And you see that, the details are not important here, but what you see is the volume accessible in a coherent analysis. So you had these two LIGO detectors and a third detector which you could place anywhere in the world. And if the volume accessible was large, then you paint that particular pixel with a lighter color. And you see that this entire Asia Pacific region, western coast of Australia, southern India, maybe Singapore, and certain Southeast Asian countries, Madagascar, surprisingly, this area was very, very well suited for placing an additional detector. And this also sets the context for the LIGO India detector that is coming up in this region, in the state of Maharashtra in India. So the Asia Pacific region was ideally suited for a new detector. And it's not very hard to understand why, because it gives you the longest baseline with which to pinpoint sources in the sky. So here is the network of current ground-based detectors. So here are the two detectors, one in Hanford and the other one in Livingston. There is a detector called Virgo in Europe, Kagra in Japan, and there is this proposed LIGO India detector, which we hope will come up around 2030, maybe. Right. So unlike telescopes or electromagnetic telescopes, the gravitational wave detectors have a nearly omnidirectional antenna pattern. What it means is that imagine there is this gravitational wave detector whose arms are along these, you see these little dimples. So one arm is along, is perpendicular to the dimple here, and the other one here in an L configuration. You see all sources that come from the top or are incident from the top are, it's very hard to pinpoint the source in the sky. So you wouldn't be able to tell whether a gravitational wave came from the bottom or the top. They would be equally sensitive to that. And pretty much the same for any other direction in the sky. So what it means is that with a single detector, although you would be able to record the gravitational wave, it would be impossible to pinpoint this in the sky. So you need a network of detectors, multiple detectors that are geographically located far away from each other, to be able to use a technique known as triangulation to actually pinpoint these sources in the sky. So with the LIGO India detector, which is an Indian mega science project, we would have a network of gravitational detectors for the best possible science. So here is a little work that was done by my project student Sachin Shukla, where you see, so this is the entire sky, and here is a gravitational wave that we have injected, which is denoted by this little star that you cannot see but probably can see in the zoom out. And if you just use two detectors, which is the Livingston and the Hanford detectors, you would localize this on a circle like this within an area of 194 square degrees. So it's a very large area to actually follow it up with electromagnetic telescopes if you detected something interesting. But as soon as you bring in the Virgo detector, you constrain it within this red ellipse, which is about 22 square degrees, which is a sharp, very, very sharp, tack sharp localization. But as soon as you bring in the Indigo or the LIGO India detector, that further reduces by another factor of 2. So now you are able to localize this within this much narrower, error ellipse, which is 9 square degrees in size. So, the punchline here is that LIGO India detector could play a very vital role even at an early stage of commissioning. So, I mean, when a detector is commissioned, as Professor Suresh Doravari has mentioned earlier, that it goes through a series of steps before it is finally up and running. So even in its early commissioning stage, when it is not optimally configured, and it has much less sensitivity than what you would otherwise expect, even then LIGO India detector, although it may not play an important role in the detection of the sources, but if the data is up and running, it could play a very vital role in the localization of these sources. So this one last slide about this. So for instance, if you added an advanced LIGO detector at O4 sensitivity, so with the detector in Aundha, along with the other detectors in the gravitational wave detectors, as I showed you in that network figure, even with with a very modest duty cycle, it could shrink the localization errors by almost a factor of 2. And once it reaches the design sensitivity, which is A+ design sensitivity, even at a 50% duty cycle. So what it means is that the detector is up and running only for 50% of the time. It's a buggy detector. So even then it would reduce the median localization errors by a factor of 2. So from 6.5 degrees square to about 3 degrees square, which is fantastic from the point of view of doing follow-up studies and with electromagnetic observation. So gravitational waves. So this is the second part of my talk, which is gravitational wave data and how we try to pull out these signals. So gravitational wave data is basically broadband data. So the top panel shows you a simulated gravitational wave signal. But we are typically not interested in very low frequencies or very high frequencies, and we are able to use a huge plethora of signal processing tools to basically clean those kind of frequencies out. And what you have is this, a reasonably clean data here, which has a gravitational wave signal possibly buried in it. But the other type of, so the question, of course, then is that given this kind of data, is there a signal in this or not? So this is the first kind of question that you ask typically. And once you're convinced that there is a signal that is hidden, as you can see, this light blue trace that is hidden in this dark blue trace of noise, so it's completely smothered by noise, you then first ask the question, is there a signature for gravitational wave signals? And if so, how do we estimate the source mass? So the mass of the black hole, the spin of the black hole, how far it is, and how is it oriented with respect to my line of sight, and so on and so forth. How do you estimate those kind of things from something like this? So this is your input, and the output is a picture like this. So which gives you the probability of various parameters in a multidimensional parameter space. So I really don't want to spend a lot of time in the. So how much time do I have? I'm sorry. 15 minutes maybe?
So 2-3 minutes. In 2-3 minutes, if you can wrap up, sir.
In 2-3 minutes. Maybe I'll just go to the conclusion.
Okay.
Thank you very much for your attention. Bye-bye. I'm done with my talk.
Sure, sir. Thank you, sir. Thank you very much. There is a question for you, sir. Yeah.
Sir, what is solar mass radiation? Solar mass या मैं हिंदी में बोल रहा हूँ सर. सोलर मास जो रेडिएशन है उसको जो डिटेक्ट करने का एक पर्टिकुलर एरिया है, जैसे कि इक्वेटर के ऊपर या टॉपिक ऑफ कैंसर या टॉपिक ऑफ कैप्रिकॉर्न के ऊपर. क्योंकि मैंने ना सोलर सेल एफिशिएंसी पे जब काम किया था ना अपना, तो सोलर मास रेडिएशन का यूज किया था. 4 सोलर सेल एफिशिएंसी निकाली थी हाइब्रिड पेरोव्स्काइड की. तो मैंने जो सोलर मास रेडिएशन यूज किया था वो यूएसए के एक पर्टिकुलर एरिया में दिया हुआ था. तो क्या सर ऐसा होता है कि पर्टिकुलर एरिया में सोलर मास रेडिएशन को कैलकुलेट करते हैं?
I think he is not here. So I think no. Others are there. So I think he wrapped up, and he thought that. So I will ask for the last speaker of today, Professor Arnava Mukherjee, who will be speaking about the aspects of fundamental physics and astrophysics with compact objects in gravitational waves. Are you there, sir? Professor Arnava Mukherjee? Yes. Hello. Am I audible to you?
Hello, hi. Can you hear me?
Yeah, we can hear you.
Yeah, okay.
Now you may share your screen with us.
Yes. Okay, hang on just a minute.
Sir.
Yeah, I am trying to share it. Somewhere it is.
Share your screen. Please click on the share. Present now.
Hello.
Please click on present now and then click on the entire screen.
Yeah, so it is actually saying that something is blocking this setting in the permission section. So I am trying to resolve that actually.
I don't think I have given all permissions to everyone.
Yeah, no, I am just trying to resolve it.
On the top left, there is that.
Okay, so what I will do, I'll switch to a different computer just in case some firewall is blocking me here. Just within a minute. I hope this is.
He needs to do this. He needs to click on here and then allow on permissions on his browser.
Okay.
And then he needs to allow here.
Hello. Professor Mukherjee, are you there? So if you are not there, so I will request Professor P.C. Deshmukh for the concluding remarks of the seminar.
He may be coming up.
If he comes, then we will continue. We will wait for 5 minutes, but during these 5 minutes, I think if you can say something about what has been discussed. So one question was there. Yes, sir. If you can share.
Yeah, I am trying to. There is some kind of firewall that is preventing me to connecting. I am trying to resolve it actually.
This firewall, I think it is
side possibly.
It is from your side only, I think.
Right. It looks like it is my side. Yeah.
So meanwhile he connects. Let us. आपका सवाल क्या था? जरा रिपीट करिए।
सर मेरा क्वेश्चन था सोलर मास रेडिएशन।
मैंने सुना लेकिन मुझे लगता नहीं कि ऐसी कोई चीज है जो जहां तक मैं समझ पाया।
जी
ठीक है।
एक पर्टिकुलर एरिया में मुझे ऐसा लगा जब मैं उसको मतलब
एरिया स्पेसिफिक उसके कोई डेफिनेशन होगी।
टॉपिक ऑफ कैंसर पर या टॉपिक ऑफ कैप्रिकॉर्न पे ये शायद वो सोलर मास को निकालते हैं।
रेडिएशन इंटेंसिटी हो सकती है। रेडिएशन इंटेंसिटी दैट वी रिसीव फ्रॉम द सन और समथिंग
वो तो इक्वेटर पर होगी, लेकिन सोलर मास रेडिएशन की मैंने एफिशिएंसी निकाली थी सर एक मटेरियल्स की, तो उसमें मैंने यूज किया हुआ।
Maybe you can share that work with some of us and we will see if we can figure out what it means. लेकिन जहाँ तक कि मैं समझ पाया तो I am not able to relate it to anything that I am familiar with.
So I will need to read this further about it. तो आप जरा वो references share करें.
Okay.
Professor Mukherjee, will it be possible for you?
Yeah, I am trying to. I'm not very sure. I'm trying to resolve it. Yeah. No, it's blocking me from sharing the screen for some reason. Sorry, settings for this website.
Yes, as suggested by Patrick Das Gupta, sir, you may use your mobile.
Yeah, but
that mobile you can show us the screen of your laptop. It is also one possibility.
So it presently saying that there is a some setting issue in Safari setting from this website to update some permissions. I'm not very sure what exactly.
Yeah, it is at the taskbar of your screen at third in the taskbar you will see 4 different symbols. Okay. You are in a different browser. ये है ना सफारी कैसा ये तो है सफारी अच्छा so I think you may use some different browser if it is possible for you to.
Yeah, that I can try. That I can certainly try. Yeah.
Meanwhile, मुझे लगता है सर कि आप
नहीं will wait.
We will wait.
I think he will hopefully succeed in using another browser and connect.
कल जाना तो कल वो परसों नहीं गया
that link
Professor Sharma, may I suggest something to maybe resolve the issue?
Sir, please, sir.
If Arunava doesn't mind, he can send you his presentation and you can display it on your local computer.
Yeah. I have requested him for that.
Okay.
Earlier also. Oh, I think he is not able to. Sir.
Maybe I should also mention that Professor Deshmukh was my teacher and mentor in IIT Madras.
Sir, it is very nice.
I'm very proud of you, Suresh.
Well, sir.
I was very excited when I saw your name in the list of speakers and waiting to hear you. And it was wonderful to hear you. We have not met for some time. We met in Bangalore not too long ago. I'm looking forward to another opportunity to meet you very soon. So, congratulations for all the wonderful work you and your colleagues are doing, Suresh.
Thank you, thank you, Professor Deshmukh. It is always wonderful to see you, even if it were on the screen.
He is carrying, sir, same energy as
Yes,
those.
it's amazing.
I suppose on those days when you were a student, he is always guiding, inspiring, helping.
Yeah, but Suresh had that
motivating.
energy all along. I've seen it for a long time.
So आज क्या है सर, आज हिंदी दिवस है. मैं थोड़ा सा बताना चाहूंगा. दो तरह के टीचर्स होते हैं. एक होते हैं पारस दीक्षित. पारस के साथ क्या होता है कि उससे अगर कोई लोहा भी टच करता है तो वो सोना बन जाता है. तो शिक्षक ऐसा माना जाता है, 90% तक माने जाते हैं. कुछ लोग लोह दीक्षित होते हैं, वो अपने साथ जंग लगा देते हैं, वो अलग बात है. पर पारस दीक्षित शिक्षक को माना जाता है. और पीसी देशमुख सर जैसे कुछ लोग दीप दीक्षित होते हैं. तो जो ज्योति इनमें है, दीप के साथ एक सबसे बड़ी बात होती है, जो एनर्जी और जो क्षमताएं उनमें खुद में होती है, वो आप जैसे लोगों में भर देते हैं. और निश्चित रूप से ये श्रृंखला आगे से आगे चलती रहती है. सो वी आर आल्सो ब्लेस्ड कि हम भी इसी चैन में कहीं न कहीं हाथ लगा सके.
Both of you are very kind and generous. I think I suggest that you both have a glass of water. Calm down. Have a glass of water. Thank you so much.
I hope to see you again soon in Bangalore.
Yes, I would love to do that.
Yeah.
And moreover, sir, I would thank all of you, even including Madam. I think she has left.
Yeah,
Archana Pai, ma'am.
Yes.
And then Patrick Dasgupta, sir, he will not remember me. But I was there for 15 days, sir, at St. Stephen's during October 2003. There was a refresher course on theoretical physics conducted by Indian Academy of Sciences. And you were young then, at that time. I was also young at that time, around 23 years old. But I enjoyed. You were there, and then Professor Rai Chaudhary was there, and Professor Hyderabad ke Vice Chancellor bane the University of Hyderabad ke. He was from JNU. Chaos पर काम करते हैं. I forgot his name. Professor Dasgupta, if you can remember. Yes, I do remember it. Sir, SERC course, sir. Professor Mukunda, yes, Professor Mukunda from IISc Bangalore and Indian Academy of Sciences, he was coordinating that. And then from JNU, one professor who was teaching us classical physics, I don't remember his name, but I remember that he used to consume cigarettes. So many cigarettes are consumed. But he was he is a very nice teacher. Professor Raj Dasgupta, and he usually came to North Campus from JNU. One day he was sharing with us that it takes 2.5 hours for him to come to the North Campus. Yes. Professor Ramaswamy. Thank you, sir. Professor Ramaswamy. And I think he works in the field of chaos.
I see.
Sir.
That's right. Chaos. Yes.
Chaos पर काम करता है ना वो. Yes, sir. So ये आज एक उपनिषद चल रहा है सर. और I think Professor Arunava, if you are not able to share your screen, please send your presentation to me. We will present that for you.
Okay, yeah, thank you. I am sending that.
Arunava, if it is a large file, you can put it on the Google Drive or something and they can download it.
It's not very large. Probably I will try sending it directly.
Please send me. मैंने निकाला पता नहीं है क्या हो गया. He knows.
I have sent it. It should be on the way.
So I'm sharing it for you. I have received and you can start.
Yeah, sure.
I think it is where it is. It is here.
Yeah, exactly.
Is it visible to you? To
Yeah,
everyone?
very much. Yeah.
So you may start, sir.
Yeah. First of all, okay, I hope you all can hear me well, right? Um, so, so yeah, first of all, I am extremely sorry for this inconvenience and delay due to this technical glitch. Once in a while, it becomes a bit difficult to say a few things here. Um, Having said that, I would like to thank very much to all of the organizer for this, 2 days national seminar series, and in particular to Professor Sharma for inviting me to give this presentation. I would like to keep it brief, particularly because it is already a bit late and you had an exhaustive, throughout the day seminar. It is exciting and good to see that so many different frontiers, different areas has already been covered, and there are still some interest left in the room, in the audience to sit through. So bear with me, with my apologies. So let me begin straight away. So in this last talk in today's seminar series, I would like to briefly mention about a few key topics that are very interesting to, at least to me, and maybe some of you also in the future, that has a great prospect in gravitational astrophysics and certain kind of fundamental physics that we will go through. Okay, so Professor Sharma, maybe next slide, if I, yeah. Presentation mode, I think it should be fine perfectly. Like it's a PDF file, so Control L or something like should work. Yeah. So yeah. Okay. If it is.
No, you please continue.
Yeah. So so this is to give you a brief overview of the astrophysical compact object in the large context, in the large landscape of gravitational field strength. You have already seen one of these figures. What it says is that in the, if you focus on the right side of the figure, it gives you two parameter family that characterize the strength of the gravity. In the x-axis, in the horizontal axis, it gives you the measure of the gravitational potential. In the vertical axis, in the y-axis, it gives you a measure of the curvature. Technically, this is the square root of Scratchman curvature scalar, which is, if you are aware of the Einstein GR, so this is a quadratic term in full Riemann curvature tensor are mu nu rho lambda downstairs and are mu prime rho prime lambda prime. If you write in upstairs and you contract that and take a square root, that is the exact quantity it is plotted. So it is a proxy of how curved your space-time is, as described by general theory of relativity and as mentioned already by Professor Sudip Bhattacharya and maybe others also, that for compact objects like neutron stars and black holes, they fall in the extreme part of curvature and extreme part of the potential, extreme part of the gravitational potential that you can see in this vertical red line at numerical value of 1. That signifies the horizon of the black hole if you cross that line in the right hand side. Now, gravity, as you all know, is the weakest fundamental force, and any measurable signature of gravitational wave has to come from massive and compact objects, purely due to the fact that it is very weak. It very weakly couples to the matter part. But exactly due to this reason, this is an excellent tool to probe the strong field gravity. What it means is that if you are able to detect the gravitational wave signal, then automatically you are actually probing, you are actually playing with those objects which are in the extreme part of this parameter space. Not only that, this type of extreme objects can be used to explore exotic properties of matter and under extreme condition. For example, neutron star, as you have heard already in Professor Sudhir Bhattacharya's talk, that are made of matter with ultra high density and in extreme conditions like extremely strong magnetic field and around a part of the gravity where the space-time curvature is extremely large also. Can we go to the next slide, please? Yeah. So we have in the previous talk we have seen that LIGO, Virgo, and Kagra collaboration has detected a whole bunch of the order of 100 gravitational wave events. Each of these events, as far as we know, are a consequence of a two-body merger. It could be either a black hole merger, or a black hole neutron star merger, or a neutron star merger. So this is a summary plot where you can see the gravitational masses of each merging compact object, that is neutron star or black hole, and their distribution throughout the entire observation history. Next slide, please. Next slide. Yeah, thanks. So here is the summary plot of all BBH sources that we have seen till GWTC catalog, Gravitational Wave Transient Catalog 3. So here you can see in the x-axis the total mass of the system, and in the y-axis you can see the mass ratio. And some of the very loud and prominent sources that have been observed are also plotted here. Along with that, a bunch of neutron star black hole sources will also be shown in the coming plots. Next slide, please.
So next.
Yeah. So in this slide, you can see there are three diagrams. It shows the binary black hole mass and spin distribution, and also their distribution in cosmological redshift. These are one of the latest published results, and what they tells us is that how the masses and spins in this merging binary black hole system and neutron star black hole system are distributed throughout our universe, and how those properties change as a function of cosmological redshift parameter Z. So this will be very useful for us to infer the origin of this type of system through different evolutionary pathways. Next slide, please.
Next slide.
Yeah. So, knowing this population of binary black hole system, their masses, their spins, and their cosmological redshift evolution, will be very useful to know how the binary black holes form in nature, how they come closer together and they merge. For example, there are at least two very well-known, very established formation channels, formation pathways. In the left side, you can see that you have an isolated, in situ binary stars. They are main sequence binary star, one of them first evolve, and it expands and it fills its Roche lobe, and it transfers certain amount of mass to the other object, other star, and then it collapses to a black hole, and eventually the second object also goes through a supernova and collapses to a black hole. Now, if it so happens that both the supernova kicks are not strong enough or not oriented in a unfavorable direction, then the system remains gravitationally bound, and if their separation is not too large, they can start emitting gravitational wave and come closer together and merge within Hubble time. This is a well-known formation channel. There could be other formation channels which are very different. You can have multiple compact objects, or even the stellar system in dense globular cluster-like environment, and you have a dynamical capture of multiple, stellar objects, and then they can eventually come closer together and sequentially go through a supernova explosion and collapse to a black hole. This is a very different type of formation channel, but knowing the mass, spin, and their cosmological evolution, the theoretical astrophysics persons will be astrophysicists will be able to predict or infer which type of evolutionary history a particular source might have gone through, and this is one of the open area of research. Let's go to the next slide, please. Yeah. So unfortunately, this video will not play here in PDF, but you have probably already seen this slide that we have already observed neutron star merger system, that is GW170817. There, the LIGO-Virgo collaboration first detected a very clear charge signal that is shown in the lower part. Video won't play here. And within 2 seconds of this charge signal, peak of the charge signal, there was a clear detection in Fermi Gamma ray satellite that detected the GRV. Now, this is the first simultaneous detection of gravitational wave and electromagnetic signal from the same sources. Along with that, LIGO-Virgo collaboration has also detected at least 2 confirmed neutron star black hole mergers. These are mixed binaries where one component is more massive, it is stellar mass black hole. The other component is relatively lighter, it's a neutron star. Excuse me. So it is now well established that not only binary black hole merge, but other compact objects like neutron star also contribute to these merger events that we have observed in LIGO-Virgo and Kagra detectors. Now, the significance of presence of neutron star in these events is that neutron stars are made of physical matter, unlike black hole, where all the matter has gone beyond the horizon and is not accessible to the normal classical observer outside, far away from the horizon. Neutron stars have a surface, physical surface, and they do emit other forms of emission, like electromagnetic emission, neutrino, and possibly other charged and uncharged, fundamental or composite particles also. So neutron stars have a larger scope of being observed with other window channels, and they do give rise to the multi-messenger astronomy. Now, let's go to the next slide, please. So what are the implications? There are a whole bunch of implications of having a neutron star in the system that you can observe, but I will mention a few of them here. Next slide. So just to give you a very quick summary, you have already seen this type of slide earlier. So what is a neutron star? Is typically a compact star. It's a stellar disk that is formed after supernova explosion. The typical mass is roughly from 1 to 2 solar mass, slightly larger than 2 solar mass that we know from observational site today. The exact upper limit is unknown because it's a function of, it's a property of the underlying neutron star equation of state, which is not known to the to us. Its radius is roughly from 9 or 10 to 15 kilometer, and density could be in the interior of the neutron star could be as high as 10 to the 15 gram per centimeter cube. That is several times nuclear saturation density. That is the density, highest density known to the heaviest nuclei on Earth, like lead nuclei. The magnetic field is also very strong. Like magnetas, it can go as high as 10 to the 15 Gauss. The primary problem for neutron star is that we don't know what is there deep inside the neutron star interior. That is the core of the neutron star interior. This is completely unknown. And this type of matter, has a very unique property. You cannot create it in normal collider laboratory and accelerator physics to study them, because when you collide two nucleus, it will be hot naturally. A lot of kinetic energy goes into those particles. You need something very special, like a huge amount of gravitational field to hold this, highly dense compact object, which is not hot and not in the excited state, but close to their ground state. And this type of system are also very complicated from the theoretical perspective, because they are essentially a strongly correlated system. The problem that you need to solve is not just two-body problem, but many-body problem, which you cannot solve it perturbatively either, neither from the first principle theory like lattice gauge theory, because you have a very high density. A finite density is a problem for lattice gauge theory because of this infamous sign problem, But it also opens up the possibility that you might have a deconfined quark in the interior and other exotic degrees of freedom. It could be a hybrid star, it could be a strange star and things like that, or a mixed phase of these two. It can also show color superconductivity, at least partially, and superfluidity also in the core of the neutron star. Can we go to the next slide, please? Yeah. So what happens, when two such neutron stars come closer towards each other after the inspiral part, in the late inspiral part, when they are about to touch, they are the companion of each neutron star will exert a gravitational field that is not quite homogeneous. This inhomogeneous gravitational field induces a tidal forces on the extended body of the companion, very much similar to the Earth-Moon tidal system, but much more exaggerated, and that deforms the body and changes the dynamics. So that dynamics, then when you look at the gravitational waveform, you can see the clear effect of tidal deformability at the late inspiral part that has been shown here. For your reference, these black dotted lines are the binary black hole waveform. If the two black holes of same mass are colliding, as compared to that, if the same mass of two neutron stars are colliding with different equation of state, which are proxy for different radii and different scale of the neutron star surfaces, then how the waveform may change. And this signature is imprinted in gravitational wave observation, and from there we can extract those parameters and can learn about their properties of the neutron star tidal deformability and their equation of state. So can we go to the next slide, please? So we have been lucky enough to have our first detection, which was so loud and such a high SNR of around 33 or 35 in joint Hanford and Livingston detector, that we have been able to put some measurement of this tidal deformability parameter that I was telling in the last slide. And here you can see that if you assume certain equations of state, which are shown by this, these grayish curves, starting from this, this diagonal straight line and going all the way top left part. So each curve there represents one particular equation of state. That is, you start with a specific composition as your hypothesis and say how the neutron star tidal deformability should look like, and then you ask this question whether our observational data is consistent with that hypothesis. Then you end up with getting this type of figure where it shows that some of the equation of state predicts an inconsistent, behavior in gravitational wave signal, their tidal deformability should be sufficiently large than what we measure with statistical significance, say even 90% confidence bound. So what it means is that those neutron stars are most certainly not made of this type of matter, which can give rise to this set of equations of state like MS1 and MS1b, if you can see with high resolution in your projector. So immediately we can rule out a whole bunch of equation of state, and we can put a constant of what type of matter the neutron star may not be made of. But we have not been able to yet completely pinpoint this to a only very narrow uncertainty, so that we can tell you what type of matter is neutron star actually made of with a high precision. So let's go to the next slide, please. However, subsequent study have been done following this original first discovery, where people or different groups have been able to put a constraint on the density pressure plane of the parameter space. In the left panel, you can see only these green shaded regions are allowed, part of the parameter space in the density pressure plane, and any equation of state that falls outside must be ruled out, because that is not consistent with gravitational wave observation of GW17817. Not only that, people have taken it further, and people have made an unified analysis of the finite nuclear properties and neutron star merger properties as seen in GW17817 to put a joint constraint. So the basic logic here is that, after all, the underlying interactions in between this constituent matter in the microscopic scale are strong interaction and weak interaction primarily, and you have charge neutrality. Essentially a device screening of your electric charges, but apart from that, it is essentially strong and weak interactions, and that strong interaction sector, which is the primary part that contributes to the density pressure relationship, can be studied very accurately for the low density part in terrestrial laboratory in nuclear accelerators. So when you put joint constraint, you get more tighter bound on the parameter space that is shown in the right side of the panel. And next slide, please. So this then immediately opens up a whole new window through gravitational wave that we can learn in the coming days. So in the left part of the left figure, of this slide, it shows what different types of fundamental particle can reside in the interior of the neutron star. There could be pions, there could be kaons, and both of them being bosons can be in the condensate stage also, phase. And you can have other, higher baryon like lambda baryon, cascade, and delta, all these things. And you have different flavors of quarks, those are also possible. And in the right hand side, this is a schematic diagram of QCD, schematic plot of a QCD phase diagram. QCD is the quantum chromodynamics, that you may be knowing that this is QCD describes one of the four fundamental forces, that's the strongest force, and that you can explore from this type of observations. Next slide, please. Yeah. Now, so far we have observed only binary mergers, but there is a completely different class of objects that's called continuous gravitational wave, which is briefly probably touched by Professor Sudip Bhattacharya. So if you have a spinning neutron star and it is slightly deformed, and in this deformation is not properly axisymmetric, it will emit a nearly monochromatic gravitational wave. But these signals are much weaker, and you need to integrate this, observe this signal for a very long duration of time to integrate the signal to noise ratio so that you can detect that. And this type of emission can be caused by different types of non-radial oscillation modes of the neutron stars also. For example, if you have R mode that is excited in the interior of the neutron star, then it will emit a powerful near continuous gravitational wave signal. Freely precessing neutron stars can also give rise to continuous gravitational wave signal. And not only that, if you have a certain type of axion like dark matter, that can get accumulated in the in the vicinity of a spinning black hole, and it can extract energy to super radiance instability of the black hole. It's a slightly technical term, but that can also give rise to a continuous gravitational wave signal. So if we see a particular CW signal, depending on their characteristics and their properties, we might be able to tell probe and more exotic physics. Next slide, please. Yeah, this slide is a bit busy and I would like to skip it for the interest of time. So we may go to the next slide. Is the last thing in next 2-3 minutes I would like to tell you that there is also a very interesting implication from the gravitational theory side of observing continuous gravitational wave signals. So next slide, please. So we have seen in some of the earlier talk by Dr. Suresh Dorabori and maybe others that gravitational wave propagates as a oscillation in space-time itself, and in the perpendicular direction you can have two different polarization, plus and cross, or circular, left circular or right circular. This is nothing but a linear combination of plus and cross polarization, but there are fundamentally two tensorial polarization in general relativity. Let's go to the next slide, please. Yeah, but if Einstein's GR is only an approximation and the real theory of gravity is something different that is beyond GR, then you can have more than two polarization. You can have at most 6 polarization, depending on which particular theory we are talking about. So here are a schematic diagram of six different polarization. This green figures in the left column are our well-known tensorial polarization in GR. In the middle column, those shown in red colors are the vector polarization modes, and the right column shown in black, black color, those are the scalar polarization. So depending on your theory, whether you are looking at the branch decay or scalar tensor theory, you can have different breathing and longitudinal modes, and you can use your observation that you see in GW detector data to constrain or to pinpoint to the correct theory of gravity. So maybe next slide. I would just very briefly want to mention that detecting CW signal is much difficult than detecting transient binary signal, because these signals are much weaker, and if we don't know the source properties, it needs extremely large amount of computing time, which we currently don't have anywhere in the world, and makes our life much challenging. Next slide, please. However, if we can suitably combine different multi-messenger windows, then it will be very useful. If we have the third detector, even the LIGO India detector in place as proposed in AUM, then that itself will increase the total sensitivity of a coherent analysis for CW signal, and with the same amount of computing cost, we'll be able to search a larger volume of the universe. Next slide, please. Maybe we skip to the next slide. Skip. Yeah. So now, if we combine, along with gravitational wave detectors, if we combine other electromagnetic telescopes, for example, we have GMRT and we have UT radio telescopes, which regularly or at least periodically observes radio pulsars. We had AstroSat, which observes X-ray band, which observes the neutron stars and accreting pulsars in X-ray band. And those information, if we can combine, then we can increase the sensitivity, and there is a potential chance that in next few years we might be able to detect one such signal, which will be of great interest to the community, that can be used for probing extreme matter and strong field gravity signatures that will, allow us to explore unseen territory of fundamental physics. With that, I'd like to conclude here and we'll wait for any questions that you may have. Thank you very much, everyone, and my apologies, sincere apologies for the technical glitch and delay for this presentation.
Thank you very much, sir. Any questions? Now I will request Professor P.C. Deshmukh, sir, to address her with his concluding remarks.
Arnav, are you still there?
Yeah, there.
Arnav?
Yes, yes.
I have a short question.
Sure.
You talked about theory beyond Einstein.
Yes.
Now, similar questions have been asked in a slightly different context. If there is a theory beyond quantum mechanics, quantum physics, which is perhaps more accurate, and if you look at, there is a noise coming from somewhere. So one can look at classical physics as an approximation to quantum physics, and a question has been asked if there is another theory beyond quantum physics to which quantum theory is an approximation. And you refer to theories beyond Einstein theory, suggesting that there may be a theory to which Einstein's theory would be an approximation. Nonetheless, there is at least one paper that I have seen in the context of quantum physics, which is a no-go theorem, that such a theory may not exist. And it is within certain constraints, of course. So has any such study been done in the context of general relativity?
Okay. So, okay, I will try to reformulate your queries, and please let me know if I understood correctly. So, the main concern is that that Einstein's GR may not be an emergent theory from some more fundamental theory. Is that your primary concern, or
yeah?
Or yeah?
Yeah. Yes. In some way, yes.
So the problem is that we know there has to be a, I mean, any consistent logic will tell you that in the fundamental level, at the Planck scale, there has to be a description of matter that is consistent in quantum mechanics.
Yeah, of course.
If you leave the something close to the point of singularity, or where curvature is extremely high,
yes,
in a small curvature limit, if you are confining yourself locally in a small part of space-time, then Einstein equivalence principle say that it is no different than any other inertial observer or equivalent observer. So now we know that quantum mechanics is experimentally verified and correct. Correct in the sense that we have an experimental evidence that the laws of quantum mechanics, what it says, is consistent with the experiment. If so, it has to be similarly taken properly in the whole framework of general relativity. And that's a bit of a problem, because the way GR is formulated is in the form of space-time manifold and continuum. There is no structure of scales as such, and quantumness and things like that. So that is a fundamental problem for which people think that there must be something more fundamental theory that is at play, even when you include gravity sector. But then when you average, when you look things at much larger scale, very much similar to, like, I mean, you go to the large in limit or something like that, a large quantum number that tends to push you towards observable being, described by classical mechanics, a similar
Yes.
thing might have been happening in the general relativity form also. That's the primary reason to probe, as far as I am aware. But regarding the fundamentalness of the quantum mechanics, so as far as I know, maybe my knowledge is limited, but no experimental indication is there that you need something more fundamental than quantum mechanics. So that quantum mechanics itself becomes an emergent theory. I mean, yeah, but maybe I'll be happy to inject
Yeah. Thank you very much, Arnav. This has been a wonderful day, very exciting for all of us. I think everybody in the audience feels extremely privileged that we had the opportunity to listen to some of the most learned scholars in this field all through the day. It's right since morning. Everybody who has spoken is a leader in this field, contributing to pushing the frontiers of our understanding. And it seems that we are really living in very exciting times. And what we are going to discover in, I don't know if it is going to take another 1 or 2 years or 10 or 20 years, but I think there are very exciting advances that humanity will learn about in the what I would think will be near future. Even if it is 20, 30, 50 years, I would call it as very near future, considering how long humanity has taken to get to this point. So the progress now is very rapid, very exciting, and my deepest admiration to all the speakers for their contributions to the field. I would like to congratulate the organizers, particularly my good friend Yogesh Chandra. He has really driven this whole event consistently with a huge amount of effort and commitment. This is very exciting because this brings within comfortable reach of large number of students across the country and perhaps elsewhere in the world as well, who can listen to these talks, listen to these scholars. So it has been a long day. I don't want to add too much. So thank you all very much. Yogesh Chandra, would you like to add anything?
Thank you very much, sir. Now at the last full hour, I would like to request you and sir, please come. Professor Sunil, a small token of honor from छोटा सा एक कोई गिफ्ट टाइप है वो हमारा चीज है.
So for all the participants who are there, joined remotely, very many thanks to all of you.
Yeah, I would also like to thank everyone, particularly the organizers, very much. Yeah.
अब एक बार सब आ जाओ इधर, है ना? एक बार सर के साथ. So thank you very much everyone online present for being with us throughout the day.
Thank you very much. Thank you very much for having us. It's been a nice meeting. I learned a few things. Thank you.
Just please stay for some more moments. You will have a group photo.
Oh, with online participants.
Yeah, online.
Yes, all the online participants will be in the background on the screen.
Okay.
And everybody who is physically here is coming up in front of the camera.
Okay.
Please on your camera also.
Yes, so please switch on your cameras, everybody.
Anjana, Shreya.
All the participants, please switch on your cameras.
much.
Thank you, sir.
Thank you. Bye bye.
Thank you. Thank you, everyone.
Bye.
Bye, Patrick. Bye bye.
Thanks.
Thank you very much.